Hi there, and welcome to this Amazon Web Services Linux Operations Live Lessons course. I'm your instructor, Richard Jones, and I will be guiding you through this series of videos. Through this course, we review a number of key AWS services and tools we can use to automate the creation and maintenance of our infrastructure. We also perform plenty of hands-on, detailed labs making use of the AWS command line interface, AWS CloudFormation, and the Python SDK. Just a little about myself and my background. I have been developing web and mobile applications for the past 15 years and started using Amazon Web Services in early 2009. In the last 8 years, Amazon Web Services has matured incredibly, and I have continually strived to deepen my knowledge of and experience with their offerings by working with companies of all sizes to migrate applications to AWS and build cloud-native applications. As of this video, I have all 5 certifications, including the Solutions Architect and DevOps Engineer professional levels, and have delivered official AWS training to Fortune 500 companies around the world. In this lesson, we discuss the importance of automation, various tools we can use to achieve a highly automated environment, and some common tasks we might see in a cloud operations role. We review the AWS command line interface, AWS CloudFormation, and the AWS SDK for Python. We finish this lesson with our first lab, installing the AWS command line interface tools. First, let's talk about the challenges of a manual process. Of course, if we are doing things, especially in a GUI, click by click and screen by screen, then of course, they're going to be slow. They're also going to be unreliable because as humans, if we do things one day, then the next day, we might come into work without enough coffee, without enough breakfast, without enough sleep. And so how do we know if we want to build out the same exact infrastructure, how do we know we're going to build it in the exact same way every time? If I want a particular environment for development, for testing, for UAT, for production, and then let alone repeating that across numerous regions, we need to build it out consistently every time. And so a manual process is ultimately unreliable in that regard. And then, of course, it's difficult to repeat for the same reasons. We might want the same exact thing to be built out in numerous regions and numerous environments, and we have to be able to repeat that. And of course, as software developers, engineers, we're not necessarily known for our documentation skills. And so doing things manually, there is an inherent lack of documentation that becomes a big problem, especially for compliance and auditing and security purposes. And so all of that together means that, again, difficult to repeat, lack of documentation, all of that adds up to a manual process being ultimately less secure. So the benefits of automation are that it's fast and efficient. Once we write a script, then we can play that out any number of times we want across any number of environments, across any number of regions. And of course, and so we get efficiency out of that. And because we know that something is being done by a scripted process, it's going to be reliable and consistent. And it's going to be repeatable consistently. And then, of course, because it is scripted, all of the resources that are being built and all of the ways that these different resources are connected are inherently documented in those scripts. And so we get inherent documentation. Altogether, automation gives us a much more secure environment and secure process. So that is the importance of automation, and that ultimately is what this entire course is all about, really diving in and understanding some of the tools that we can use to automate our environment to gain all of these benefits. All right, now let's talk about the tools for automation. AWS gives us plenty of tools to use to automate our environments, including the command line interface, software development kits or SDKs for numerous languages, including Python, Java, .NET, PHP, Node.js, Go, and a number of others. AWS also gives us CloudFormation, Elastic Beanstalk, and OpsWorks. In this course, we are specifically looking at the AWS CLI, the Software Development Kit for Python, and AWS CloudFormation. We are going to go fairly deep into these and explore some details, get a lot of hands-on experience with these particular tools. Now, it is worth noting that there are a number of third-party tools out there like Troposphere, Terraform, Ansible, and SaltStack. Now, I've personally used Terraform and Ansible, and those are really great tools. But again, for the purposes of this particular video, we're going to focus on the AWS CLI, the SDK for Python, and the AWS CloudFormation. Now let's talk about some common tasks in AWS. Of course, there's creating infrastructure. We want to create infrastructure for our applications, not only in numerous environments, but also perhaps in numerous regions or in numerous accounts. If we are consultants or where we are doing particular things for numerous clients, then of course we have that. And so we're regularly creating and managing infrastructure. Beyond that, some of the maintenance tasks, and this is by no means an exhaustive list, some of the things that we see that we do regularly would be things like resetting passwords and rotating credentials. Those could be our own passwords. Those could be passwords for members of our team. We might make changes to security group rules, whitelisting IPs, blacklisting IPs, and of course, not only do we need a way of doing that efficiently, but we need a way of recording who did that, why did we do that, and perhaps make a note so that 6 months later we can remind ourselves of why did we whitelist that particular IP range. We might want to inventory our resources. We might want to create new Amazon machine images. And then of course, in terms of EBS volumes and RDS, creating snapshots is a really important thing for disaster recovery, for backups. And not only do we want to take snapshots of our EBS volumes and RDS instances, but we may very well want to copy those to another region for the sake of gaining geographical diversity in our data, for the sake of DR. And so we also want to copy those snapshots to other regions. And then of course, we might have sandbox environments so that our employees can experiment and just play with Amazon and learn new things. But we don't want the resources in those sandboxes living forever. We want to clean them up so that we're not, spending money on things that we don't ultimately need. And the same goes for development environments. As we're going to see, there are ways that we can use AWS as for development, but at night, come 7 o'clock at night, if people aren't using those environments like dev and test, then why run them? We can turn them off at night. We can turn them off on weekends and holidays and save money. And so cleaning up unused resources is a really big thing. It's one of the key processes that we can use to control cost. And all of these things are things that can be and should be automated. So those are just a few of the common tasks that we see in AWS, and many of these we will review throughout this course. Let's talk about the importance of tagging. Now, just as a reminder, tagging is ultimately, or resource tags, are ultimately key value pairs that we can place on numerous resources. Not every resource supports tags, but most of them do, especially EC2 instances, EBS volumes, and so on. By tagging our resources, one, we can help keep our environments organized so that we can find the resources that we need. I can speak from personal experience, having come in and inherited environments where tagging was not really used. It was really difficult to find what I was looking for. Members of the team might have an application and I would go, well, where is it? I don't know what machine it runs on. Or I might see a list of hundreds of machines and think, well, I don't even know what they're being used for. And so we want to avoid that. And we can avoid that by consistently tagging our resources so that when we do see a list of servers or EC2 instances or security groups or S3 buckets, whatever the case may be, when we see that list, we know exactly what they're being used for. And conversely, when members of our team need something for a particular project, for a particular team, for a particular application, we know exactly where to find what they're looking for. Now, furthermore, this is a really powerful thing, is that tagging enables cost tracking. Finance and accounting really wants to know where money's being spent. Now, in traditional on-premises IT, it was challenging for us to allocate cost. We spent a whole lot of money up front for resources that are now running in our data center, but we have a hard time saying, well, we're using this much money for this project or this team or this application because they're all sharing the same servers, the same racks, the same switches, and so on. Within AWS, by consistently tagging our resources, AWS can account for billing according to tag. We can see exactly how much money EC2 is costing us per project, per team, per cost center, and so on. That's all according to the tags that we use. And AWS can break our costs down by tags, and it gets very detailed, very fine-grained, down to EC2 instances, EBS volumes, the disk space, bandwidth, and so on. We can also use tags to enhance automation, and we are going to see some examples of that throughout this course. That right there is very powerful. It seems like a simple idea, but it can be very powerful in our scripting. The last note that I would say about this is that ultimately tags are arbitrary. It's up to you to name the keys and the values, whatever makes the most sense for your application in your business. AWS does not specify what we should or shouldn't do or have to do other than, particular characters being allowed or disallowed. So ultimately, whether you use env versus environment, whether you use all caps or lowercase, whether you use camel case, all of that doesn't really matter. What matters is that we be consistent. If you're going to use dev versus development, be consistent. Pick one and stick with it. If you're going to use uppercase or lowercase, just pick one and be consistent across the board. It is also possible to use IAM policies to control who is allowed to use what resources given a particular tag. And you can use IAM policies to enforce those tagging standards that you set. Let's review the AWS CLI. The AWS command line interface is a really excellent and very powerful, very rich set of tools, which are great for writing bash scripts. And because it's running within bash or ZSH, whatever your favorite shell is, some of those common tasks can be aliased. We can take something that might normally be a really long, complicated string, and instead of typing all of that out every time, we can assign that to a bash alias so that we type 1 to maybe 3 characters plus perhaps an argument and leverage that powerful alias feature of bash. Now, the CLI tools do require Python. For Linux environments, for the Mac, we can install the AWS CLI tools using pip. For Windows, we just run the installer. Now, if you are running applications on EC2 using Amazon Linux, then the AWS CLI tools are already included. One of the great features of the CLI tools and the SDKs are that they auto-discover credentials. There are a number of places where we can store credentials for those tools. They could be within environment variables. They could be in a hidden .aws folder, in a credentials file and a config file, or we can leverage EC2 roles. Now, a lot of these things we will take a more in-depth look at as the course progresses. But the important point here is that the CLI tools will discover that for us. We don't have to necessarily do a lot of configuration every time we go to use them. So again, the CLI tools are ultimately a very rich collection of tools that we can use to script and manage our AWS environments. Now let's talk about controlling the output of the AWS CLI tools. First, let's take a look at the filters parameter. The filters parameter ultimately limits what the API returns. So the filters parameter acts at the API level, and it is supported by many commands, not necessarily all commands, but many of them do support the filters parameter. And so by using the filters parameter, again, we can control how much data actually comes back from the AWS API. Once we get that data back, we can then use the query parameter to control, again, how much data we actually see, or control the format in which we see that data. So ultimately, the query parameter is used to limit or transform what is actually being displayed by the CLI tools. Now, the query parameter is ultimately using a language specified by JMES path. You can find that link here, jmespath.org, and ultimately that is a query language for JSON. And we're going to take a very in-depth look at writing queries based on JMES path, seeing just how powerful that can be and how we can use that to manipulate the data that we get back from those tools so that we can use that data in our scripts, or to use that data in a human-friendly way. And in that regard, we can also control the output. We can have JSON, text, or table output. There are plenty of times when our automated scripts will need JSON output or text-based output. But again, if we want to use these tools as a fast and fluent way to do read operations, then instead of logging into the console and clicking screen by screen through the GUI, if we become fluent at the CLI tools, and especially using the table output type, then we actually get a much more efficient and human readable output. So let's take a look at an example here of some of these filters in action. Here we are seeing an example. One, we're using the AWS command line tool. So we're calling the AWS command. We're using the service here, which is the EC2 service. The command for that is describe instances. And of course, you can see here we're using the filters parameter, and this is where filters typically follow this pattern. The name of the filter is going to be the image ID. The values that we're putting in for that is going to be a particular image ID. And so in this regard, we are limiting what comes back from the API based on the image ID value. We're only interested in that one particular image ID. We could put, in this case, we could put multiple values there and limit the return from the API based on numerous machine image IDs. And then, of course, here, we are also using the query parameter, and we're saying that I'm going to start from reverse. It's easier to read JMES from the right side in this case. So what we're saying is, I want all of the instance IDs within all instances, within all reservations. That's what the wildcards are for. And then I want to control the output. Ultimately, instead of JSON or a table, I want the output to be text. And that's how we can control the output of the CLI tools. using these combinations of the filters and queries and different outputs, we have all the control we need to either script our environments or use the table view for human-friendly reading. And again, we will see that very in-depth as we move through this course. Now let's review AWS CloudFormation. And AWS CloudFormation is a part of a system of tools along with the CLI and the SDKs that we refer to as infrastructure as code. Ultimately, what we're looking to do is apply the same tools that we've been using for software development to our infrastructure. We want to manage our infrastructure as software, and by doing that, we gain a level of flexibility and agility and a much more decreased time to market than we ever had with on-premises solutions. And so ultimately, when we look at the infrastructures that we have, the architectures for applications are often complex. And of course, we've already talked about those challenges with the manual process, reliability, reproducibility, and that inherent lack of documentation. And so we can solve those with scripts, and with CloudFormation, we can also solve challenges with dependencies, parallelization. And so again, the solution here is in many cases to automate with AWS CloudFormation. With CloudFormation, ultimately, everything starts with the template. Now, the template is either a JSON or a YAML text file that is ultimately describing or declaring all of the resources that we want and all of the ways that we want them put together. So CloudFormation we could describe as a declarative programming language. We are not concerned with the order of operations. CloudFormation handles the order in which things get built out. It inherently knows that certain things come before others. And so ultimately, it doesn't really matter what order things are within our template. We are using our template to declare or describe the resources that we want. And we can write that again either in JSON or YAML, which we will again see throughout this course. And then of course, we take that template and we provide that template to the CloudFormation engine. And the CloudFormation engine is what is responsible for actually performing the creation or updates to those resources. Once we've done that, once we've given our template to the CloudFormation engine, we end up with a stack, and the stack ultimately is that collection of resources that were created from that template. The nice thing about that is that now that those resources are all underneath one umbrella resource, if we decide at some point we no longer need that, if it's some kind of a prototype environment or a test environment, something that we're just not using anymore, then we can essentially select that stack. By deleting the stack, CloudFormation will then delete all of the resources underneath that stack. That right there can save us a ton of time. Imagine doing that manually, having to go through and select and find all of the resources that are in a particular environment, and being sure not to delete the wrong ones, but deleting the right ones. So again, by having them all underneath one thing, it makes it much more easy to manage in the long run. So here's a sample template written in YAML. And in this particular case, again, we have the format version, which we can find this in the documentation. This is Amazon's version number. This is not our version, but this is a version of the CloudFormation language that we're using that we get from AWS. And of course, we can give this template a description. And here we are declaring some parameters. In this case, we are declaring the CIDR parameter that we can use at runtime when we give this template to the CloudFormation engine and say execute. Then we can change the values of these parameters and then use those values later in our templates. In this particular example, we are going to, at runtime, specify the CIDR range for this particular VPC. And then, of course, we have our resources. Here, I'm creating a resource that I'm calling VPC. You can see the type of resource is an AWS EC2 VPC. Everything is namespaced. And then you can notice here that we're using this word ref, R-E-F, with a capital R, and that is a reference to the CIDR parameter. You can see here that CIDR matches what we're doing up here in the parameters. And so we're using the CIDR parameter, so whatever we put in here will ultimately be used down here in the actual values for that particular resource. Now, another really powerful feature within CloudFormation that we will see a lot of throughout this course are cross-stack references. Imagine that you have a particular environment that includes a lot of networking resources. You might have VPC, subnets, security groups, network access control lists, internet gateways, route tables, the list goes on. Autoscaling groups, load balancers, and so on. If you try to put everything into one template, that one template now starts to grow and become very large. And two, you end up losing a lot of flexibility. And so instead of trying to put everything in one large template, it can, and oftentimes, make more sense to split it out into numerous templates where you keep things much more focused. And so in this example, we're going to use one template to create our VPC. And here, what we're going to do here is we're going to export a value. You can see here we're saying export, we're creating an outputs section, and we're going to create an output called VPC ID. What we're exporting from this template is, first of all, you can see here we're using another what we call intrinsic function. We're using the substitute intrinsic function to substitute the variable AWS stack name. This is one of the built-in intrinsic variables that we have access to. So we're going to substitute the value of that, and we're going to join that with -VPC ID. And that together will be the name of our export. And then the value of that will be the VPC ID from the resource that's created up here. And now we can use, because we've exported this, we can use that export to import into another template. So the other side of that looks like this. Now that we've exported something, perhaps we create our VPC with one stack, and we want to keep all of our security group declarations and our network access control declarations in their own scripts so that they become easier to manage. And so here in this example, we have two different CloudFormation templates. We have the one that's creating our VPC, and we have another that we're going to use to create our security groups. In this example, we're going to take a parameter called the network stack name, and here, whatever we named our VPC template, we're going to use that as the input for this particular parameter. And now notice what's happening. We're going to take that and we're going to use it here in another intrinsic function called import value. So we're going to import a value, and we're going to, again, use the substitute intrinsic function to take the value of the network stack, plug it in here, join it again with -VPC ID, and now by doing that, we get the same value that we exported from the other template. So you can see by using cross-stack references, we get a really powerful way of organizing our templates, but also having them reference one another. That way we don't have to hard code values, we can reference values that are stored within CloudFormation. Now let's review the Python SDK. For anyone who might not be familiar with Python, ultimately Python is a very easy language to learn and a very easy language to read and write. Python ultimately uses indentation versus curly braces, and it doesn't require semicolons. In many cases, it doesn't require parentheses, and so it has much less punctuation than other languages, and as a result, it becomes much easier to read. Now, the SDK for Python is called Bodo 3. So if you've ever been out there reading up on AWS and you've seen that term Bodo or Bodo 3, then now you know that that ultimately is the SDK for Python. Very much like the CLI tools, the Python SDK, and this is true for all SDKs, it will auto-discover credentials in these places. The Python SDK gives us both a very low-level access to the APIs as well as higher-level abstract access. Generally speaking, it's much easier to use the abstract layers, but if we needed to, if we wanted to do something custom in a way that's different than what the abstractions give us, then of course we could go to those lower-level functions. What I like about using the Python in combination with things like CloudFormation is that Python is really great for changes to our infrastructure that need to happen programmatically. And then, of course, because Python is supported by AWS Lambda, we get a really great opportunity within operations to use Lambda in places where we may have used cron in the past. That way, we can take our scripts, put them into Lambda, and now we don't have to manage a server for the case of operations. So again, the Python SDK, really easy to learn, really easy to read and write, and we will get a lot of hands-on experience using the Python SDK throughout this course. Let's take a look at an example, just a little bit of Python code using the SDK. So again, you can see how clean Python is. Very little punctuation. We are importing Bodo 3, which is that high-level abstracted resources. We're also importing Bodo Core, which gives us lower-level access to things. Here, we're setting up some variables for our S3 buckets and keys. We are creating a Bodo 3 resource called S3, and then we're going to use the S3 client. We're going to get a reference to a bucket using that bucket name variable, and we're going to call the download file function using the keys that we've specified up here. We're going to download this to our local file system, and then of course we are trying and then catching exceptions as well. So you can see very straightforward, very clean example of using the Python SDK. Throughout this course, we will be creating a number of resources within AWS. And all of those resources, networks, subnets, internet gateways, security groups, load balancers, auto-scaling groups, RDS instances, all of those will ultimately go towards creating our end result, which is containerized services. In that regard, most of the labs do build on one another. Some of them are independent, but just keep in mind that because most of the labs build on one another, if you try to skip ahead several lessons, then some of those labs might not work. The labs are meant to be performed in a particular order so that we can achieve containerized services. Now, in order to perform these labs, you will need a few things. First of all, we will need 2 separate AWS accounts. They are really easy to create. You just put in your email address, create a password, enter your billing information. And I do recommend that when you do that, that you create email aliases so that you have one email from which you can receive email notifications from Amazon. If you're using Gmail, then Gmail supports the plus sign operator, and so you don't, that already gives you an alias. You could say your email name plus admin, your email name plus development. And so we're going to be creating two accounts, one for what we're going to call our admin account and another AWS account for what we will call our development account. And through these labs and lessons, we will see just how we can connect those accounts and how we can leverage them for different purposes, how we can leverage multiple accounts to achieve segregation at the account level. So besides the two separate AWS accounts, we will also need to be running on some kind of Nix-based system. I have tested these labs for Bash and ZSH, so I can speak to them working on Bash and ZSH, but I can't speak for any other shells. We will also need Docker, at least Docker version 17.03. Now the code for this class is available on GitHub. You can just follow the link on the product site wherever you are watching the video. A link will be available there. And as far as going through the labs is concerned, I would encourage you to type the commands out. Don't just copy and paste. So type, don't just copy and paste. And of course, this is one of those situations where I'm asking you to do as I say, not as I do. Within the labs, you will see me copy and paste quite a bit. That is simply for time, for the sake of not forcing you to watch me type out long strings every single time. So yes, for the sake of the video, for moving along, I will be copying and pasting, but for the sake of your own learning, for the sake of helping you to ingrain these commands and languages and principles, I would suggest that you actually type them out. And then once you've done that once and you understand what's really going on, then of course you can go on and copy and paste them and modify them on your own for your own needs. And so in that regard, I would highly encourage you to use this code, take inspiration from these labs, and apply it to your own scenarios that you're trying to solve. One last point that I'll leave you with is about my local environment. People ask me about this. I am running Mac OS 10.12.5, and I'm also using, as my shell, I'm using ZSH with a plugin called OhMyZSH. You can Google that and find that is also available on GitHub. OhMyZSH is a very rich, comprehensive collection of plugins for ZSH. It includes some really powerful features like auto-completion and highlighting for Git, as well as for the AWS command line interface. For my text editor, I use a text editor called Atom that's available here at atom.io. Really powerful, really flexible, and extensible text editor. One final thing here is that I do want to point out that as we move through this course and perform all of these labs, what you will be seeing, what you will be performing is really a way of doing things. It is not the way of doing things. So I would encourage you to go through these labs and see it in that way. See it as just one of many ways in which we can achieve something. There are numerous ways to achieve automation within AWS, and this course focuses on the AWS CLI, the Python SDK, and AWS CloudFormation. You don't have to use these tools. And if you do use these tools, you don't necessarily have to use them in exactly the ways that we're seeing in this course. So I would encourage you not to stick with exactly what you're learning here, but to, again, see it as a way of doing things, and as you move forward in your career, open yourself to exploring other ways of doing things. And so I'll leave you with that, a note about the labs. In this lab, we will install the AWS command line interface and the Python SDK. So first, we're going to open our bash commands for this lesson. Now, of course, all of these could be run as one script. You could just execute the script, but we are going to walk through these command by command just to see what's happening. So the first thing that we want to do is be sure that we update our package manager. If you're running on Ubuntu, that's going to be apt-get. If you're on a Red Hat family of Linux, then that, of course, will be yum. In this example, I am running bash within an Ubuntu machine. So first thing that we're going to do is update apt. So let's go ahead and do that. And we're going to apt-get update. Now, in this particular example, I am running as root. I, of course, don't typically do things as root, but for this example, this could be scripted to install things on EC2 instances during their bootstrapping processes. Remember that user data on EC2 executes as root, so it's a good idea to see how things like this will execute as the root user. So here we're going to say apt-get update, make sure that all of our apt-get repositories have been updated. And now from there, let's see what's next. The next thing that we want to do is, here's a few commands that first, using the hash command, will check to see if Python, curl, and JQ are installed. I'm sure most of us know what Python and curl do, but JQ is a really powerful JSON parsing and querying tool. So that we will see examples of using JQ in some of the upcoming labs. So we want to ensure that all of those are installed. So here I'm going to make sure that Python is installed. I'm just going to paste that, and there we go. You can see here the only reason it's going through all of this stuff is because here the apt-get install Python with the -yes force install option, that's running because the hash command determined that Python was not already installed. So there we go, we have Python installed. So the next one, let's make sure that we do indeed have curl. If it's already there, then fine, we'll just use it. Otherwise, if it's not there, then it will be installed. So again, we're going to use the hash command hash curl to see if curl is installed. If not, we're going to use apt-get to install it. So let's go ahead and run that one. Now, if you're running this on a Mac OS, then of course you can use other tools. You can use installers, Mac OS packages, or Homebrew in some cases. But this example is installing for something like Ubuntu. And again, if you would prefer to do this on a Red Hat family like Fedora or CentOS, then you could very easily use yum instead of apt-get. So here, let's go ahead and make sure that JQ is installed. I'm going to again copy that. Again, making sure that testing whether or not JQ is installed. If it's not, using apt-get to force the installation. And there we go. So now if we clear all that and we do a which just to be sure, we can say which Python. There we go. Which curl and which JQ. They are all installed. I'm going to clear that again. Now, once Python and curl are installed, in order to keep going, we also need pip. So pip is a Python package installer. So I'm going to copy this script here. So ultimately, we're going to be using curl to download this get pip Python script, and we will pipe that to the Python binary. So I'm going to go ahead and copy that. I'm going to paste that here. And there we go. It's downloading pip, running through its installation, and there we go. Now we have pip installed, and we can verify that, I believe, with pip -- version. There we go, and now we have pip version 9. You may end up with a later version. Okay, so now that pip is installed, we can use pip to install the Amazon Web Services command line interface tools. So I'm going to copy that, pip install AWS CLI. The AWS CLI ultimately uses Python, and it uses internally it uses the Python SDK. It uses Bodo Core, which is the low-level functionality of the Python SDK. It also uses a number of other Python libraries, most of which we don't really need to be concerned about. So there we go. Now we have the AWS CLI tools successfully installed. So from there, first we want to make sure that we're getting a particular version. We should get something greater than 111.9.3. So let's just see what we got installed there. I'm going to AWS -- version, and we received 1.11.113. Again, you may end up getting a later version installed, depending on when you watch this video and perform these labs. So let's clear that one more time. And the last thing that we're going to do is install the Python SDK called Bodo 3. Now, Bodo 3 and Bodo Core are both part of the Python SDK, but they are essentially low-level versus higher-level abstracted functions. So Bodo Core gives us the really low-level functionality. Bodo 3 is giving us that higher-level abstracted functionality, which we will generally be using. So the last thing that we're going to do here is pip install Bodo 3. Just like that, pretty fast. Now we have Python installed, we have JQ installed, we've installed the AWS CLI tools and the Python SDK. I think we can agree that security is one of, if not the most important aspect of our environments. And in AWS, security starts with our accounts. In this lesson, we cover managing users, groups, roles, access credentials, and multi-factor authentication. Let's review credential types that we see within AWS. If you find yourself logging in with an email address and a password, right then and there you know that you are ultimately logging in to what we call the master account. And remember that the master account has root access. There is no way to limit the permissions that are granted to the master account. The master account can perform any action on any resource at any time under any condition. There is no way to limit that. And generally speaking, we don't use the master credentials for day-to-day operations. Ultimately, what we want to do is create admin users in order to do our day-to-day operations. We want to create users and groups that we can limit their permissions in case we feel like credentials were compromised. In order to access the AWS Management Console, we will log in with a username and a password. This is very different from an email address and a password. By logging in with a username, you know that you're logging in with an IAM user. Now, if we're going to be using the CLI tools or the SDKs, especially locally, then we will need a combination of an access key and a secret key. If we are using the CLI tools or the SDKs on EC2, then we should be using roles. The CLI tools and the SDKs will still need access keys and secret keys, but they can get them through the use of EC2 roles, and we will talk more about that later on. So again, as a review of credential types, we have email address and password for the master account, username and password for logging into the AWS Management Console, and access keys and secret keys for use with the CLI tools and the SDK. Now, as far as credential best practices go, remember, again, the master credentials have root access. They cannot be limited. So we want to protect those master credentials at all costs. And I say that, I want to draw strong attention to that because companies have gone out of business as a result of their master credentials being compromised. I have read stories of companies being held for ransom and having production resources deleted, and then as a result, the company is now out of business. So it's really, really critical that we protect those master credentials as well as possible. One of the things that we can do is, one, enable multi-factor authentication. Also, delete any access keys that might exist on those master credentials. We won't use them anyway. That just goes against best practice to be using access keys that belong to the master account holder. We should enable a strong password policy for our organization in that account. For any users that need to log into the console, we should implement a strong password policy, leveraging a certain number of characters, uppercase, lowercase, symbols, and even perhaps disallowing the previous 3, 4, or whatever number of passwords. Another thing that we absolutely don't want to do is embed code or embed credentials within our code. We should not be doing that. There are a number of not only logistical concerns, but security concerns as well, right? If you embed credentials within code, if you need to rotate those credentials like we should be doing regularly, then now you have to redeploy code for the sake of changing credentials, right? If you put them in environment variables, they could be exposed. If they're in the code, other developers could find them and perhaps use them in ways they weren't intended. So ultimately, if we are running applications on EC2, then we should be using roles for EC2 so that the CLI tools or the SDK tools can use those roles to get temporary credentials that we'll talk more about as the course goes on. Another thing is that we definitely should not be sharing credentials either. Each user should get their own credentials and they should keep those credentials to themselves. And of course, as far as security goes, we should follow industry best practice that says follow the principles of least privilege, giving users, groups, roles, and so on enough permissions to do their job, but not enough to be dangerous. Now, in a large organization where you have perhaps hundreds or thousands of IT employees that are accessing AWS, then we probably don't want to use IAM as a place to store users and groups of users. We want to use our existing directories such as LDAP or Active Directory. And in those cases, we will use federation for large organizations. So federation just means that we're going to use an existing directory and authenticate against that existing directory, call the Amazon services to get temporary credentials that those employees can use for a limited period of time. Right, let's talk about how we can leverage multiple accounts with AWS organizations. With AWS organizations, this is a service that allows us to group multiple accounts together and relate them to one another. Before organizations, we had access to consolidated billing, but it meant that we were managing these different accounts for different purposes on our own. The overhead and the organization was done on our own. And now with organizations, we have some help from AWS. Now, this is very true for larger organizations where you have perhaps multiple business units. You might have multiple projects, multiple cost centers, multiple teams that all want their own isolated account and their own isolated environment, but still being a part of a larger organization. So with AWS organizations, first we create an organization. And then within that organization, of course, we have what we call the root, and the root is essentially the very top of that upside down tree. The root is essentially the account that created the organization itself. Now, of course, that master account can be anywhere within this upside down tree. In this particular example, I've just drawn it here to make it clear that the root and the original master account are very much one and one. Now, within organizations, we can create what we call organization units, and organization units could represent, this is just one example, they could represent different business units. They could represent subsidiaries. They could represent projects, and then you could have different accounts here. In this example, we could have a project as the organization unit, and we could have environments here underneath these separate accounts. We could have, again, subsidiaries over here, and you can see here, according to this tree diagram, that an organization unit can be grouped underneath another organizational unit. So we can go just about as deep as we want to go, where ultimately the various accounts are what we might describe as leaves on this upside down tree. And the way that you use it is up to you. If you want to separate this by project, by team, by organizational unit, if you want to separate U.S. operations from European, from Asian operations according to organization unit, then you can do that. There is nothing within AWS that says you have to do anything in any particular way. They've tried to make this as generic as possible to suit the needs of your particular business. Now, another thing that we have access to here within AWS organizations are service control policies. Service control policies are a way of limiting what these organization units and their sub-accounts are allowed to do. Let's say that I have one organization unit that is only doing data archiving. They're only going to use perhaps S3 and Redshift. They're not going to be using Kinesis or queue services or simple notification service. So with a service control policy, we can say that one particular organizational unit, we could even apply these to specific accounts. We could say that those organization units or those accounts are not allowed to use simple notification or simple queue service, but they are allowed to use S3 and Redshift. And so again, service control policies allow us to control what an organization unit and what an account is allowed to do. Now, it is worth noting that service control policies do not apply to the master account, the account that created the organization. Even if we place this account underneath one of these organization units that has a service control policy attached, this master account remains unaffected by service control policies. So again, this is a way that we can organize our Amazon account and resources according to how our business is organized. Along with AWS organizations, we also gain access to consolidated billing. Now, effectively using AWS organizations requires understanding some of the terminology. As we've talked about, an organization is that very top-level organization that does represent our larger business. And then, of course, the root is the very top of that upside-down tree. An organization unit is how we can further start to segregate different things in our business. Again, that's up to you to use that for whatever purpose makes sense, whether it be subsidiary, business unit, U.S. operations versus Asia operations, and so on. The account that we saw there is actually what contains those AWS resources. So all of the resources that we create, EC2 instances, load balancers, S3 buckets, RDS instances, and so on, will be created within those individual accounts, and the accounts will be grouped according to organization unit. Now, in order to make this work, ultimately we create our various accounts for their various purposes. Again, we could have an account per project, we could have an account per environment, development versus production, and so on. That is totally up to us, But ultimately, we create our various accounts, and then starting from that root account, the root account will send invitations to the other accounts. And so that's how it's through an invitation that we get another account to join that organization. As I've talked about, service control policies specify what services and actions are allowed to take place within that particular organization unit or account. We also have what we call feature sets. So when you are actually in there, when you're in the console and you're looking through AWS organizations, you will see the various, the two different feature sets that we have access to. The first one would be simply consolidated billing. That if you choose that one, you're essentially saying that I'm only using organizations so that I can consolidate the bills from all of these various accounts and have one bill to pay at the end of the month. Now, if you wanted access to the service control policies, we will need to enable the all feature set, which will include service control policies. So again, that is AWS organizations, how we can organize our various accounts according to whatever makes the most sense for our particular business. A part of AWS organizations is also consolidated billing. Again, consolidated billing is that we can have many accounts but still pay one bill. We have one account that is dedicated to essentially paying the bill for all of the other accounts. One of the nice things about consolidated billing, aside from the fact that we get one bill, is the fact that we get aggregated volume pricing. So keep in mind that a lot of AWS services are tiered in their pricing. So bandwidth, as an example, you might pay a certain amount up to 8 terabytes, and then another smaller amount for bandwidth above 8 terabytes. So in one classic example is if you had two accounts, one account did say 7 terabytes and another account did 5, individually neither of them would qualify for that next tier pricing. But if they were consolidated so that 7 plus 5 equals 12, now you could gain the tiered pricing discount on those 4 terabytes that go above 8 terabytes. So that's aggregated volume pricing, and that applies to all services when you see that service is tiered in its pricing. We also have reserved instances, and the reserved instances can apply to all accounts. So it doesn't really matter which account buys the reserved instance. With consolidated billing, if one account has purchased, 10 reserved instances but only used 2, then the other reserved instances can be applied to other accounts. And then, of course, we also have, as I've mentioned, detailed billing. When you turn detailed billing on, those reports can be published regularly throughout the day, every day. Those reports can be published to a S3 bucket. They are published in CSV format, and all of the costs are broken down by service, by region, by availability zone, and, as we've mentioned before, by tags. And so we can download those, we can import them into spreadsheets, you can do all the pivot tables you want to do, you could import them into Redshift. There's a lot that you can do with those reports if you really want to get some detailed information as to where your money's being spent. Let's review roles for elevated privileges. Another thing that we can do here within AWS is have really fine-grained control over who is allowed to do what under what circumstances. So one of the really powerful things that we might make use of are roles, not only roles for EC2, but roles for our users. Now, in this particular example, this is assuming that we are using the IAM, the Identity and Access Management Service, to manage our users in groups. If we're doing federation, then this doesn't necessarily apply, at least in the same way. So if we are using IAM to manage our users and groups of users, one thing that we could do is, let's take a look here at an example IAM policy that is being applied to our developers group. So here in this example, we have a group of users that are developers, and we could say, according to this IAM policy that's applied, that our developers are allowed to launch new EC2 instances. You can see here that they are allowed to launch EC2 instances, and perhaps a few other things, but for the sake of this demo, they're allowed to launch new instances. They are also allowed to assume a role. Notice here that we're specifying the security token service, STS, and we're saying that they are allowed to assume a role, and we are giving specifically an ARN, an Amazon resource name, specifying that particular role. And of course, the role itself has its own policy. And that policy for that role, the lead developer role, might say that now, after assuming that role, we are now allowed to perform the EC2 terminate instances action. Now, combined, this will not prevent developers from terminating. It just means in this particular case, we're using the role as a way to gain elevated privileges. By just being a developer, we understand that terminating an EC2 instance can be a dangerous operation. We don't want to do that by accident. We want to do that through intention. We want to know that that's what we intend to do. And so in this particular example, we could say that the lead developer role, giving us access to terminate EC2 instances, we could describe that as kind of a safety grip, providing one more step to go through in order to gain those privileges so that, yes, indeed, I do intend to terminate those instances. By adding that layer of difficulty to it, it creates an extra layer of security, and it creates that step so that you know that you intend to do that and that you're not going to terminate something by accident. So that's just an example, just one example of how we can use roles to gain elevated privileges. This could be a group of DBAs having access to RDS, gaining and assuming a role to gain elevated privileges for the purpose of deleting or archiving or doing some other potentially dangerous operation on that RDS instance. So again, we can use roles for our IAM users so that they can gain elevated privileges, and not just within one account. This particular role over here, the lead developer's role, could be in a separate account, and we are going to see examples of this as we move through this course. So let's take a look at how exactly this will happen from a programmatic standpoint. So again, we have our group of developers, and whoever they might be, ultimately what needs to happen in the background is that the role will give us temporary credentials, and we need a way of getting temporary credentials. And so ultimately, if we were to do all of this manually, we could call the AWS STS assume role command, passing in the ARN of that particular role. That will then make a call to the security token service, which is responsible for returning temporary credentials. And you will see that we also get an access key ID, a secret access key, and in addition, we get a session token and an expiration that represents those temporary credentials. Again, if we're doing this manually or potentially programmatically, we would then take all of these and use them to set environment variables. And by setting them into environment variables, since environment variables take precedence over other locations of credentials, the other calls that we make, we could then use the AWS EC2 service to make the terminate instances command to then terminate an EC2 instance. And of course, these temporary credentials represent the permissions that have been granted in the policy that is applied to the lead developer role. Now, fortunately for us, we don't necessarily have to do all of that on our own. That is just what's necessary behind the scenes. Calling the security token service, getting those temporary credentials, using those temporary credentials for subsequent calls where they're necessary. The CLI tools and the SDKs can do that for us by leveraging other mechanisms that we will talk about throughout this course. So overall, that is how we can use roles for our users to gain elevated privileges, again, either within one account or across numerous accounts, where the group of users can be in one account and the roles can be in another account. In this lab, we're going to enable cross-account admin access. Now, ultimately, we're going to have an admin account and we're going to have a development account, an account that represents our development environments. Again, there is nothing within AWS that says we have to organize our accounts in any particular way. That is totally up to us. We don't necessarily have to do it in this way. This is just one way that you can do it. It's not necessarily the way to do it. So again, we're going to have an admin account, and that admin account will be used to centralize a number of things that are key to compliance, like users. We want to have one place where we can organize all of our users, all of our groups, and organize certain things like publishing Amazon machine images, among a few other things. And so our admin account is where we will create users, and we will create groups of users. In this particular lab, we're going to create the S. Cooper user. We're also going to create an admin group, knowing that Mr. Cooper would settle for nothing less than being an admin user. And of course, within the admin account, all members or all users that are a part of the admin group will have full access to the admin account. They will also have the permission to assume a role in the development account. Now, when I say that they have full access, even though they have the asterisks in place for actions and resources, they have the ability to perform all actions on all resources, that still does not give them access to billing. Billing permissions are yet a separate group of permissions that still have to be explicitly declared. So again, we're going to have an admin account, and we're going to create within that account the S. Cooper user and an admins group. We're also going to have, again, our development account that represents our development resources. And in that account, we're going to create the dev super admin role. That's just what we've named it. Again, there's nothing within Amazon that necessarily inherently creates that. This is just how we've chosen to organize things. We are also going to give that particular role full access to all resources within that account. And with that role, we can read and write to all of these resources. We can create EC2 instances, we can create and manage RDS instances, we can create and manage S3 buckets, and so on. And so for this lab, we're going to create the S. Cooper user, and we're going to create a role, a cross-account role, in the development account by granting the admin account the ability to assume this role. We create what's called a trust relationship. The development account is essentially saying, for the purposes of this role, we are trusting the admin account to then delegate that access to its users. So the development account will trust the admin account, and from the admin account, we can then delegate that permission to members of the admins group. All right, now let's enable cross-account admin access. The first thing that we're going to do is log in to our admin account. So again, we have two accounts. For this particular lab, we're going to log in with our email and password. That means that we are logging in using master credentials. We typically don't do this on a day-to-day basis, but this is one of those few times when we need to, because at this point, if we've created 2 brand new AWS accounts, then the only credentials we have are the master credentials. So the very first thing that we're going to do is give ourselves an admin credential. So the first thing that I'm going to do is log in to the admin account. Now, whatever account that you have set aside as your admin account, this is what we're going to log into with. So I'm here on the Amazon Web Services website, and I'm just going to click here, sign in to the console. I'm here, I've signed into the console, and you can see here, if it's asking for an email or a mobile number, then you know that you are signing in using master credentials. Now, just really quick, I want to show you the difference between these 2 logins. Let me just go here. If you see yourself at a login like this, where it's asking for an account and a username, then you are attempting to log in with an IAM user. For the purposes of this lab, we need to log in with those master credentials with what Amazon calls root account credentials. So if you are on this screen for this lab, we need to go here at this tiny little link down here that says sign in using root account credentials. So again, I'm going to sign in with my admin account. So I'm going to whatever email alias or email group that I have used for creating the admin account. And again, there's nothing in Amazon that calls something an admin account versus a development account. This is how I have chosen to organize things for our purposes here. And you can, of course, organize things how you want. Ultimately, all accounts are functionally identical. It's how we use them that sets them apart. Again, I have logged into my admin account. So the first thing that we're going to do is go to the IAM service. Now, I could find that up here. And of course, you can see that it is in my history because I've been there recently. But if it's not in your history, then we could find it by typing IAM, and there we go. So I'm going to go to the Identity and Access Management within my admin account. First thing that I want to do is to create a group for my admin users. You can see here, this is a fresh account. I don't really have anything in there yet. So I'm going to create a new group. I'm going to call that group admins. I'm going to click next. And I want to, you can see here that if I filter by these policy types, I'm going to choose AWS managed, which still leaves me with essentially that same list. But now I know that I'm looking at sort of stock policies that AWS gives us. So I'm going to attach the administrator access. If we were to look at that policy, it would say that our admins are allowed to perform all actions on all resources. So I'm going to click next, and from there I'm going to create the group. And of course we can click on that and see that if we look at the permissions tab, we can see that we have the administrator access policy enabled. If I show that policy, there we go. You can see that now our administrators are allowed wildcards for actions and resources. So they are essentially unlimited. This still does not allow our admins access to billing information. If we did want to give our admin users access to billing, that would actually be a separate set of permissions. So you can trust that your admins cannot view billing information like credit card numbers. But we could give them read access to view cost reports and whatnot. So we have our group of admins. Now let's go and create a user. I'm going to add a user called S. Cooper. Of course, Mr. Cooper would settle for nothing less than being a super admin. So at this point, I'm just going to leave it at that. Mr. Cooper does not need access to the management console. He will be using the CLI tools. He will need programmatic access, but we're going to come back to that later. For now, we're just going to create the S. Cooper user. I guess it's not going to let me move forward, so I'm just going to go ahead and say programmatic access. Click next. And now we're going to add that user to a group. I'm going to say, yes, let's add Mr. Cooper to the admins group and review. And you can see here that in the review, I've created the user, s.cooper. and I've said that he will have programmatic access with an access key, and he will be a member of the admins group. So once I create this user, now at this point, because we have created an access key, this is the only time that I will be able to download this access key. And so I could show that if I wanted to, or I could download the CSV. So I'm going to download the CSV, which will be the credentials. I'm going to place this in the same folder as the code. Okay, so I'm going to choose the folder where my code is, and I'm just going to choose the root of this, and I'm going to call this credentials-s Cooper, assuming that I am going to be operating as Cooper. All right, so now I've downloaded that. I know that I've downloaded those credentials over a secure connection. And now if I need to give those credentials to another member of my team, I need to be sure to do that in a secure way as well. Okay, so now that we've created our admin group, we've created a user for our admin group, all within our admin account. Our admin account is where all of our users will belong. So we want one place. If we have numerous accounts for development, for test, for UAT, for production, accounts for other business units, then we want one place where we can manage all of our users. I don't really want to have to remember and go to all of these different accounts to find users and groups. By using an admin account in this way, we centralize the management of our users and our groups. And the way that we will gain access into these other accounts is through roles. And we're going to see that as we move forward. So now that I've gotten my scooper user into an admin group in my admin account, I'm going to go ahead and log out of my admin account. You just sign out of that. And now I'm going to log back into the console using the master credentials for my development account. So again, you should have two AWS accounts, one that you've set aside for admin, one that you've set aside for a development environment. And now we're going to log into that development account using the master credentials for that. So again, I'm going to go to sign into the console. You can see here that it's asking for my email, so I know I'm logging in with root credentials. I'm going to use the credentials that I saved and noted for my development account. All right, so now I'm logged in to my development account. I'm going to go back to IAM, and of course, because it's in my history, I can choose it here, or I can type it here. I can also find it up here. So plenty of places where I can find that. So I'm going to click on IAM. In our development account, we will not have users. We will not have groups. We will have roles. All of our users will log in through their credentials in the admin account and then use cross-account roles to gain access into those various resources. So if we have an account for development and an account for production, not every user needs to log into production. Not every user needs to gain access to development either. So we have very fine-grained control over who we allow into what environment. So here I'm going to go to roles. You can see this, again, this is a fresh account. I don't have any roles yet, but I'm going to create one. And here I'm going to create a role for cross-account access. I want to grant the admin account access into my development account. So you can see here we have the choice between access between AWS accounts that we own or access between ours and some third party. So if you are ever in a situation where you want to work with a vendor like a consultant or some other company providing Amazon services and they have their own account, you can use the third party account. But because our admin accounts and development accounts are two accounts that we own, then I'm going to choose this first one here, accounts that we own. I'm going to select that. And here it asks for the account ID. What is the account ID that we're trusting? So here I'm trusting the admin account to gain access into the development account. So what I'm going to do is go back here to my accounts. Where did I save that? I saved the credentials scooper CSV file, and from that I will show you something here. If we open the credentials that we saved for scooper, we actually can see our account number right here. Here is the console. This number here is the account number for our admin account. So I'm going to save that, and I'm going to create another file. I'm going to call this accounts.txt. I'm going to say my admin account has that number, and then while we are we're going to come back and save the development account number as well here in just a moment. But here is our admin account. I'm going to copy that account number. I'm going to go back to my Amazon console where I'm logged into my development account, and I'm going to paste the account ID in there. And I'm also going to check that it requires MFA, multi-factor authentication. I'm going to click Next Step. Again, I'm going to assign to this role the administrator access policy, so that by logging into the admin account, assuming a admin role into the development account, I can now gain access to resources across two accounts. So I'm going to click Next Step. I'm going to call this role name Dev Admin. I'm going to give this a description, administrator role for the development account. I'm going to create that role. And if we take a look at the details of that, you can see in the trust relationship says that our development account trusts our admin account to make that connection using this role. So now what I want to do while I'm on the screen, this is really important. You see up here the role ARN, the Amazon resource name. This uniquely identifies this role out of all accounts across all of Amazon. So I'm going to copy this, which includes the account number for our development account. So I'm going to copy that. I'm going to come back to my text editor, and I'm going to paste that down here. And you'll notice here, again, that this role contains the account number for the development account. So I'm going to copy that and paste that up here. We will be using these account numbers later on. So you will have your account number for the admin account, and you will have your account number for the development account, and I will have mine. So in places where we need to use these, be sure that you reference back to this accounts.txt file so that you can paste those accordingly. By the time you're watching this video, my accounts won't exist anymore. I will have cleaned those up. So if you try using these numbers that you see here in the video, things won't work. All right, so I'm going to save that text file. I'm going to go back to the web console. Now that I've created the role in our development account, there's one more thing we need to do to ensure that our scooper user or our admins group has the permission to leverage that role. Right now, they, as a user, they don't quite have that permission. So we still need to do one more thing here. I'm going to log out of the development account. And now that I've logged out of the development account, we're going to log back in one more time, back into the admin account. So here, I'm going to use my credentials for my admin account. I'm going to go back to the Identity and Access Management Service. I'm going to find this group here, the admins group, and I'm going to create an inline policy that allows that group to assume the role in the development account. I'm going to click here. I'm going to use the policy generator, and I'm going to say, I'm going to choose the AWS Security Token Service. And the only action that I really need is this one here, assume role. And then I'm going to paste the ARN of the development dev admin role. So I'm going to come back to my text editor, and I'm going to copy that role. I'm going to paste that. I'm going to add that as a statement. Click Next Step. And here, very simple policy document. It's allowing the admins group to use the security token service to perform the assume role action on the role that we created in our development account. All right, so now I'm going to apply policy, and you can see here that our admins have administrator access into the admin account. They also have an inline policy that allows them to assume the admin role into the development account. And of course, at this time, now I can log out. Now I have finished enabling cross-account admin access. Now let's take a look at using profiles with the AWS command line interface. If we were to take a look at this hidden AWS folder here, we would see a couple of files. We would see our credentials file. We would also see a file that houses some configuration information as well. You will see that just by configuring the CLI tools for the first time, we end up with a default profile. So if we don't specify a profile, then we have the default profile. Now, aside from the default profile, we can also create custom profiles. You can see here that we still have the default, but we've also created perhaps what we call a personal profile. The only thing that's necessary here, the only thing that's required, is that we specify the word profile so that the CLI tools and the SDKs, because they all use these same files, knows that we have multiple profiles. And here we have a profile for setting our access keys and secret keys. And we also have a profile for our default regions. You can see here the default profile might use US West 2, which is Oregon, and our personal profile might be US East 2, which is Ohio. And so in this example, this might be a use case where the default profile is what we're doing for our employer, and the personal profile is what we're doing for our own personal projects. Now, another thing that we can do with the AWS CLI tools as far as profiles go is, here's an example of creating an admin profile. We're going to see this as we move forward in this course. And you can see here that we have a dev profile that depends on the admin profile. If you notice here, we're saying that the source profile of the dev profile is actually the admin profile. In that regard, you'll also notice that we are also specifying a role. And so here we can use this custom dev profile to tell the CLI tools in the SDKs that ultimately, in order for us to access the dev account, we will do so by assuming a role in the dev account. And you can also see here that we've specified an MFA, the serial number of an MFA device, so that when we do perform that cross-account access, when we use the dev profile, we want to do so ensuring that we have entered an MFA token that adds an extra layer of security. And so we are also going to specify the token. And so that's using profiles with the AWS CLI. It really takes care of a lot of the low-level things like calling the security token service, setting those temporary credentials, and then refreshing them when they expire. And so by using profiles in this way, we can offload that low-level burden of managing temporary credentials to the CLI tools and the SDK. Okay, now let's configure the AWS CLI tools. Here in my text editor, I'm going to open the 2.6 lesson bash commands. You can see here we have a number of things that we can do as far as configuring goes. First of all, you could configure with use the default profile using AWS Configure, which we're not going to do here in this lab. Or we could list out configuration details. So let's just try that. And of course, I'm doing this here on my Mac in ZSH, and wherever you are working, if you're working in Bash or whatever, all of these commands should work after you have installed the necessary tools. So let's say AWS configure list. Now, if you are brand new to this, then you might not see anything there. You can see here it says the profile is not set. That is the default profile, and all of this stuff is my personal information. And so if you have already configured the CLI tools before this particular video series, then you may see something here for work or for your personal. Otherwise, you might not. Let's go ahead and configure a specific profile. Here we're going to configure the admin profile. And whatever default profiles we may or may not have, we're going to leave them as is. For the sake of these labs, we will be leveraging two profiles, one for admin, one for development. And here, for now, let's go ahead and configure the admin profile. And so before we do that, I'm going to go ahead and also open the CSV file for the S. Cooper user so that I can copy and paste some of those credentials from there. Let's go back to the terminal, and I'm going to say AWS ---- profile admin configure. So we're configuring a specific profile. You can see here it says AWS access key ID none because we don't have one set yet. Otherwise, if we had, it would show us some of the last characters. So I am going to go to the credentials file that we saved for our Sheldon Cooper user. And you can see here, it is a CSV file, and the third field is the access key. So after that second comma, I'm going to copy all the way to the next comma. There is our access key. I'm going to copy that, and I'm going to paste it here. Now we need the secret key. I am going to, again, here copy between those commas all of the values for the secret access key. And of course, these will be unique for you. I'm going to copy that, paste that in here. Now, for the purposes of these labs, we will be using the Ohio region, which is US East 2. So for the default region name, I'm going to put in US-East-2. For the default output format, I'm going to leave that as none. For the most part, it will default itself to JSON, but throughout these labs, we will be specifying different types of output. So I'm just going to leave that blank. And now we have configured our admin profile. A couple of more things that we could do just to show you what's possible with these tools. We could, aside from setting all of the properties at once, we could also use the set command to set specific properties. So here, I'm going to, again, use the profile flag for the admin account profile, and I'm going to set the specific region. And so here, if I wanted to change the region, I could set my default region to Oregon if I wanted to. And now if I were to say AWS ---- profile admin configure get region, you can see that I have changed it to US West 2. For the purposes of these labs, that's not what I want. I want to use the US East region. So I'm going to do that again one last time just to make sure that I am indeed using US East-2 region. So I've set that region. Let's get that again. And one last time, let's do profile admin configure list, and you can see we have set our admin profile, we have our access key, our secret key, and we also have set our default region to US East-2, and that is configuring the AWS CLI. In this lab, we're going to create some users, groups, and roles using AWS CloudFormation. Now, we're going to create a couple of users. We're going to create our A. Fowler and L. Hofstadter. We're going to also create a developers group and, of course, add our users to that group. We're also going to create a policy that grants this group of users limited abilities to do certain things. We're going to create a policy that gives them the ability to launch new instances and stop and start existing instances. Keep in mind that with the identity and access management policies, they start with a default deny. And so the only thing that users are allowed to do are those things that they are explicitly granted. And so these being the only two things that they're explicitly granted, this policy would not allow them to terminate instances. Perhaps we save that for lead developers or another, or give them the ability to elevate using a role to gain elevated privileges. But again, for now, we're simply going to create a policy, we're going to create a group for our users, and we're going to create a couple of developer users. All right, so here in my editor, I'm going to open the 2.7 bash commands. You can see here the first command asks us to use the AWS tools, the CloudFormation service, to validate a template. And the template that we're looking at is going to be found here under Source CloudFormation Access Users Developers. So let's go ahead and open that as well and take a look at what's going on in that template. So I'm going to open Source CloudFormation Access Users Developers. Now again, the way that I have organized things makes sense for this particular project. It makes sense for the sake of providing labs and a video that's easy to follow. How you decide to organize it is completely up to you. There's nothing that says you have to do it in any particular way. So find a way of organizing things that make sense for your application and your business. So within this template, you can see we have a YAML template, and the very top level key here in this template is resources. And resources is essentially a map of all of the things that we are creating in this template. The first thing that we're going to create is the developers group. We need a place, a group that we can lump together our users and assign policies to the group. And now part of learning CloudFormation is learning what values are arbitrary and up to us, and what keys and values are expected by the CloudFormation engine. In this case, this will be what we call the logical ID. The name of that key is up to us. There are certain characters that aren't allowed, but ultimately we can call this what we want. Here we're calling it developers group. We also have a type, so we're saying that the type of this resource is an AWS IAM group. Notice the namespacing there. And so it is worth noting that generally for keys and values, we cannot use AWS : in our keys and values because that namespace is reserved by AWS. We also have the properties. Every resource within a template will have its own properties. So here, the group name property says developers. Pretty straightforward. The next thing that we're going to do is create not an inline policy, but a managed policy, a customer managed policy. We want to be able to apply this policy to numerous groups and or users. So we're going to create this as a managed policy. You can see here the type as a managed policy. We're going to call it EC2 limited access so that here the policy document will contain a couple of different statements. The first statement says that whomever this policy is applied to will be allowed to perform the following actions. They can launch EC2 instances, they can start instances, and they can stop instances. Now, because we have not explicitly granted them the ability to terminate instances, they don't get to do that. And so we are only giving them the permissions that they need. We're also saying that they can only do that, they can only launch, start, and stop instances under the condition that the EC2 instance type is one of T2.small or a T2 medium. So if they try to launch a C4 8 extra large, which is a rather expensive machine, they would be denied. They can only launch instances that are small for the purposes of development. We're also going to allow, because we're going to create this in the admin account, we're going to allow these users the ability to list and modify access keys. We're going to allow them to change password. But notice here, notice what we're doing in the resource. This is a really interesting thing that's happening here. There's several things that I want to point out. We're saying that they're only allowed to do so on their own account. So let's start from the back of this. The $AWS username is one of the intrinsic variables of one of the built-in variables of IAM policies. This essentially says that at the time the user goes to do something, it will evaluate this variable to determine their username. So if the A. Fowler user tries to change the password or access key of some other user besides her own, she will be denied. And the same for our other user. So another thing that's happening here is that we are declaring this resource programmatically. We're not just hard coding something. We're using the intrinsic join function to join an array of things with a colon. And part of that array is, one, a hard-coded prefix here, ARN, AWS, IAM. And then here, notice we are also using the reference. This REF is short for reference, and we are referencing here an intrinsic variable, which will pull out our account ID. That way we don't have to hard code our account ID. If we choose to use a template across several different accounts, then by using this variable, we don't have to hard code anything. It will automatically pull the account where this template is being run. Now, when you see, and we'll see this a lot throughout this course, when we see !ref, that is shorthand. Shorthand is only possible in YAML. And YAML is much easier to read and write than JSON. That's why we're using it. And of course, with YAML, we get access to the shorthand versions of the reference and shorthand versions of functions that we will see later on. So again, going back here a little bit, we're creating a managed policy, allowing users to run, start, and stop certain types of instances. We're also going to allow them to manage their own access keys and their own password. And we're applying that managed policy to the developers group. Now we're going to add a couple of users. We have our Amy Fowler user and we have our Leonard Hofstadter users. And of course, you can see here, these are of type AWS IAM user. We're giving them a username. We're also giving them both a password that if you were to read that, it says change me now. And we are saying that they are required to reset their password when they log into the console for the first time. And so each of these users are getting that password required to be changed, and they are also being added to the developers group. So that's what's happening in the template. Now that we understand what's happening in the CloudFormation template, let's go ahead and create those users using the AWS CLI to launch the CloudFormation template. So I'm going to open the 2.7 bash commands, and first thing that we want to do is validate the template. So again, I would encourage you to do whatever you need to do to ensure that you're ingraining this material. Sometimes if you're just copying and pasting, then it might not sink in. So by all means, pause the video and type it out if that would help. So here we're going to again use the AWS CloudFormation. We're running the CloudFormation service, and here is the validate template command. We're also specifying the template body parameter, and anytime we need to reference a file stored locally, we need to use the file : / prefix. And so we are going to point to our users developers YAML template. So I'm going to go ahead and run that. And now you can see that it's giving us back some information. Had there been an error, it would have been pretty clear that there was an error in the template. And so here, we don't have any parameters involved in this template, but we do have, notice here, this is really important. In the case where we are creating IAM resources like users, groups, policies, and roles, anytime we create those kinds of resources, we need to be aware of the capabilities. And so this has to go in on our following commands. We have to be sure that we specify the capabilities that our CloudFormation stack requires. So the next command, let's go back here, is to actually create the stack. You'll notice here, we're going to, because we want our users and groups in our admin account, I'm going to use the admin profile. And I'm going to, again, use the CloudFormation service. With the create stack command, I'm going to use the -- stack name parameter to name that particular stack. And again, I'm going to tell the CLI tools where to find my template. We're also, back here, also going to specify the capabilities that this particular template needs. So I am going to copy that entire line, come back here. The validate command says that we need capability named IAM, and here we're actually giving it one more capability than it really needs, but that's okay. That's not going to break anything. So here you can see that it returns a stack ID, and we're going to, at this point, what we want to do is wait for that stack to finish. And so most commands have what we call waiters, where they will automatically poll every so often, every so many seconds, looking for that stack to reach a create complete status. So here again, we're going to run, I'm going to copy this and wait for that stack to complete. And there we go, it's already complete, just like that. Now, sometimes you will see that the waiters might take a while. So this one was already finished. So now that that's done, let's go ahead and describe the CloudFormation stacks that we have. I want to describe that particular stack. So I'm going to copy this next one here, again, using the admin profile, the CloudFormation service, and we're going to call the describe stacks command. And we're also going to specify the particular stack that we are interested in. In this case, we're interested in reviewing the users group developers that we just created. And now we get back a fair amount of data in JSON, which is our default output format. We can manipulate this data in any way that we want. This next command is going to show us how we can do that. If we wanted to manipulate that, we can use the query parameter to control the output of that. Maybe we aren't really interested in all of that other data. Maybe we're only interested in seeing the stack name and the stack status. So we're using here, we're going to say, give me the stack name and the stack status for every member of the stacks array or the stacks list. And don't show it to me in JSON, show it to me in text output. So I'm going to copy that one. And you can see there, by using the query parameter, we've totally manipulated how that data is being shown. And you can see here that the users group developers shows in a state of create complete. That's a good sign. That's exactly what we want. If there were an error or something else, then we would see something different. Now, of course, if we wanted to see some details about that stack, let's take a look at the resources that the stack created. We've already described the stack itself, but now let's take a look at the resources that it created. In this command, we are going to again use the CloudFormation service, but we're calling the describe stack resources command, again specifying which stack is in question. So here, when we run that command using the admin profile, describe stack resources, let's see what we get back. And you can see here, it's giving us back all of the resources that were specified in that template. And you can see if we notice the logical resource ID, that logical resource ID lines up with the names that we used in our template. You might recognize that. There's our developers group, our EC2 limited access policy, our Amy Fowler user, and our Leonard Hofstadter user. Now that those users are created, we can use the IAM service to list our users. So let's try that. Again, use the admin profile with the IAM service to list our users. And there we go, we get back a list of users. Not only do we see the Amy Fowler and Leonard Hofstadter users, but we also see our own Sheldon Cooper user. We can also list the managed policies that we've created. Now in this case, we want to list the managed policies that we've created, not Amazon policies. So we're going to again use the IAM service to call the list policies command, but we want to limit it to our own customer managed policies. And we can do that by declaring the scope parameter with a value of local. And so if we copy that, if we run that command, let me just clear this one more time. There we go. Now we see a list of the policies, and here is our policy, the EC2 limited access policy that has been applied to our developers group. And then one last thing we're going to do here is that we can see the details of the policy document. I'm going to run this. We're going to need to paste in some of our own stuff here. So here, we need to make a replacement. You'll notice that throughout the labs, when you see these greater than, less than, and something in there, that is a placeholder. That's a variable. That's an opportunity for us to paste in your own unique values there. And so in my case, I need to place the policy ARN here. I'm going to copy this, everything in quotes there. I'm going to copy that, and I want to use that here in place of that placeholder, including the less than, greater than sign. So I'm going to paste that. You will do the same thing. We hit return, and there we go. Now we get back the policy that our CloudFormation template created. And you can see it has all of the actions, all of the conditions, and all of the IAM actions and conditions that we've specified. And that is creating users, groups, and policies with AWS CloudFormation. In order to enforce multi-factor authentication, we need a policy applied to a user, a group, or a role that says MFA is necessary. In this particular case, we have a policy that allows a user or a group of users to assume a particular role. Now again, this could be a role within our account, this could be a role in another account, like the difference between our admin and our development accounts. Here, what we're saying is whatever user or group this is applied to, they are allowed to use the STS assume role action to assume this role, which happens to be in another account, so long as MFA is present. So you can see here the condition is a Boolean, and we're saying we're using the AWS namespace. We're looking for the condition where multi-factor authentication is present. And so what that will do is if anyone tries to make this call, the call to the security token service to assume this role, they will be denied if they are not using multi-factor authentication. So using this kind of a policy with this condition here to enforce MFA is a really great way to enforce an extra layer of security within your account. In this lab, we'll use the AWS CLI tools to enable a multi-factor authentication device. So here in my text editor, I'm going to go to the 2.9 bash commands file. Going to go ahead and hide that sidebar. Now again, because this MFA device is for a user and users exist in our admin account, I'm going to use the admin profile for these commands. The first command, again, we're using the IAM service, and we're calling the create virtual MFA device. Now we're creating a virtual MFA device for use with virtual MFA software for our phones. So what I use is a piece of software called, an app called Authy, A-U-T-H-Y. There's also Google Authenticator and a number of others. I really like Authy. So we're going to create the virtual MFA device. We're also going to specify a name for the device with the virtual MFA device name parameter. Here we're calling it scooper MFA device. What we want back in this case, because it's a virtual device for our phones, and I don't want to have to type out some really long secret text string, I want back a QR code. So I'm flagging the bootstrapping method as QR code PNG, and we're going to specify that the output of that goes to qrcode.png. So let's go ahead and create that. And there we go. Now we get back a serial number for that device. We're going to come back and use that serial number here in just a minute. And so if we list, you can see here that we have our qrcode.png file. And of course, being on a Mac, I can open this from the command line. And whatever system you're on, you may have the ability to do something similar. But let's go ahead and open that. I'm going to say open. And there we go. So now what I'm going to do is use my phone. I'm going to open my Authy app, and I'm going to add another MFA device by scanning that QR code. And so simply by scanning that, now I have that particular MFA device enabled here on my phone. And so I can hit done. And now you can see I'm getting tokens, 6-digit tokens for that particular MFA device. And we're going to come back to that here in just a second. And so now we've created the MFA device. The next thing that we need to do is to enable that device. And in order to enable it, we have to enter 2 consecutive codes. And so here, what we're going to do is use the IAM enable MFA device, again, for that particular user. We're also going to notice here, these are our placeholders that we're going to replace with the ARN that we got back from that previous command. And we also will need to enter 2 consecutive codes. You can see here code 1 and code 2 will need to be entered. So I'm going to go ahead and take that over here to the terminal. So let's paste that. I'm going to come back here to that device ARN, and I want to paste in the serial number that the previous command gave us. So here's the serial number of the device. I'm going to copy that and paste that here for the serial number parameter. Notice that I replaced the placeholder including the less than, greater than signs. Now I'm going to refer to my phone here for the first code. It's just 2 codes in consecutive order. So the first one here I'm going to put in 412549. And of course, you may need to wait a few seconds. The code generally refreshes every 30 seconds. And so I still have a few seconds left for this one. And by doing 2 consecutive codes, that allows AWS to verify that we indeed have the right MFA device enabled. And Amazon is also doing the same mechanism that is used to generate the 6-digit PIN on our phone is also happening on Amazon's side, and that's how they're able to verify that we are indeed using the registered MFA device. And so the authentication code number 2 is 847978. Now, these numbers that I'm putting in are from my phone. You will use codes from your phone. There we go, and now I've entered that. And so if something had gone wrong, it would have immediately given us back an error. And so the fact that we did not get any kind of an error back shows us that that MFA device was added. And so now what we want to do is configure our dev profile. We want to configure a profile so that when our scooper user wants to perform actions within the development account, that he can do so using the dev profile. And so what we're going to do here is we're going to use the configure set command to set the role ARN for the role from the development account. We're going to set the source profile as the admin, and we're going to also set the MFA serial number. So let's go ahead and first set the role ARN, and here I'm just going to copy up to this point, and I also want to open, let's go back here and open the accounts, and we're going to need this role that we created in the development account. So I'm going to come back here, let's go ahead and clear that. Configure set role ARN, let's copy that. This is what we pasted when we created the role, that cross-account role in the development account. And so what we're doing right now is enabling the S-Cooper user. We're giving him a way to assume this role in the development account. Right? So I'm going to paste that in there. The next thing that we want to do, let's go back to our bash commands. We're going to set the source profile as admin so that the system behind the scenes knows that we are performing these role assumptions from the S-Cooper user, which is defined in the admin profile, or at least the key and secret key that represents the S-Cooper user are represented in the admin profile. Right? So let's go ahead and do that. We're setting that source profile to admin. We are going to then configure and set the MFA serial. So I'm going to copy that. And then, of course, that serial was back here a little ways. Here it is. I need that one more time. And then one last thing that we're going to do is also set the region. So again, AWS minus profile dev configure set region Ohio, which is US East 2. And now if we do AWS minus profile dev configure list, you will see here that in order for us to even see that, we need to enter the MFA code. So I'm going to pull up my phone and enter the MFA code. Now, even though I've entered it, it doesn't show that I'm doing anything. So there we go. You can see that we have, for the dev profile, we have access keys, secret keys, and regions. These access keys and secret keys, you can see here, were done by assuming a role. These access keys and secret key are temporary. They were granted by the security token service based on the role that we provided, and they will expire at some point. When they expire, we will be asked for our MFA PIN one more time. And so you can see that at this point I could do that again. I could do that configure list again, and it didn't ask me for my MFA PIN number because the access key and secret key, those temporary credentials, have been cached. And again, once they expire, I will have to re-enter the MFA device PIN. That is how we enable an MFA device. Now let's use the AWS CLI tools to reset our password. If you recall, when we enabled cross-account admin access and we created that S-Cooper user, at that time, we gave Mr. Cooper the ability to interact with AWS using access keys and secret keys that we then configured into the CLI tools. We did not give Mr. Cooper the ability to log in to the management console. So that means that that user does not have a login profile. So let's not confuse profiles in the CLI tools with login profiles. They use the same word, but they're actually two different things. And so before we can really change a password, we have to have one to change, and Mr. Cooper doesn't have one. So for users that don't yet have a login profile, we can create one with this command. Again, using our admin profile, the IAM service, we're going to create a login profile for Mr. Cooper, and we're going to set an initial password of change me now, and when he goes to log in to the management console, he will be prompted immediately to change that password. Okay, so let's go ahead and do that. We will create a login profile for him. And there we go. Now you can see that the S-Cooper user has a login profile. Here, if we wanted to change our own password, in this case, we are acting as the S-Cooper user. Our command line tools with the admin profile have been configured to use the access keys for that user, and so we are essentially acting as Cooper in this case. So here, we're going to change our own password. We're going to use the im change password command. The old password needs to be specified plus a new password. In this case, we're going to set the new password as I love physics. And we're going to go ahead and paste that change password. And there we go. The fact that it did not report an error told us that the password was changed. So now if Mr. Cooper logs into the management console, then he will use that new password. If we wanted to change the password for someone else, then we could do this. We could say update login profile specifying the user that we are helping. So it could be that Amy had her password set to something really secure, but she either forgot it or lost access to her encrypted password directory and needs her password reset for her. And so here we're going to set her password to change me now, ! And we're also going to specify that at the time she logs into the console, her password will need to be reset immediately. So here we're going to change the password for another user. And there we go. We've changed the password for Amy. All right, so that's how we change passwords using the AWS CLI. Here, we'll use the AWS command line interface to rotate our credentials. Now, the access keys and the secret keys that we use, in this case, we've granted the Cooper user some credentials, access keys and secret keys. Those are what we call long-lived credentials. They need to be rotated. Outside of roles, Amazon does not offer an automated way of rotating credentials for users like we have here for the Cooper user. We have to do that, and it's up to us to specify some type of business policy around credential rotation, whether you rotate them every 30 days, 60 days, or whatever. Whatever that time period is for you, then this is how we can do it. So here, I've got my bash commands open for 2.11, and the first thing that we want to do is to get the current access key ID because we want to delete that later. If we delete it first, things will get a little weird. So let's go ahead and capture the old key so that we can delete it later because we're going to need this old key to create the new one. So let's go ahead and get that. If we get the access key, so there we go. Now you'll notice that it showed us the access key. It will not show us the full secret key. It will always keep that hidden if we do the same type of command for the secret key. So now what we want to do is create an access key for the Cooper user. So here I'm going to specify s.cooper. I'm going to copy that. And here, there we go. Now we've been given back an access key and a secret access key for that user. So now we want to use those to configure the CLI tools, right? So we're going to use the configure set commands to set the access key ID and the secret access key. All right, so let's go ahead and do that. Configure, we're going to set the AWS access key ID, and I'm going to copy and paste that there. And we're also going to set AWS secret access key. And I'm going to copy this one here. And there we go. Now we've generated a new set of credentials. We've used the configure command to set those new credentials. And now we can delete the old one. Here we're going to use the delete access key command, and we're going to specify the Cooper user, and we're also going to paste in the old key because the old key is the one that we want to delete. Now, you'll notice here I have left a note here in the code that says beware eventual consistency. That is because when we make these kinds of calls, when we create access keys within AWS, that ultimately needs to be replicated to numerous regions around the globe because changes that we make to IAM are global. So if we were to script all of this out into one automated script, bash script, then without giving us time here, if we don't do like a sleep command here, if we don't give it a few seconds, then this last command may actually fail, and then we would be confused. Why is it failing? And that's simply because potentially it could be because of eventual consistency. And so in the time that I've been talking, that is no longer a problem. So now that we can go ahead and delete that key. So here we're going to delete, let's go ahead and copy this. And again, I'm going to delete a key for the S Cooper user. The access key ID is the old one that we grabbed earlier. I'm going to copy and paste that one. And there we go. I've deleted the old key. So now I've used the AWS CLI tools to rotate my credentials. For applications running on Amazon EC2, the infrastructure begins with the network. A network that provides both public and protected private access has a lot of moving parts, and automation is the most effective way to manage that. While AWS gives us all the tools to create secured networks, it is our responsibility to use those tools properly. In this lesson, we review Amazon Virtual Private Cloud and use AWS CloudFormation and the Python SDK to create and manage a number of networking resources. With Amazon VPC, we have the ability to create networks, logically isolated networks that are inherently private from one another until explicitly connected. So we might have a VPC, and a part of that VPC will be to specify the IP range. We do that using CIDR notation. In this example, we have one with a /16, which will give us somewhere around 65,000 IP addresses and some change. We've also created, you can see here, 3 different subnets. We have a subnet 10.2/24, 10.2.1/24, and we also have another one over here, 10.2.2/28. So it's worth noting that subnets are specific to an availability zone. The VPC itself will span the entire region. Subnets are one-to-one with availability zones. So the general architectural practice is that we create a subnet per tier, per functional purpose, per availability zone, and by leveraging multiple availability zones, we gain high availability and fault tolerance. It's also worth noting that a /16 is the largest range that we can produce, giving us, again, somewhere around 65,000 IP addresses, and a /28 is the smallest range that we can create, giving us, mathematically speaking, that would give us 16 usable IP addresses. It's also worth noting that every time we create a subnet, AWS will reserve the first 4 and the last 1 IP address from that range. So a /28 mathematically would give us 16 addresses, but as far as Amazon is concerned, we're going to have 11 usable IP addresses in that range. Now, a common question would be, why would you create such a small range? Well, and here we're going to have a /24 mathematically would give us somewhere around 256 IP addresses, minus the 5 would give us 251. So in that regard, we have plenty of room to scale for, say, a web fleet or an API fleet. Over here, /28s are great for relational databases. Relational databases don't scale horizontally very well, so we're typically going to have relatively few instances set aside for relational databases. And so that's typically, when you see a /28, it's the typical use case for that is doing something with relational databases. That's my particular pattern. So again, we have our VPC that spans the region. We have subnets per availability zone. So another aspect to Amazon Virtual Private Cloud is routing. Routing I consider to be our first line of defense, because routing is essentially a way of saying that traffic is allowed to flow from one network to another network, either from our VPC to the internet or our VPC to a VPN connection back on premises. Now, the default route is local. Every route table that we create will always contain that default route that says traffic within this range will always stay local to that VPC. And so routing is not really concerned with ports and the type of traffic, UDP versus TCP versus ICMP. Routing is about all traffic, and it is concerned with IP ranges, but not ports. And so it's a very coarse-grained way of saying traffic is allowed to flow or not allowed to flow. And it's that first line of defense. So packets that aren't routed aren't dangerous. So here, if we want traffic to route between our VPC and the internet, then we're going to need to create, first of all, we need a route table associated with that subnet. And you'll see here in this route table, we have essentially all other IPs. It's wide open. 40/0 means it's wide open. All ranges route to an internet gateway. A gateway is a device that bridges two networks. Over here, we have, in this example, this is our corporate network range, 192.168, and we're saying that all IPs or all traffic destined to that IP range will get routed through the virtual gateway. And this is how we can route traffic between our on-premises network and our VPC. And of course, we could route the entire VPC. We could route specific subnets as well. And then of course, here in the middle, this particular subnet has its own route table that remains local. This particular subnet directly is not allowed to reach the internet, not allowed to reach a VPN connection, and of course it remains privately protected. It is not reachable directly from the internet. After routing, the next layer of defense are network access control lists. Network access control lists you could think of as a firewall that is applied to the subnet as a whole, no matter how many machines are in that subnet, no matter what security groups they happen to be using, the network access control list applies to the entire subnet. It's also worth noting that network access control lists are stateless. They don't remember TCP sessions. And so because they're stateless, they don't recognize response traffic as response traffic, whether it's inbound or outbound. They don't recognize responses. And so because of that, we have to specify both ingress and egress traffic rules. And of course, we can allow or deny traffic. We specify the protocols, source IP range, destination port ranges as well. In this example, what we're saying is that we want to allow port 80 from anywhere, from perhaps the internet, port 443 from anywhere. We're going to allow port 22, but only if it originates from 192.168/16, which is our corporate range for our VPN. And then, of course, the next rule says that everything else will be denied. And so that's going to be our default fallback, so that if it was not explicitly allowed or denied up here, then we're just going to fall back to a default deny. Now, you can see here that we've specified port 80 and 443 as being allowed to come in as ingress rules from anywhere. Because network access control lists are stateless, we also have to specify explicitly the egress rules. And so, technically speaking, response traffic to HTTP requests would go out on what we call an ephemeral port. That ephemeral port is, even though there is a standard, somewhere around 32,768, if I'm not mistaken, is a standardized range of ephemeral ports. But in my experience, I have seen response traffic come through on a number of ports well outside the official standardized range. And so I typically don't like to count on receiving or sending on any particular small range like that. I generally like to make sure that I am indeed going to get my responses. And so here in this case, I'm saying that we're going to allow TCP traffic to go out, egress, over any port between 1024 and 65535. That right there excludes privileged ports such as port 22 and SMTP and a few others, FTP and so on. And we're allowing that to go out to anywhere on the internet. So those are network access control lists. Where network access control lists applied to the subnet as a whole, security groups apply to the individual instances. So again, security groups apply to instances, and unlike NACLs, they are stateful. They do remember, they do understand that response traffic is in response to something that went out. And so that means that we can specify ingress or egress. We have a bit more control in that regard. Again, very much like NACLs, they are denied by default. We have to explicitly allow certain traffic to come in as far as initiating connections goes. And again, we're going to specify protocols, IP ranges, and destination port ranges as well. In this example, again, the network access control list is concerned with the subnet. The security group is concerned with the EC2 instance. So just because our subnet allows port 80 in, we still need a mechanism to allow it to get into the EC2 instance, and that's what security groups are for. And so we're going to apply, again, allow TCP traffic on port 80, on port 443 from anywhere. We might have some other application that internally communicates on port 9999. So we're doing a custom port here, and we're saying instead of marking an IP range, we're going to reference another security group. So what we're saying here is that this, whatever instance or instances has this security group applied, is allowed to receive traffic or allowed to receive initiating connections on port 9999 as long as it came from a EC2 instance that had this particular security group applied to it. We're also, again, going to allow port 22 so long as it came from our corporate IP range. Now, egress rules are a bit different than how they work with network access control lists. Egress rules are really there to control initiating connections. Again, because security groups are stateful, we don't necessarily need a security group rule here in egress to allow responses to go out. Here, we're saying that this machine, whatever machine this is applied to, is allowed to initiate connections on port 3306 so long as the destination has this particular security group applied. So that's VPC, creating logically isolated networks, dividing it into subnets, controlling the flow of traffic by way of routing, and also protecting our subnets and our instances by using network access control lists and security groups. In this lab, we're going to use AWS CloudFormation to create a virtual private cloud. Now, in this lab, we're going to be creating a VPC, again, that spans the entire region, and we're going to choose the US East 2 region, which is the Ohio region. And for the purpose of our end result, in order to create and manage our microservices, containerized microservices cluster, we need a network. And we need that network to also have access, protected access to and from the internet. And so we're going to create a VPC with this range here, 10.0.0/21, that will give us in total 2,048 IP addresses, which is plenty of room to scale, but not so much room that we end up using large ranges in case we want to subdivide later, right? Now, we're going to create a subnet per functional tier per AZ. In the Ohio region, we have 3 availability zones, US East 2A, 2B, and 2C. In each availability zone, we're going to create the same functional tier. We're going to have 3 subnets that are that we're calling public. These are essentially our DMZs. These public subnets will communicate to the internet. We'll also have subnets specifically designed to hold nodes of our cluster, and we will have subnets specifically designed to hold RDS instances. And so in this lab, we're going to create the VPC, and we're going to create these 9 subnets. Okay, so I have here in my text editor, I've got my bash commands for 3.2 open. I'm also going to, before we get into actually creating the CloudFormation stack, I want to take a look at the YAML template. So let's go to Source, CloudFormation, Network, and take a look at the Microservices Network YAML. So one more thing that I do want to point out here is that we are splitting our resource creation into numerous networks. Like we've talked about, we're using cross-stack references so that we don't have to put everything in regards to our network in one long script. If we put our network, our subnets, our load balancers, our security groups, and so on, if we try to put all of those things in one script, then we end up with a really long, hard to maintain, potentially hard to read and edit script. And so we're going to split things out into their own templates so that we have an easy ability to manage and maintain this moving forward. So all we're creating right here is the VPC and the subnets themselves. So with this particular stack, all we're creating is the VPC and subnets for our microservices. The first thing that I want to point out here is that this particular stack will take some parameters. This stack allows us to specify a CIDR prefix. Now, CIDR notation will have 4 numbers separated by periods, all followed by a slash. And so here we're specifying the first 2. And then later, we're going to use that parameter, the VPC CIDR prefix, we're going to use that and combine it with other prefixes for the VPC and for the subnets, right? So we are accepting a parameter. We are also specifying what we called an allowed pattern. We're using regular expressions. We're saying that if you're going to supply a value here, you have to supply that value following this pattern, 1 to 3 digits, followed by a period, followed by, again, 1 to 3 digits. Now, of course, we're going to create our VPC, and then the CIDR block for that, which has to be, this is a required property. The CIDR block, we're going to, again, use the intrinsic join function. This is the shorthand form of that, with, note, the exclamation point. We're using the shorthand of the join function to create a string by essentially combining the CIDR prefix parameter with a hard-coded range for our VPC. So our VPC itself will be a /21. And then, of course, we're going to name our VPC. And notice here what we're doing. Here's another intrinsic variable called AWS stack name. And the stack name, at the time we launch this template, we will name the stack. And whatever we pass in as the name of the stack will come out through this intrinsic variable. And then, of course, we're going to create our public subnets. I'm calling them DMZ-A through DMZ-C. And these public subnets, you can see here, we're going to map a public IP on launch. Again, we're doing the same type of join for our CIDR blocks. Another thing that we're doing here is using the select function. For the availability zone, I don't necessarily want to have to hard code this for region by region. I want to be able to deploy this particular template in any region without having it be hard coded to one specific region. I might want to deploy microservices in not only US East to Ohio, but also US West to Oregon, or in Europe or Asia. And so instead of hard coding availability zones, what we're going to do is use a couple of different functions. First of all, we're going to use the getAZs function, which will return a list of the availability zones within the region where we are executing this CloudFormation stack. We are then going to use the select function to pull the first one. Starting at index 0, we're pulling the first availability zone out of that list that was returned by getAZs. Now, getAZs, you'll notice here, is followed by empty parentheses. That essentially says, get the availability zones of the current region. So we're doing that same thing for all of our subnets. And we're going to add some tags to it. In this case, again, tags are arbitrary. They're just key value pairs. It's up to us to use them and be consistent with our tagging. So here I'm going to say that the scope of these are public versus private. They're public because they will eventually have access to and from the internet, right? So I'm creating my 3 public subnets that I'm calling DMZs. I'm also going to create some private subnets. Here I'm calling these nodes A, B, and C. This is where we will actually create an autoscaling group and our EC2 instances for our microservices container cluster. Again, using the select function to pull out the first availability zone, the second availability zone, and then down here for node C, I'm pulling out the third availability zone. And with each one, you'll notice here, the IP range goes 3024, 4024, and 5024. And all of these are scoped to be private. I've also added a key here called purpose. This is a tag called purpose, and I'm saying that the purpose of these subnets is for our nodes. We can use that key later when we go to find subnets that we're looking for. And then, of course, at the bottom, we're going to create our final 3 subnets. We're going to create these as /28s for the purpose of holding RDS instances. Again, pulling out the availability zones programmatically. Here, we're also using join, but notice we're doing a different IP range. Here is 6028, and because that would give us 0 through 15, we're going to start the next one at 16. And on down here, we're doing the same thing here for subnet DBC. We're doing .6.32. And of course, again, the scope of those are private. They will not have access directly from the internet, and their purpose is for databases. You'll notice here that the VPC ID for all of them is also set to a reference. We are referencing the logical ID of the resource that we created earlier called VPC. Now, the final thing that I want to point out in this script, and we will see a lot of this as we move forward, is the output section. There's a number of things we can do here. In this example, we are going to be exporting several values that we can then import into other templates. So here, the value of the VPC ID will be pulled programmatically from the VPC resource once it's created, and we are going to export that. Notice here, this is an intrinsic function we haven't seen yet, where we are exporting that as a particular name. We have to name our exports. And so here, we're going to use the substitute intrinsic function to take the AWS stack name, This will go in at runtime, and whatever it is that we name this stack will come out here, and we will essentially combine that with dash VPC ID. We're going to do that same thing for our VPC CIDR block. We're going to do that for all of our DMZ IDs, for our node subnets IDs, and for our DB subnet IDs. We're exporting those IDs and values so that we can use those in later templates with cross-stack references. Okay, so that's what's happening in the YAML template file. So let's go ahead and run that. We're going to, first of all, let's validate that template with this first command, and you'll notice that this first command does not have a profile because we're not executing anything. We don't need a profile here just to validate a template, all right? So I'm gonna go ahead and run that, and you will see that because it is returning a list of parameters, in this case I only have one, the VPC CIDR prefix, then that means that the template validated okay. Otherwise, if there were an error, it would be pretty clear. Okay, so now we need to create the stack. And so here we're going to, again, use the dev profile because we want to create these resources in the dev account. All of our users and groups of users are in our admin account, but the network here for our development environments will be in the development account. And so I'm going to use the dev profile. And we're going to create that stack. I'm going to call it here. I'm going to give that stack a name called Microservices Network. And again, that name will come out through those variables that we talked about. I'm going to point to the same template. And here, notice here, this is how we specify parameters for CloudFormation templates. Each parameter needs a key and a value. And so this is the pattern. We specify the parameter key is VPC CIDR prefix, and the parameter value in this case is going to be 10.0. Of course, we could do whatever we wanted to here. We could do 192.168 if we wanted to. We could do 10.111. That's up to us, according to whatever range makes the most sense for us. I would just encourage you to be aware of any potential VPN tunnels you might create in the future so that you don't prevent yourself from creating a VPN by having overlaps in your ranges. Okay, so here we're going to go ahead and create this. Now, because we're using the dev profile, it is asking for our MFA pin. So I'm going to refer back to my phone. There we go. Once we put that in, now it'll cache those temporary credentials for some period of time. You can see that the stack is being created. While it's being created, let's do this. Let's use those waiters we saw earlier to wait for the stack to be complete. So I'm going to go ahead and run that command. Let's wait for that stack. And now this command will periodically poll the CloudFormation stack and ask for a particular status. When it sees the status is in the create complete, that's when we know everything is finished. And so this might take some time. And there we go. Our stack is now complete. Had there been an error during the stack creation, the waiter command would have made that very clear. All right. So now that we know that the stack has been created, we can do a few more things. Let's do this command here called list exports. If we list our exports, we can see here that all of those exports that we specified in our YAML template are now here coming out through the CLI tools. So if we go back to our tools, we might want to clean that up. We might want to get a better display of that. And so we can do a better display by using the query parameter. And also we can make it more human readable by doing output table. And so I'm going to say, again, the dev profile, list exports. So let's go ahead and run that one. And there we go. You can see that we have our VPC ID, we have our VPC CIDR, and then we have our 9 subnets that belong to that VPC. Now we can do something very similar with the JQ command. Instead of using query, we can take the raw JSON output and we can pipe it to the JQ executable, and we can give JQ its own sort of query language and ask it to do the formatting. So let's see what we can do with JQ. There are plenty of times when JQ is more useful than query. There we go. So we get, it's not quite a table view, but it just shows how we're not limited to using the query parameter. We can also use JQ. And there we have created our VPC using AWS CloudFormation and the command line tools. Now let's take a look at getting resource details with the AWS CLI. In my text editor, I'm at 3.3. I've got my bash commands open. I'm going to go ahead and minimize that. The first thing that we want to do is take a look at the VPCs that we have. So we're going to use the EC2 service, and we're going to call the describe VPCs command. Now I do want to point out here that so far we've seen a number of different commands, and we will continue to see even more with a lot of commands and a lot of different parameters that need to be specified. All I can say in that regard is that the documentation will be your best friend. So throughout the code, you will see links to the documentation, and I would say just get familiar with it and make the documentation your best friend. I've been doing this for going on 10 years, and what I find is that the only thing that I can remember is where to find it in the documentation. So definitely rely on that. So let's go ahead and take a look at the VPCs we have using the dev profile, because again, we've created our VPC in the development account. So we're going to again use the EC2 service to describe our VPCs. And there we go. You can see we get back a whole lot of JSON, and we get some useful stuff in here. Programmatically, JSON is really great. And so if we wanted to write scripts that leverage this information in some other way, then JSON is wonderful. But for human readability, it's not the best. Right? So let's take a look at some other things that we can do. Now, as we've talked about, the filters parameter limits what comes back from the API. The query parameter controls how that data actually looks on our screen. So we're going to limit that by in this case, we're going to create one filter here, and we're going to say that we are looking for the name of the filter is a tag with a key of name. That might seem a little confusing there, but it'll become more clear as we go along. We're looking for a tag whose key is name with a capital N, and the values of that tag are microservices network. All of that went in at the time we created the VPC with CloudFormation. All right, so let's try that one. And you can see we get back a little bit less information. If we were to scroll back here, the reason that we got so much information the first time is you'll notice here that we're actually seeing two VPCs. The first one here is our microservices network that we created. You can see here's the 10.0.0/21, and you can see a second one here with a CIDR block of 172.31/16. You'll also notice a difference in is default equals false versus is default equals true. And so the second VPC that we're seeing here is the default VPC that comes with every account in every region. So we might make use of that later, but for our purposes moving forward, at least in the dev account, we're not really going to do a whole lot with it. So by using the filters parameter, we've limited what came back from the API to only the one VPC that we really care about in this example, which is our microservices network. All right, so now programmatically, what we might want to do is grab the VPC ID. So let's go ahead and do that. You can see here that I'm going to set a bash variable called VPC ID, and it's going to equal the output of this command, as denoted here by the parentheses. Again, I'm using the dev profile. I'm going to describe VPCs with that same filter, but here I don't want all of that JSON. All I want is the VPC ID from the one and only VPC in that list that we know we can find at index 0. And then in order to get that in the right output, I want to output it as text. Okay, so by outputting it as text, I can capture that VPC ID in a variable. So let's go ahead and do that. And then we can verify that we have that by echoing that. So there we go. You can see here that we've echoed that variable out. We get that, and we can come up here and verify that by looking up here. That's the same value that we got just a second ago with the earlier command, but we've now captured it in a variable. And now we can use that variable in subsequent commands. We could describe subnets, and in order to describe subnets, I'm not interested in the subnets that are a part of other networks. For this particular example, I only want to see subnets that are a part of my microservices network, and here I can find those based on a filter. In this case, I can filter by VPC ID. So I'm naming the filter VPC ID, and I'm going to pass in that bash variable here as the value, right? So now let's find our subnets using that VPC ID. And of course, that comes back pretty fast. You can see if we scroll back here, we get a lot of subnets. We get 9 of them, right? So that's a lot of information to scroll through. Great for programmatic things, great for scripting, not the best for reading it with human eyes. Let's use the query parameter to clean up the output a little bit. We're going to do the same thing, but here, let's only take a look at the subnet ID and its correlated CIDR block. Again, we're going to output that as text. So let's try that one. There we go. That's a much cleaner, much more human-friendly output for taking note of all of the subnets and all of the CIDR ranges that we have. You can already pick out the 3 that are used for our databases because those are the ones that are /28s. In this regard, even though we can pick out the ones that are for databases because they are /28s, we still can't determine from this particular list. We have no way of knowing which ones are public and which ones are private. So let's do that. Here, we're going to build on that query parameter. And what we want is we want to grab the value of one of those tags. Ultimately, tags is a list, but we're not interested in every tag. We're interested in the tag whose key is scope. So remember, tags are key value pairs. So the name of the key is scope, and the value will be either public or private. Here, what we're doing, essentially what we're saying is find the tag whose key equals scope, and then give me the value of that tag. So let's try that one. There we go. So now you can see we have this subnet is private. Here's one that's public, so on and so forth. That kind of works, but they're on different lines. I want them to all be on the same line. Okay, now we can do that by flattening that a little bit. This is how we might do it. Notice the subtle difference between the query in this line versus the query in the following line. Instead of just taking the value off of that, which here, this value is not necessarily a straight value. It's an array, and we don't want the array. That's why it came out on multiple lines. So we want to flatten it out of an array. And so using the pipe here, we can say, essentially, take the resulting array, which will only contain one element, but it's still an array. We're going to take that. Using this pipe parameter, we can now say, you know what, let's grab the value of the first element. By doing that, it will flatten things out. There we go. And now we've pulled out that one value and made it all on one line. That's much more easy to read. Now we can identify which subnets are private and which subnets are public. So the last thing that we'll do here in terms of getting resource details is to not only pull out the value of the scope, but we also want to see how many IP addresses do we have available? And what availability zone is that particular subnet a part of? And instead of outputting it as text, let's output it as a table, which makes it much more easy to read. Okay, so let's try that one. There we go. Now we have a really easy to read table showing all of our subnets in that microservices VPC. And we can see the name of that subnet that we gave it. We can see our subnet IDs, the IP range, whether it's private or public, and we can also see how many usable IP addresses we have left. So keep in mind that a /24 mathematically would give us 256 IP addresses, but because this is a subnet, Amazon is reserving 5 of those. The first 4 and the last one for every subnet gets reserved. That's why we only have 251 usable IP addresses. And then here for the /28s, normally mathematically would be 16, but Amazon is reserving 5, so that leaves us with 11. And so that's how we can get resource details with the AWS CLI. And again, we will continue to see more of this as the course progresses. In this lab, we're going to use AWS CloudFormation to create gateways and routes for our VPC. Here we have 3 public subnets that need access to the internet, and we have 3 private subnets that need access to the internet, but we still want them to be private and inaccessible from the internet directly. And so for our public subnets, first of all, we're going to create an internet gateway. We're going to create a route table that allows it to communicate with the internet. We're going to associate that with our public subnets, and that will give our public subnets bidirectional access to and from the internet. For our private subnets, for EC2 instances in the private subnets to reach out to the internet, to receive network time, to receive, to make logging calls, or to reach some other system that's out there, we need their traffic to go through network address translation. So we're going to create a NAT device, a network address translation device as well. Aside from the internet gateway, we're also going to create a couple of route tables. We're going to create routes for public traffic. We're not only going to create a route table for that, we're going to create a route that says all other traffic besides local traffic, all other traffic is to be routed through the internet gateway. And of course, that route table will be associated with the public subnets. We will also create for the private subnets, we'll create a route table specifically for protected private traffic so that EC2 instances in those private subnets can reach out to the internet. We're going to create a route again. All other traffic is routed through the NAT gateway. All right, so here in our code base, we're going to open the 3.4 bash commands. Before we run these CloudFormation commands, let's take a look at the template. So here we're going to look at the CloudFormation Network Microservices Internet template. So down here, we're going to open that Microservices Internet template and take a look at what we're creating in here. Now, in this one, the only parameter that we're asking for is the network stack parameter. Whatever the stack name that we used to create our VPC, we will use that here. And of course, for that one, we called it Microservices Network. So that is what we will end up putting in for the network stack parameter. Now here we're going to create an internet gateway. We don't really need many properties other than a tag. We're going to give it a name tag, and the value of that is going to reference the current stack name, which is different than the network stack that we put in up here. So this one we're going to name Microservices Internet, and that stack name value will come out as the value of the name tag for our internet gateway. Now, it's not enough just to create the internet gateway. We also have to attach the internet gateway to a VPC. And in this case, we want this internet gateway to be attached to the VPC that we created earlier. Again, if you recall that we exported some values from that VPC that we created, and in this case, we are going to import those values. So here for the VPC ID, we're going to use the import value function to import a value, and here we're going to derive the name of that export from the network stack parameter. Once the internet gateway is attached to the VPC, we will also need a way of routing traffic. And so in order to do that, we will create a route table. You can see here, type EC2 route table. The VPC ID is again going to belong to the VPC ID that was exported by the previous template. And again, using a combination of the import value and substitute intrinsic functions. Now you'll notice here that I'm using the long form in one line and the shorthand in another line. I generally prefer to use the shorthand, but in some cases like this, CloudFormation won't let you use the shorthand for both. So in this case, because of the combination of import value and substitute, one of them has to be the long form. So I choose here to make the import value the long form and use the shorthand for substitute. And so here we're also giving it some tags. We're calling this our DMZ routes, and the scope of it is going to be public. A route table is one thing, but a route is another. So not only do we need a route table attached as a part of a particular VPC, we also need a route. And here you can see we're creating a route. We're going to say that essentially all other traffic, aside from local VPC traffic, will get routed through the internet gateway that we've created within this template. And we're going to use the reference command to do that. So again, for the gateway ID, we're referencing the internet gateway that we're creating. For the route table ID, we are referencing the route table that we're creating. Now, it's not enough just to have an internet gateway and an internet gateway attached. We also had to create a route table and a route, but now we have to attach or associate the route table with our subnets. And so here we want to create 3 different route table associations, one for each public subnet. For the route table ID, we're going to reference the route table that we just created, and we're going to essentially do this, create these associations for all 3 of our public DMZ subnets. And here again, for the subnet ID, we are using that import value intrinsic function and deriving the name of that export from the network stack parameter. Now, our public subnets will gain access to the internet directly through the internet gateway. That means that not only can they reach out to the internet, but they can also be reachable from the internet. And that's great for a load balancer. Not so great for a database or an application server. We might want our application servers to reach out to the internet, but we surely don't want anyone on the internet getting in. And so we can make that one-way traffic by using a NAT gateway. And so here we're going to create a NAT gateway, and this is an interesting parameter that we haven't seen before. We're using the depends on parameter. We're telling CloudFormation, before you create the NAT gateway, first make sure that the internet gateway attachment has finished. That way, when the NAT gateway comes up, we know that by the time the NAT gateway has been created, that the internet channel in the public subnets is already there. And so we're creating a NAT gateway. We also need, here we're going to use the get attribute intrinsic function to get the allocation ID of an elastic IP resource that we're creating here. So notice that we're using this value here matches the logical ID that we're using here to create an elastic IP. Now, our private subnets will need their own route table, and we want to ensure that our private subnets that traffic not destined for anything local will go not directly to the internet, but through the NAT gateway. So you can see here we're going to create, again, another route table. This time we're going to call it a private, and we're going to change the scope of that to private. And here we're saying all other traffic, aside from local traffic, will be routed through the NAT gateway. And of course here, we need to associate that route table to our subnets. We're going to associate that with all three of our nodes subnets. We don't really need our databases to access the internet. So down here, I have commented those out and shown an example of how we could give our databases outgoing access to the internet, but because they're running on RDS, they don't need to reach out to the internet. That's all fully managed and taken care of for us, right? So we're only going to enable our subnet nodes, the nodes that will make up our container cluster. We're going to allow them to gain outgoing access to the internet. So now that we've reviewed our CloudFormation template, let's go ahead and run those commands. First of all, let's make sure that our template validates, that we don't have any errors in there. I'm going to validate that template, and you can see that because it's returning a list of parameters, that means that the template has validated, and we only have one parameter key called the network stack. And so now let's go ahead and create that. Again, we're going to use the same thing that we saw earlier, create stack, and we're going to name this one Microservices Internet. We're going to refer to that template, and here for the parameters, we're going to put in, notice here, that for the network stack parameter, the value that we pass to that is microservices network. That's the same exact value that we used in an earlier lab to create the VPC. Okay, so let's go ahead and run that one to create the stack. There we go, we get back an ARN that represents that particular CloudFormation stack. And now all we need to do is, just like before, we're going to wait for that to finish creating. So let's go ahead and run the waiter. And of course, it's asking for our MFA code because those temporary credentials expired. This may or may not happen to you depending on how fast you move through this. But anytime you see that enter MFA code, just go ahead and refer to your phone and enter the code that it gives you for that MFA device. And so there we go. We're waiting for that stack to create. We could sit here and wait for this to complete. And of course, just watching a flashing cursor doesn't really do us a whole lot of good. We know that something's happening, but we don't know what, and we don't know how much longer it's going to be. So, in a programmatic situation, we just let it run. But if we are, waiting to perform something else, then we might want to see some action. And so we could, instead of waiting, we could describe the stack events. So we could use describe stack events, giving the stack name. And with this particular query that I've built here, we could build out, you'll notice here what we're doing is we're taking essentially for every event in that stack events array that comes back, we are building out our own object. We're renaming these keys. And so we're saying resource, status, and reason, and we're going to output that as a table. So let's try that. Even though it's already finished, we can still get the stack events. So if we run that, there you go. You can see all of the events that happened in that creation of that stack. And so if while it's running, instead of waiting for it, you could run a command like this and just keep tabs on it and see where it is. Some templates may have more resources than others. Some resources may take longer to create. And instead of just waiting on a blinking cursor, then you could run a command like this describing the stack events to see where it's at. Of course, you could log into the console as well, but I find that when you have commands like this that are already stocked and ready to go, especially if you alias them within Bash or ZSH, then you can be much more fluent in the command line than clicking through the screens of a GUI. Okay, so now that we've created the internet stack, we've listed out all of the events that took place during the creation of that. And we can see that ultimately our microservices internet has reached create complete, right? So now let's go ahead and capture that VPC ID one more time, just like we did earlier, filtering by the microservices network, pulling out the ID of the first VPC. There's only one VPC so far that's named microservices network. Based on that, we know that we're going to get the right ID. Let's go ahead and do that one. Make sure that we've captured that VPC ID one more time. Okay, so now that we've gotten the VPC ID, let's go ahead and show the route. So here we're going to use describe route tables. We're going to say filter that by VPC ID. So let's take a look at the routes. And there we go. That will pull back all of the route tables that we had created, including a default route. Every VPC that is created gets a default route table. Even though we didn't explicitly create one in the VPC or in the internet stacks, because we created a VPC, it already created a default route table for us. So that one is also in this list. Okay? So one last command here is that we can get those with some cleaner output. Here, what we want to do is for every route table in that list, we want to find the value of the name tag, and we also want to show the subnet ID that it's associated with, or the list of subnet IDs. For every association, we're pulling out the subnet ID. Okay, so let's run that one. And there we go. We can see that our private routes are associated with 3 subnets, and our DMZ or public routes are associated with another 3 subnets. The default route table will still be associated with our database subnets. And of course, the IDs that you see will be different than the IDs that I see. So that is creating gateways and routes with AWS CloudFormation. In this lab, we'll use AWS CloudFormation to manage network access control lists. Now, what we're going to do in this lab, again, we have our public subnets that have access to the internet. We have our private subnets that have protected outbound only access to the internet. So we want to create some network access control lists that allow only certain types of traffic, regardless of what machines are in there. You can think of these as guardrails. And so if someone were to inadvertently open a security group to, let's say that on the security group they opened port 22 to anywhere, they will still be protected by the network access control list. So in this lab, we're going to create a network access control list that allows UDP port 123 from anywhere to come in. So we're going to create inbound access and outbound access, ingress and egress rules that allow UDP 123 to pass anywhere. And then we're going to rely on the all other traffic being denied. Now, for the sake of this particular lab, we're only going to focus on the public subnets, restricting access to UDP 123 for the sake of network time. And we're going to allow the private subnets to receive all traffic, to send and receive all traffic. Because they are inherently protected from the internet by way of routing, we don't have to worry about network access control lists being wide open on those. So again, for this lab, we're creating a network access control list that allows network time protocol traffic to come in and out of our public subnets. Okay, so in our text editor, we're going to open 3.5 bash commands. And just like before, the first thing that we want to do is validate our template. Before we do, let's take a look at that template. CloudFormation, network, microservices, security. We have 2 of those. We have security and then security-2. We're going to come back to -2 later. For now, let's open security and take a look at what we're doing in this one. So again, just like earlier, we're going to reference the network stack because all of the things that we're doing in this template will be applied to the VPC that we created earlier. So here we're going to create a network ACL, a network access control list, again, which is a firewall for the subnet as a whole. And here we're going to call this one internet traffic. So we're creating a network access control list around our public subnets, our public DMZ subnets. Again, we are using the substitute intrinsic function along with the import value function to bring in that exported value, the VPC ID that we exported from our VPC stack. So we're creating the ACL. We're then going to associate that ACL with all three of our public DMZ subnets. So you can see here we're also importing values for all three of those. We're going to associate all three of those A, B, and C. And then down here, what we're going to do is create an inbound and an outbound rule. In this case, we're going to allow protocol 17 is UDP. So we're going to allow UDP port 123 from anywhere to come into our subnet. And down here, we basically have something very, very similar. The only fine difference is that we're specifying egress equals true, which makes this an outbound rule. So we're allowing NTP traffic, network time protocol. We want our cluster of machines to be able to communicate with time servers out there on the internet. And so we need UDP port 123 to be able to flow through both in and out of our public subnets. And that's all we're going to create in this particular lab. Okay, so first of all, just like before, let's go ahead and validate that template. So our microservices security template validates. Again, we can see, we know it validates because it's showing us a list of our parameters. And of course, now the next thing that we want to do is go ahead and create the stack. We're going to create a stack and we're going to call it microservices security. Now, hopefully you can see at this point, because we've separated all of these resources into different stacks, our VPC and subnet into one, our gateway and routes into another, and now our network access controls into another. Moving forward, if we need to make changes to routes or make changes to network access control lists, we know exactly where to go to make those changes, instead of trying to dig through a really long template. And so a common thing in a cloud operations role may very well be to whitelist different IP ranges. And we might want to do that in the network access control lists. Now, if you do that manually, either using the CLI tools directly outside of CloudFormation or using the console, there's no way to leave yourself a note as to why you whitelisted that IP range. But using YAML, if we look at our YAML file, you'll see that there are all kinds of comments that I've left into these templates. And so if later we come back and add more ACL entries for the purpose of allowing certain traffic from certain sources or to certain destinations, then we have a way of commenting and reminding ourselves 6 months later, why did I whitelist and allow that particular range? Without a comment, it would be really easy to forget what that range is, what purpose that range serves. Let's go ahead and create this stack, again, using the dev profile. So let's go ahead and do that. Here again, for parameters, we're using the network stack parameter, and we're passing in microservices network as the value so that this template can use that as a way to import those values. All right, so now that we've got an ID, we know that creation is in progress. And here we're going to wait for that to finish, or we could list the events if we wanted to. This one being ACLs and ACL entries should create pretty quickly. All right, so let's go ahead and wait for that stack to finish. And it's already done, just like that. So you can see that some CloudFormation stacks, depending on the resources involved, will create faster than others. So that one's already finished. Okay, so now again, just like we've done before, let's capture the VPC ID so that we can use that in subsequent commands. We're going to capture that. We may already have it, but sometimes if you have left and come back, closed your terminal or console, and then come back to it later, then this ID might not be there. So it's just safe to go ahead and do it again. All right. So we've got our VPC ID captured. So now let's take a look at our network ACLs. We're going to use the describe network ACLs command. Again, we're going to filter by VPC ID, and we're going to filter by, noticing here, we're filtering by the CloudFormation stack name. CloudFormation will apply its own tags to resources. And so here, I'm looking for not just network ACLs attached to this VPC, but I'm looking for specifically for ones that were created by this template, which would exclude the default ACL, which I'm not interested in at this time. We're also going to give it query parameter. Here, what we're saying is, I want the network ACL ID and the value of the name tag for every network ACL in that list. And I want to see that as text-based output. All right, so let's go ahead and run that one. Describe network ACLs. And there we go. You can see here is the internet traffic ACL that CloudFormation created based on the code within our YAML template. Now let's take a look at the entries that are in there. Not just the ID, but let's take a look at all of the entries for every network ACL that's in that list. We're going to go ahead and run that last command. And there we go. You can see that we have a number of entries. We are allowing UDP port 123 to go out. We are allowing UDP 123 to come in, so that means egress equals false. That means an inbound rule. And then, of course, you can see here rule number 32767. That just means the default rule is to deny all traffic. These rules are evaluated in ascending order. So it will start with rule number 100, and if it doesn't find one, it will end with being denied, right? So the only traffic that's being allowed right now is UDP port 123. I will leave you with that, and I would encourage you to challenge yourself to play around with the query parameter to manipulate the output of this into something more humanly readable. That is how we can manage network ACLs with AWS CloudFormation. Now let's talk about using change sets in AWS CloudFormation. Change sets are a really powerful feature that gives us ultimately a preview of the changes that we will see when we update a CloudFormation stack. There are plenty of times when we might want to make changes. Let's take our network stack as an example. We might want to later come back and update our network access control list rules. We might want to whitelist certain IP ranges. We might want to add certain protocols for whatever reasons. We might want to change the instance type on an autoscaling group. We might want to add new availability zones to our network or to our autoscaling group. And before we actually make the change, we want to see a preview of the change. And so in that preview, it's going to show us the resources that are going to be changed. It's going to show us the scope of changes, whether or not we are adding, removing, or modifying existing resources. And a really important one is whether or not that change will require a replacement. This is a really, really important thing to take a look at, because in some cases, certain changes can't just be made in place. Certain changes require that a resource be deleted and replaced. If you were to make those changes without going through a change set, you could get yourself into a very precarious position. I speak from experience. I have seen this happen on autoscaling groups where, without realizing it, the autoscaling group was replaced, which meant that the instances inside of it were terminated. Luckily, in my experience, that happened in a development environment and no harm was done. But that kind of thing happening in a production environment could be catastrophic. So by doing a change set, we can be warned that a change might require a replacement, which in turn might require a maintenance window or might require us to go about things in a more careful or a different way. Another nice thing about change sets is that they are great for auditing change management so that you have a paper trail of the changes being made. And then, of course, once you have that change set, once you have verified the changes and the resources that are going to be affected, perhaps someone else in the organization has looked at it and given their approval, then you can execute those change set updates, which will then update the stack on which you were trying to apply those updates. And again, we can use the AWS command line tools. We can call the CloudFormation service and call the create change set action to create a change set. And then, of course, executing the change set is an additional step. So again, lots of benefits to be had by using change sets with AWS CloudFormation. And my recommendation is anytime you update an existing CloudFormation stack, always use change sets so that you know exactly what you're going to get as a result. In this lab, we're going to apply some change sets to AWS CloudFormation. Now, in this particular lab, again, we're going to allow, not only do we already have the ingress and egress of NTP traffic on UDP port 123, that's already there. What we want to add now is the ability to allow port 80 and 443 to come in. So we want ingress port 80, 443 from anywhere. And we also want egress of port 80 and 443 to anywhere. We want also, in order to receive the response traffic back from those HTTP requests, or to allow the responses to go out, we need to open the ephemeral port range. And so we're also going to allow TCP 1024 through 65535 from anywhere to come in, and we're going to allow that same ephemeral range, 1024 through 65535, to go out to anywhere. So these are the changes that we're going to be making to the network access control list for our public subnets. Okay, so back to our code base. We're going to open 3.7 bash commands. And here, we're also, before we validate our template, let's take a look at microservices security -2. So -2 is just going to show us the differences, how we can apply change sets. So it's basically the same template, except I've added a few more network ACL entries to it. Okay, so let's open up microservices security -2. Now here, again, this is basically the same template, but down below, I want to show you how we've added a few more entries. So this is an example of how later, if we come back and we want to add more rules to our network access control list, to open more things or to close other things, then we should be doing that in an automated way. We really should not make a habit of going to the console just to make the change and then you forget why you made it. And then 6 months later, you're gone and someone else has taken over and they have no idea why you did what you did because there's not much record of it. You could probably go back and find it in CloudTrail, but within the console, there's no direct correlation. So again, giving yourself notes is really the best way to go about something like that. So here, we're going to allow, because our public subnets, we're going to have a load balancer in our public subnets, ultimately. We need them to receive HTTP traffic. We need them to receive port 80, and we need ephemeral ports to go out. Okay, so we're going to allow those port 80 to come in. Protocol 6 is for TCP. And of course, we're allowing that to come in from anywhere, which essentially means the internet. We're going to allow port 443 to come in. We're going to allow port 80 and port 443 to both go out. So Port 80 and 443 can come in from the internet. They can also go out when the load balancer forwards the request from the load balancer itself to our backend instances. Those ports will go out to our backend instances. And then the ingress ephemeral ports, when our EC2 instances respond to something, they will respond in the ephemeral port range. So those packets need to come in to our public subnets, and they also need to go out, back out to our users out there on the internet. And so those are the ACLs that we've added here, and everything else is just as before. We're still referencing the DMZ ACL, so all of these entries are being applied to the DMZ ACL, the public ACL. And we should see in our change set that these additions here, these different ingress rules, are being added. So the first thing, just like before, let's validate our template, make sure that there are no syntax errors. Let's go ahead and run that one. It gives us back a list of parameters, so we know it's good. Now what we're going to do is, instead of just calling the create change set command, we want to also capture the ID of that change set so that we can use that ID later. So here, we're going to create the change set. We're going to give it a name, change set name called allow HTTP traffic. It will apply to the microservices security stack that we created. We're going to reference the template body. Here we're referencing microservices security-2. Now notice what we do for parameters. Anytime we do an update, we could either change the value for that parameter, or we could use the previous value. So in this particular case, I'm going to create a change set saying for the network stack parameter, just go ahead and use the previous value. Now what I'm going to do is, since I know that the create change set command will return a JSON object, all I want out of that object is the ID field. I'm going to query for the ID field and then output that as text, which we will capture in the change set variable. Okay, so let's go ahead and run that. There we go. Sometimes that takes a little bit longer than we might think it should take, but now that it's returned, let's echo the change set and see, there we go. Now we have an ID, an ARN, that represents the change set that we just created. From here, now we have satisfied change management processes. Now we could have other members of our team review this change set and get a second pair of eyes saying, yes, I've seen it, I approve it, and so on. And so there are several things that we want to look at in this change set that I want to point out. Let's view the details of that change set. So here, again, we're going to call the describe change set command, and we're going to tell it which change set we're interested in. There could be several change sets out there. Here, we're interested in the change set that we just created. And for the change set name, even though we gave it a name up here, sometimes this can be confusing about the CLI. Again, the documentation is your best friend. The change set name that we gave it up here actually won't work for this parameter here. We have to give it the ARN that we captured. Okay, so let's go ahead and copy that. We will run the describe change set command. There we go. Came back. Sometimes those things come back really fast. Sometimes they take a little bit longer. So we can see here the change set itself has reached a status of create complete. This is different than the CloudFormation stack. So this status here is talking about the change set. What we're really looking for through this data is for what type of changes are being made. You can see here the resource change we're seeing add network ACL entry, add network ACL entry, and so on. We're simply adding a number of network ACL entries, but that's not the easiest to read. So let's get some cleaner output. Here, instead of all of that other data that we might not be interested in, let's pull out, for all of those in that array, let's just pull out the stack name and the resource change within the list of changes. So let's try that one and see. There we go. So now this is much easier to read. We can see that we are adding an egress HTTP. We're adding an egress HTTPS, web ephemeral. We're also adding 3 ingress rules for HTTP, HTTPS, and ephemeral ports. It's really important to take your time to make yourself aware of exactly what changes are being made to your CloudFormation template. Some changes can be done directly on the resources. Some changes can be made by updating that resource in place. Other changes require a replacement of that resource. So it just depends on that particular change. Any time you see here requires replacement, or if you see the word replacement, you really want to step back and understand the type of the effects that might make on your infrastructure. So I can speak from personal experience. In one case, I had an autoscaling group that the change that I made to it required replacement of the autoscaling group. I did not go through a change set process. I just made the update. And then because the autoscaling group was replaced, that meant that all of the EC2 instances that were existing in that autoscaling group were terminated. And fortunately for me, I did that in a development environment and no real harm was done. Had I done that in a production environment, I would have found myself in a lot of trouble. So learn from my mistake there and always go through a change set and always take the time to see exactly what changes are being made. If you see that something's requiring a replacement, then make sure that you are aware of what that means for your environment. Now that we've reviewed the changes, let's go ahead and apply the changes. And you can see here what we're going to do is we're going to execute the change set. Again, specifying the change set name as the ARN that we captured earlier. And notice here we're using the bash double and to do 2 commands at once. Not only do we want to execute that, but we also want to wait for it to complete. Here, we know that executing a change set will cause a stack to be updated. So here, we're going to wait for the stack to reach a stack update complete status. So we're going to do both of those at once. I'm going to go ahead and copy that, execute the change set, and wait for that change to be complete. In this case, since we're only adding 6 network ACL entries, this particular change should happen pretty quickly. And there we go. How long it takes for yours to come back may appear longer than what it does here in the video. All right, so again, we're going to do some other describe. We want to describe the network ACLs. Again, before we do that, let's once again capture that VPC ID. If we want to, we can echo that just to make sure that we've got it. And now, let's describe the network ACLs for that particular VPC, for that particular stack, the microservices security stack. And here, let's pull out the value of the tag name and the network ACL ID. And we're going to output that in a table form so it's easier for us to read. So let's go ahead and run that one. The describe network ACLs. Again, we only have one ACL that we're concerned about right now. That's for internet traffic. Here, let's take a look at the entries one more time, and you'll see that if we compare that to what we did earlier, we will have many more entries. So here we're looking for all entries for all network ACLs, and we're going to output that in table form. So let's run that one. There we go. You can see now we have a lot more, but in table form, because we have the port range here, the port range is a nested object. You can see nested objects will give us nested tables, and that's not really the easiest to read. So we can manipulate that and make something that is easy to read. And we would do it like this. We're going to take that same command and modify it slightly. Back here in our query parameter, notice what we're doing here. For every entry for every network ACL, we're going to create our own custom object. And here, we're going to essentially rename all of those things. We're going to say the number is the rule number. So this is what I'm calling it. And this rule number here is what I expect to find in the data coming back. I'm going to rename rule action to rule. I'm going to rename CIDR block to range. I'm just going to call protocol, but because we're building an object, I still need a key and a value. It just happens that in this case, I'm keeping the same key, and the same thing for egress. Here, I'm going to use the join function to join our port range from and port range to. So instead of allowing the port range to be a nested object, I'm going to essentially combine those into one field on one line. And here, because those are numbers, I also need to convert them to strings. So I'm using the toString function. Then I'm also going to output that as a table. So let's go ahead and run that one. And there we go. That is much easier for us to read. You can see here that we're looking at all of our outbound rules first. Here is our UDP port 123 going out. Here is 80.443 and our ephemeral ports going out to anywhere. And then we're seeing the same thing when we see egress equals false. That means inbound rules. And so we're allowing all of those same ports to come in. And so this network ACL will prevent people from trying to come in through SSH, but it will allow people to come in and out over HTTP and HTTPS. That is how we can apply change sets using AWS CLI tools. Let's review Amazon Route 53. With Amazon Route 53, this is Amazon's DNS service. We can register new domains, we can transfer domains, and we can, or if we want to use a registrar somewhere else, we can also just use AWS name servers as well. Besides public DNS traffic, we can also use Route 53 to host private zones. So we can have private DNS that is not published out to the public internet and made publicly available. Route 53 supports a number of different routing methods, and it can also support health checks and monitoring, ensuring that certain endpoints are healthy. And so using health checks, we can tie health checks in to failover routing so that if one particular endpoint, perhaps a load balancer in one region, perhaps the system there fails, and Route 53 detects that, we can use the failover routing mechanism to switch our users to another endpoint, perhaps a load balancer in another region, or even on premises as well. So besides failover routing, we also have latency-based routing. Latency-based routing says that the Route 53 service, when a request is made for a DNS query, when our end users are looking to get an IP address for a particular name, then Route 53 will give them an IP address that will ultimately give them the best latency. Generally, that means it's going to be the closest. We can also do specific geographic regions. Outside of the US, we can specify by country. We could say that England, Spain, and France all go to the Frankfurt, Germany region. Within the US, we can go down to the state-by-state level. We could potentially say everyone in Florida, Georgia, and South Carolina go to Virginia, and everyone else goes to Ohio. So we can target by state, geographical region. We can also do weighted sets, and weighted sets is a way of saying that we want a particular percentage of traffic to go to one place and another percentage to go somewhere else. We could have 90% of our traffic go to one region, 10% of our traffic go to another region. Weighted sets is also a really great way to transition users from one environment to another environment. Blue-green deployments become really easy using weighted sets. So with blue-green deployments, we're going to replace the blue system with the new green system. And in that regard, maybe you've replaced a system and you're not ready to switch all 1 million users over to the new system. You want to go a little bit at a time so that if things go sideways, you have a very easy way of going back. And so using weighted sets, we could say, let's send 1% of our traffic to the green system. Things are fine. Everything's okay. Let's ramp that up to 5%, to 10%, and so on and so forth until we have all of our users to the new system. We also have within Route 53 some very unique features for the root domain. Keep in mind that with normal DNS, with standard DNS, the root domain, or what we call the domain apex, being the domain without any subdomains on it, typically needs to be an A record pointing to a static IP address. But as we know with AWS, especially if we're using an S3 static website, if we're using an elastic load balancer and we want to point our root domain to an elastic load balancer, then we don't get static IP addresses. We know that we don't depend on the IP addresses that come from an elastic load balancer. Ultimately, we connect to a DNS endpoint. The load balancer has its own DNS endpoint. So some of these unique features would be like the use of alias records. Alias records allow us to create a record for the root domain and point it to things that ultimately have fickle IP addresses, non-static IPs. So that's Amazon Route 53. Now again, with Route 53, we can create public hosted zones and we can create private hosted zones. If we have resources like S3, let's say that we're hosting a static website in S3, or we're hosting some kind of an API or web service behind an elastic load balancer. Both of those services are going to give us ultimately a DNS endpoint. And if we want to point our root domain to those, we need a way to do that, and we can do that with an alias record. For the case of my personal website, talentedmrjones.com, that is hosted out of an S3 bucket. And you can see here that the root domain, not only do I have name server records and MX records for mail, but the A record for my root domain, you can see here is an alias record to a S3 website DNS endpoint. And by making a call to Route 53 to get an IP address back, this alias record will return the appropriate IP address for that S3 bucket at that time, because the IP addresses can shift. With private hosted zones, we might want to use these internally. Our internal applications running on EC2 may want to make use of private hosted zones for the sake of internal functionality, and perhaps we don't want those IP addresses published out to the internet. So with a private hosted zone, those will need to be associated with VPCs. Every VPC that needs to use this hosted zone needs to be associated with that zone. And then of course we could do the same thing. We could, if we wanted to have a particular API, an internal API, then we could create a private hosted zone, create an A record, which is an alias to perhaps the DNS endpoint of an elastic load balancer. If we want to have a Cassandra cluster, say, some kind of a clustered system using DNS for its clients, then we could create A records there as well. So here is an example of creating an A record for nodes within a Cassandra cluster. And of course, we do have control over the TTLs as well. And this kind of thing here, creating A records for different nodes, can be done programmatically using the SDKs and the CLI tools. So that is an overview of Amazon Route 53. In this lab, we're going to create Amazon Route 53 private zones with AWS CloudFormation. Here, what we're going to do is create a private hosted zone. For the case of this lab, I'm going to call my zone tmj.aws. Again, .aws is not an official top-level domain, but for the case of private hosted zones, it doesn't matter. We can do that. I use .aws so that when I come back and look at my code, if I see anything referencing .aws in my code, I know that will signal to me that I'm using a private hosted zone. So we're going to create a private hosted zone. You will use your value there. I'm going to use mine. And we're going to see how we can use this private hosted zone to then later create other records within that for use within our applications. We're also going to, aside from creating the zone, we're also going to associate it with the VPC that we've created. Okay, back to our code base. We're going to open 3.9 bash commands. And here, what we're going to be looking at is creating these hosted zones with CloudFormation template. So let's go ahead and open the CloudFormation network private hosted zones template file. Now here, you're going to insert your domain name, whatever you want to call it. Doesn't really matter. Even if it's not a registered domain, doesn't have to be. Because it's a private hosted zone, it can be whatever you want. In my case, I'm going to call mine tmj.aws. So I'm also going to hard code my VPC ID here and the region for that VPC. So you will enter the domain name that you want, and you will keep track of that. We're also going to copy our VPC ID, which we should have gathered earlier. We can go ahead and capture that to a variable, right? So let's go ahead and capture our VPC, just like we've done before. And if it asks you for the MFA, let's go ahead and put that in. It may or may not, depending on when you get to it, whether or not they've been expired, right? So I'm going to enter my MFA pin, and now if I echo the VPC ID, I'm going to copy that and paste it in here. The reason I'm pasting it rather than using variables is because Route 53 is global, and so I might create this stack in the Ohio region, but also affect VPCs in other regions. And here, I might want to hard code this just to be explicit so that later I can come back and see, okay, here I'm going to leave a note. This is our microservices network in US East 2. So now I have an explicit list of VPCs that are associated with this particular private hosted zone. If I later want to run microservices in another region, I would end up with another VPC, and I would want to apply that VPC to this same hosted zone. And so here, later on, we could just extend this list of VPCs by adding those VPC IDs and VPC regions. And so here, we know that the VPC that we created was created in US East 2. So I'm going to save that. You will enter the name for your private hosted zone, your domain, and you will enter the VPC ID coming back from work that you've done. Okay, so now that we've got our private hosted zone file all nice and ready, we're going to, again, just like before, let's validate the template file using the CloudFormation validate template command. There we go. Because it shows an empty list of parameters, we know that the template is valid. There are no syntax errors. Just to be sure, we probably already have that VPC ID, but let's do it one more time just to be sure, because we're going to need it. And of course, this is an example of how you could do this programmatically by just allowing this parameter to flow to the following steps, right? Of course, if you were to script all of this and make it an executable shell script, then all of this typing and copying paste won't be necessary. Okay, so now what we're going to do is create that stack. Just like before, we're going to create the stack and we're going to call that, let me collapse that, we're going to call it private hosted zones. Going to point to that file, and we're going to wait for that stack to complete creating. Okay, so we're going to do all of those at once. Let's go ahead and run that one. Create the stack and wait for it to complete. Okay, so there we go. Our stack has finished creating. So now let's go ahead and list the hosted zones by name. Here, we're going to replace this particular placeholder here, including the less than, greater than signs, with the domain name that you chose, whatever it is you put in there. In my case, I'm using tmj.aws. I'm going to paste that and list out the private hosted zones. So there you go. You can see that I have a private hosted zone created. That is how we can use AWS CloudFormation to create private hosted zones with Route 53. In this lab, we will use Python to perform Amazon Route 53 zone updates. In our code base, we're going to open 3.10 bash commands. And here you notice one of the first commands here is to run a Python script. So before we do that, let's actually take a look at that Python script, and we can find that in source scripts update Route 53. So here, the first thing of note is that we need to import a few things. We're importing sys so that we can gain access to command line arguments. And then we're importing Bodo3, which is the AWS SDK for Python. This is the high-level abstracted SDK. Now, because we're going to run this particular Python script locally, we need a way to tell it to use our dev profile. And so we're going to create a session, and through the session specify the profile name, and then our Route 53 client will be created from that session. If we were to run this script on EC2, then we won't need this. We could just get rid of this profile name, because running on EC2 will already be configured in the way that it should be using roles. So again, because we're running this locally, we need to tell Python to use, or we need to tell the Bodo3 SDK to use the dev profile that we configured with the CLI tools. So again, the SDKs and the CLI tools will all look to the same place for their configuration. And so what we're going to do here is the first command line argument will be the name of the zone. The second argument will be the name of the record. And the third will be the IP address. The first thing that we're going to do is get the ID of the zone. So we're going to ask the Route 53 client to list hosted zones by name, and we're going to pass in that zone parameter that we captured from the command line arguments. The next thing that we'll do is capture the hosted zone ID from the data that was returned. So the ID will be available in a dictionary returned as the first dictionary in a list of hosted zones. The next thing that we want to do is make a call to the Route 53 to change resource record sets. And what we're going to do here is these are the changes that we're making. In this case, we're only going to make one change, but that change is still ultimately a list of dictionaries, even though it only contains one change. And so here we're going to perform an upsert action. The upsert says that if it's there, update it. If it's not there, insert it. We're going to add the name, and notice that we're following it with a period. We're concatenating the name with a period. So in DNS, the names generally need to end with a period. That's just a part of DNS, but we don't want to have to remember that when we type in that command line argument. We're going to say that this is an A record. We're going to set the TTL to 30 seconds, and the resource records for that, the value of that A record could be a list of IP addresses. In this case, we're only going to supply one. So one question would be, well, why are we doing this with Python instead of the CLI tools? And the honest answer is that either one will work, and it's up to you which one you want to do. The reason that I've chosen Python is that some things, when you really look at the syntax and the steps that are involved, some things are just easier to do using the Python SDK, and this is one of them. So let's go ahead and go back to our bash commands. We're going to execute that Python shell, and here we're going to go ahead and replace some things. The zone name that I chose, again, was tmj.aws. The record name that I want to supply, here's an example. This is somewhat arbitrary, just as a way to show you how we can make changes to Route 53 programmatically. As an example, let's say that we were running some clustered system like Cassandra or MongoDB or Kafka or Zookeeper or just about anything, and we wanted those systems to, as they booted, as new machines joined those clusters, we perhaps wanted those machines to record their own private IP address with Route 53. And this is how we might be able to do that. And so here, let's say that, in this example, we are updating a record for a member of a Cassandra cluster. So the name in that regard could be something like node a.cassandra.dev.ohio.tmj.aws. The nature of that domain name is completely up to you. So long as you adhere to DNS standards, and as long as you adhere to the characters and names that Amazon allows, you can pretty much do what you want. Now here, I've chosen a scheme that represents my top-level zone for my organization, and here I'm saying I'm isolating resources by region. In this case, Ohio. I'm also isolating resources by environment. So here I'm saying I want a record for one node in a Cassandra cluster in the development environment in the Ohio region. And so that's my organization. If you want to adopt that, great. If not, then you can find a way of organizing domain names that works for you and your organization. The next thing that we'll need to do is specify an IP address. Now, if you're doing this programmatically by running these on EC2 during bootstrapping, then by all means you can use instance metadata to pull that IP address out. And we will talk about that later on. Here, I'm just going to give it an arbitrary IP address, 10.111.0.1. It can be whatever. Okay, so let's go ahead and run that. Python will ask for our MFA code, and we'll enter that 6-digit PIN, and there we go. We didn't get an error, so that means that our record was updated within Route 53. So now we can use the CLI tools to verify that. The first thing that we want to do here is something very similar to what we did within Python, is to get the hosted zone ID. Here I'm going to change this name to the name that I chose earlier. You will put the one that you chose. And here, we're going to use the query to pull out the ID of the first element in the hosted zones list, and we will output that as text. So let's go ahead and capture the hosted zone ID. Let's echo that. There we go. So now we know that we have a value back, and we can correlate the value that we got from that describe with this up here. What came back from listing the hosted zones earlier. So now that we have the hosted zone ID, let's go ahead and list the resource record sets that belong to that hosted zone. Again, using that bash variable back here for the hosted zone ID. List resource record sets. There we go. We get back a list of, you can see here we have name servers that exist there, which we're not really concerned about right now. What we're concerned about is, here is our A record for node A, Cassandra, and here's the value that we gave it earlier. If we wanted that in a cleaner output, we can run the same command, but we can use the query parameter to again build out a custom object and put that in a table form. So here we're going to use a custom object. We're going to rename resource records value. We're going to pull that value out of that list of resource records. We're going to call that the IP, and we're going to use name as name. Okay, so let's run that one. And there we go. There are the records that we currently have in our Route 53 private hosted zone. So that is how we can use Python to make changes to Route 53 private hosted zones. Object storage in Amazon Simple Storage Service gives us an easy-to-use, scalable, and durable service for numerous use cases. While storing static web assets and centralizing log files are very common use cases, Amazon S3 can also be used by an operations team to help manage infrastructures, enable application deployments, and satisfy compliance auditing. In this lesson, we review Amazon S3 server-side encryption, cross-account resource sharing, and using the AWS command line interface to interact with Amazon S3. Let's review Amazon Simple Storage Service, or S3. Now, with S3 is object storage. We are storing objects, not on a file system. There is no file system. Ultimately, S3 is a key value store, and we're storing objects. Now, when we do store objects, we know that the S3 cluster spans the entire region, and so we know that S3 is storing our data across numerous copies, across numerous availability zones in that region. We know it's durable to the loss of 2 AZs, and our data will still be there. Again, we have a very flat hierarchy. Ultimately, all we have are buckets and objects. Objects go in buckets, and that's about as deep as it goes. Transfers are all done over HTTP or HTTPS. And so S3 is not geared towards giving us any degree of IOPS. We don't measure performance in IOPS. We measure performance in requests per second, because S3 over HTTP is not geared towards IOPS. If we need a file system, if we need a high degree of IOPS, then we would use something else like the Elastic Block Store. We can also use S3 to host static websites. A few other things worth noting is that ultimately there is no limit to the size of a bucket. We can have as many objects as we want in a bucket. and that bucket can be as large as, it can go into the petabytes. Now, each object, we do have a 5 terabyte per object limit. We also have a 5 gig per upload limit, or per put. So a common question here is, if we can only upload 5 gigs at a time, how do we ever get an object that's 5 terabytes in size? And we do that with multi-part upload. Multi-part upload requires, in the case of uploading something 5 terabytes, or as Amazon suggests, anything, really anything over 100 megs, you can gain some performance improvement by using multi-part uploads. And we have to initiate a multi-part upload, split that file into chunks, upload the parts, and then complete the multi-part upload. The CLI tools and the SDKs will do all of that for us. S3 also supports server-side encryption. It uses the industry standard AES 256 algorithm, and when we do that, we get a key per object. That way, if any one key is ever compromised, only that one object will be compromised. Those keys are then further encrypted by a master key, which is regularly rotated. Now, when it comes to server-side encryption, we do have a few choices as to where the keys come from. We can have Amazon manage the keys in a number of different ways, or we as the client can manage the key and give it to Amazon to do the server-side encryption. For the really paranoid types, we could encrypt the object client-side and encrypt the object server-side as well. Now, in terms of the hierarchy, again, the way that we access objects is by way of a DNS endpoint. In this example, we have a DNS endpoint that would point to the US West region. So in this example, our bucket exists in the US West 2 Oregon region. And we have the name of our bucket, slash, and then our key. In this example, the key contains a slash and a period. So we can create the illusion of a file system by using slashes and periods in our name. Ultimately, there is no images folder, and there is no cat1.jpg file. There is an object whose key contains a slash and a period. Now, one way that we can control access to our S3 buckets is by way of resource-based policies. Now, resource-based policies are the same type of policies like we would see in the Identity and Access Management Service, but they are applied at the resource level. The Amazon Simple Storage Service supports resource-based policies, as does the Simple Queue Service, the EC2 Container Registry, among others. Now, within these resource policies, because the policy is applied to the resource is implied. And so we have to explicitly specify the principal, or who it is that we are allowing access. Now, as far as the principal goes, we could specify another account to do cross-account resource sharing. We could specify a particular IAM user group or role. We could also specify another AWS service to allow an Amazon service to act on this resource on our behalf. We can also make, in the case of an S3 bucket, we can make it publicly readable by anonymous users. And so using resource-based policies applied to the bucket, that's how we can further control access to that resource. Now let's talk about enforcing encryption for Amazon S3 objects. In order for us to enforce encryption, we have to apply a policy to the bucket itself. So again, as we've talked about, that is going to be a resource-based policy that we apply to the bucket. This is going to be the document, our policy document that we apply. You can see here the SID is ultimately arbitrary. I generally like to name these something that makes sense to me, so that if I do have a long document, then the SID becomes something that means something to my brain. Now, the only stipulation there, besides certain characters being allowed or not allowed, is that each SID within each statement has to be unique. And so here, ultimately what we're doing is we're going to say we are denying anyone and everyone the ability to upload an object if they are not using server-side encryption. And we can target that here by saying under the condition that the S3 XAMZ server-side encryption header does not equal AES 256. The only way to satisfy this condition is at the time we upload an object using the CLI tools or the SDKs, the only time we can satisfy this condition is to set the --SSE parameter to the AES 256 value. This is the only value that is currently supported. And by doing that, then we can upload. So otherwise, without the server-side encryption flag, the uploads would be denied. And you'll also notice here, as far as the resource is concerned, it's worth noting that not only do I have the bucket name, but notice here I've got /star. /star indicates objects within the bucket because this uploading an object is really going into the bucket. It's not an action on the bucket itself. So that's why we need the /star for this particular action. Now, enforcing encryptions might be important to you for a number of different use cases. Perhaps you are archiving certain types of files that need to be compliant to something like HIPAA or PCI. Perhaps you are using an S3 bucket for holding configuration files or holding some type of credential file, and you want it to be encrypted at rest. And so this is one way of ensuring that nothing can be uploaded without using server-side encryption. Now let's talk about cross-account sharing and access for Amazon S3. Now there are plenty of times when we might want to share an S3 bucket from one account to another account. We might want a number of different accounts to be able to access a bucket that's owned by another account. Now, in order to do that, again, we have to apply a policy to the bucket itself. This is one more example of a resource-based policy. In this example, we're going to allow another account. So you can see here, again, because this policy is applied to the bucket itself is somewhat implied, but we still have to specify it. We also have to specify the principal. Who is it that we are giving this access to? In this example, we're giving that access to another AWS account. Now, we can shorthand this. We don't necessarily have to spell out a long Amazon resource name for doing cross-account access. We can just do the account number. And so this would be an example of sharing one bucket in one account to another account. Now, the only thing that we're sharing in this case is the ability to upload an object anywhere within this particular bucket. Now, we are only granting the put object action. We're not granting anything else. And so the only thing that the other account can delegate is this one action. The other account that we're sharing this with cannot delegate any permissions that we have not specified here. Now, when we get into these kinds of situations where we might be sharing an S3 bucket owned by one account to another account, what we have to be aware of is the nature of ownership. There's a difference between owning the bucket and owning objects in the bucket. It's possible for one account to own the bucket and another account to own the objects in that bucket. And things, if we don't understand how that works, we could really cause some problems for ourselves. And I speak from experience. I've spent hours debugging certain situations only to realize that I just didn't understand the nature of bucket versus object ownership. So in this example, we might have a bucket owned by our admin account for the sake of logging. We might want all of our other environmental accounts, development, testing, and production, to log to one place for the sake of auditing and compliance, so that we don't have log buckets in all of these different places. We have one place for all of our environments to send their logs. And so what we're going to do is, again, we're going to create a bucket policy that delegates the put object action that allows our development account to write log files. And so we might have EC2 instances writing log files to this bucket. And of course, the way that EC2 instance gets that permission is the bucket policy trusts the development account. It allows the development account to do that action. The development account is then delegating that by way of a role. The development account grants that action to the EC2 instance. So the EC2 instance is the one that's actually putting those log files. So at this point, this is what happens. In this situation, the objects that are written are owned by the account who did the writing. So in this example, these objects, these log file objects, are all owned by the development account. Now at this point, if we don't take steps to open the permissions, we could get into a situation where the admin account is not able to read these files. If we don't do anything about this, then if we ever wanted to do some type of an analysis over here in the admin account, we could get an access denied because, again, even though the admin account owns the bucket, the development account owns the objects that were written to the bucket. And so in order to fix that, we need to make sure that the development account, when the objects are actually written, that they are written with a flag that says bucket owner full control, so that even though the development account owns the objects, it's granting the admin account full control over those objects. We might want to enforce the bucket owner access to those objects. In the case where the development account is writing to a bucket owned by the admin account, we want to ensure that the admin account will always have access to the objects owned by the development account. So we can create a bucket policy that says we are going to deny that other account the ability to upload objects if they are not setting the ACL flag to bucket owner full control. So here is the condition. We're saying that if you aren't setting the bucket owner full control flag, then you can't upload. And we can execute using the CLI tools. Here's an example where the CLI tools is saying when we do this copy, when we copy a file, we're copying it with the ACL bucket owner full control flag being set on those objects. So again, in this particular case, the development account will still own the objects in the bucket, but we are granting the owner of that bucket full control over those objects. In this lab, we'll use AWS CloudFormation to create several Amazon S3 buckets. So in this lab, we're going to create several S3 buckets within our admin account. So we're going to have a bucket for general operations, scripts, and things like that. We're going to have another bucket for configs. We're going to have another bucket for doing backups. Now, the operations bucket and the configs bucket, we are going to grant cross-account access. We're going to grant the development account the ability to get object or download objects. Now, because we're not granting the list bucket operation, the development account will not be allowed to list objects in those buckets. It will only be allowed to download objects that it knows about ahead of time. For the backups bucket, we're going to grant the put object. So we're going to allow the development account to upload to that. We're also going to enforce the bucket owner full control on that as well. And so again, we're going to delegate these permissions using resource-based policies for each of these buckets. And then of course, in the development account will use roles to delegate those permissions to EC2 instances, and then later EC2 instances can download objects and upload backups to those buckets. So again, in this lab, we're simply creating these 3 buckets and the various policies that allow the cross-account resource sharing. In our text editor, we have open 4.4 bash commands. And before we get to the CloudFormation commands, let's take a look at our template. And we can find that here under source, CloudFormation, storage, s3.yaml. So I'm going to go ahead and open that over here. And let's take a look at the template and see what it's going to be creating. And so here, instead of asking for the names of things as parameters, in this case, I'm going to just go ahead and hard code the names of the buckets. Now, in this case, what I want you to do is anywhere through this particular template, I want you to come up with a unique name for the bucket. Remember that S3 bucket names have to be globally unique across all of Amazon. Even though this bucket will exist in the US East 2 region in Ohio, the bucket name still has to be globally unique across all of Amazon. And that has to do with DNS and I'm sure some other things behind the scenes. So here, for this one, we have 3 different buckets that we're creating, and we have bucket policies as well. And so we have several places where we need to create this. So what we can do is I've gone ahead and I've set this up so that we can use find and replace. So I'm going to look for that. And here I'm going to call this one AWS Linux Ops. Bucket names, besides being globally unique, they also have to be lowercase. They cannot use spaces or underscores, but they can use dashes. So I'm going to use AWS Linux Ops. What I would recommend that you do is perhaps add your initials here and maybe even your birth date, something like that, so that you can ensure that that will be a unique bucket name. Okay, so you create your bucket name, I'm going to create mine, and I'm going to go ahead and perform this replace all here. Let me hide this. Replace all of those, and you can see that now I've got AWS Linux Ops here. Where else do I have that? Here's AWS Linux Ops configs. And so that should have replaced all of those instances of that with your unique bucket name. And you will have a bucket name for the Linux Ops, one for configs, and one for backups as well. And each one will also have a policy. So let's take a look at those. If we go all the way back here to the top, we have a bucket for general operations. We want the development account to be able to read from that. Not list the bucket, but download objects when they know about the object to begin with. Later, we might write scripts that instruct our EC2 instances to download things directly from S3. And this policy here will allow them to do that. Or at least it will allow the development account to then delegate that access to EC2 roles or users and so on. So here we're also going to find our development account number, I'm going to search for that. There's several places there that we've put that. You can see here there's the placeholders for development account numbers. I'm going to come back over here and open the accounts text file that we created earlier. And I'm going to copy the account number for our development account. I'm copying mine. You will copy yours. And I'm going to come back over here and replace all of those. And you will do the same. So there we go. Now we can review this. I'm going to go ahead and save that. So we're creating a bucket for general operations. And we're going to have some other bootstrapping and various other scripts that we might put in here. And again, we have a bucket policy being applied to that bucket. Notice here that we're creating the bucket policy as a separate resource, but we're saying that the bucket that it belongs to, we are again using the reference feature to reference the bucket for general operations that's created up here. So this is our logical ID, and we're using that here in our reference. On the bucket policy for general operations, we're allowing the development account to download objects from anywhere within that bucket. Down here for the configs, we're going to do a couple of things. One, we're going to allow the development account also to download objects from anywhere within that bucket. We are also going to say that because configuration data could hold things that are sensitive, we want to be sure that whoever uploads to it uploads using the server-side encryption setting. We want to know that things that are uploaded are done so being encrypted at rest. And so here is that condition. We're saying if you try to upload an object and the server-side encryption flag is not set to AES 256, then deny that particular action to everyone. Doesn't matter who they are, we're going to deny any objects being uploaded without server-side encryption. And then, of course, we'll create one more bucket for backups, also creating a policy for backups, and this is the same thing. We're allowing, in this case, we're going to do the converse. Instead of allowing the development account to download, we're going to allow the development account to upload backups to this particular bucket. We're going to grant the development account the ability to upload objects anywhere within the backups bucket that we're creating. Okay, so now that we understand what's happening in our YAML template, I'm going to come back over here and let's go ahead and validate. Because we've made changes, especially because we've made changes to that template, let's go ahead and validate that and see. There we go. Everything's fine. Now, if you run this and it comes back saying that there are errors, then just take your time, go through, perhaps watch part of the video over again, and make sure that your template it looks like mine, except for the differences in names and accounts. Okay, so now what we're going to do is just like before. We've seen this before. We're going to create the stack with a particular name as 3 buckets, and we're going to wait for that stack to complete. Another thing to note is that we are creating these buckets in the admin account, so we're going to run these commands with the admin profile. So let's make sure that we do that. If you're typing these out, don't forget the admin profile. We don't want these buckets in the development account. We want them in the admin account. That way later, when we have testing environments, when we have production environments, then we can come back to this template and apply permissions. We can apply policies. We can edit those policies to allow those other accounts the same type of access that development has. So that way we gain centralized collection of logs and other scripts from which we have one place to publish out. Okay, so let's go ahead and create that stack. Create and wait. This could take a few minutes. As long as you see a blinking cursor, it's still going. If it fails, it will tell you. Now it's created. So now we can describe the stack and see some details about that particular CloudFormation stack. Again, we're referring to it by name, S3 buckets. Now we can see that create complete is indeed the status of that particular stack, which meant that our buckets created. We can also, just like before, we can describe the events in that CloudFormation stack. Here we're describing the stack events, but also creating our own object by renaming a few fields. We're going to rename logical resource ID to resource. We're going to rename resource status to status and rename status reason to reason, and then we will output that as a table. And there we go. We can see that all of those different resources, bucket for backups, for general operations, bucket policies, they were all at one time in progress. They all completed, and our stack itself completed. You can see by running a command like that, if we have that command handy, if we have it in a place that we can quickly copy and paste, or better yet, if we assign that command to a bash alias, then we have a very quick way of viewing the events of a particular CloudFormation stack without logging into the console and clicking through a GUI. So that helps us to be much more fluent in our work. So now we can also describe the resources of that stack. Here, let's try that command, describe stack resources, again specifying the CloudFormation stack by name. And there we go, we get a list of resources. We can see that indeed our buckets and our policies were created. Now, if you get into a situation where you're going through this lab and because of the names of the buckets that you've chosen aren't available for whatever reason, maybe you have a syntax error in there, if you find that this stack did not create, maybe by describing the stack events, you see that it ultimately failed to create, then all you would need to do is run this. You could try it again. You could just delete the stack, wait for the stack to be deleted, and then go back, fix the template, and try again. Right? We're of course not going to do that here, but if you need to, those commands are there for you. So that is how we can use the CLI tools and CloudFormation to create Amazon S3 buckets. Now let's review Amazon S3 operations with the AWS CLI. In our text editor, we have open 4.5 bash commands. I'm going to go ahead and make sure that the colors there are shell script colors. And here, let's go ahead and minimize that. So first of all, we're going to do a few operations, but I do want to point out that there are two different services that we have to work with here in regards to S3. We have the S3 service and the S3 API service. And the difference is that the S3 service is meant to function like the native Linux list, copy, move, and remove commands. So let's take a look at that. If we run this command, again, all of these we're doing with the admin profile because we created our buckets in our admin account. So here, let's go ahead and do an S3 list command. And you'll see what we get back looks a whole lot like what we get back from the native Linux list command. It's designed that way. So let's compare that with the S3 API list bucket command. If we come back here, run that, then you can see that what we get back is a list of JSON. So if we're doing something programmatically where we need predictable data, or we need formatted data like JSON, then we can use the S3 API service. If we're just doing something manually and we want a more fluent interface, then we can use the S3 service. Now, if we wanted to filter that and control the output of that S3 API list buckets, then of course we can use the query parameter and we can change the output of it. So let's try that. Let's query, but only show us the name of every bucket. And there we go. We've listed our buckets using the list buckets command of the S3 API service, and we formatted that output, and we have a human readable list of our buckets. So now let's take a look at objects in a bucket. Of course, this is going to come back empty, but this is how we would do it. We would say S3 ls, and notice here that because we are referencing an S3 bucket, we're using the S3:// prefix. And then, of course, followed by the name of the bucket. So let's list that. And you'll see we don't have anything in there. So let's go ahead and copy a file. Here, let's just copy one file. We're going to just pick one of them. Here we're going to go for the CloudFormation access roles for EC2, and we're going to copy that. You can see here we're using the S3 cp command to copy from our local files to the same place or the same folder structure on S3. So remember that on S3, there will be no folders and files. Ultimately, what is a file in a series of folders on our local machine will become an object, however we name it. Here, we are using CloudFormation/access/roles for EC2.YAML. All of that, including the slashes and the period, all of that becomes the key name for that object. So we can name that whatever we want. So whatever we put here in this place will become the name of the object. If we want the organization of our bucket to match what's on our local machine, then we need to specify that in this key name, like we're doing here. Okay, so let's go ahead and run that one. And we'll see how we can copy a file from our local machine to S3. And there we go. It says upload. Now it's done. So if we replay the list command, we will get a prefix. So you can see here that that particular list command just shows us a prefix. Let's go ahead, and we're going to come back to more list commands in a moment, but let's go ahead and upload the entire CloudFormation directory recursively. So we can do that by, again, using the S3 service, the cp copy command, and we're going to copy this entire CloudFormation folder up to S3 and specify that it should be done recursively. All right, so let's go ahead and run that one. And you'll see, there we go, it uploaded very quickly all of the files in all of the folders, and it matched the same structure, the same folder structure and names of our local files. Those got reflected in the keys of the objects that were uploaded. Okay, so now let's list that again. Let's replay that list operation, and you will see that, again, it's giving us a prefix. We can fix that by typing out that prefix, and if we watch what happens here, if I don't include the / I still get just a prefix. So I have to include that / in order to drill down into it. So ultimately, we are not listing by folders. Again, on S3, there are no folders. What we've done here is we've essentially said, hey, S3, show me everything in this bucket that shares the common prefix of CloudFormation /. And it just so happens that there are a number of things that have, again, more prefixes. So if we wanted to, we could list all of those either by drilling down into each and every prefix, or we can also list recursively using the ---- recursive flag on the list operation. So let's try that. And there we go. Now we can see that we have all of these different objects, and that matches, if we were to do an ls-l on our /source CloudFormation, that all would line up. And we can do the same thing here with the S3 API, but it takes on a slightly different form. Notice here that we have to specify the bucket as a parameter, and I'm specifying the name of my bucket. You will need to modify this to reflect the name of your bucket. And here I'm saying let's list the objects by prefix being CloudFormation. So let's try that one. So there we go. We get back a list of JSON data. Very useful for doing things programmatically. If we wanted to make it a bit prettier, we can use the query parameter to say, let's again create a custom object for the sake of outputting to a table view. Here we're not renaming anything, but we are creating our own custom object so that our table view gets named headers. Without this object, the table view would not get those named headers. Okay, so let's try that. There we go. We can see all of those keys and their sizes in an easy-to-read view. The last thing that we're going to do is take a look at syncing. Syncing is really helpful in a number of use cases. Here, what we're going to do is we're going to sync our source folder with our operations folder, but we don't want the configuration files. Configs are going to go to another bucket, and those need to be done with the encryption flag being set. So we're going to upload a lot of our files here, but we want to, again, exclude that configs folder. And here, this is a pattern, a regular expression pattern. So we're saying, or something similar to regular expressions, we're saying exclude everything in this source folder that essentially starts with configs. So everything under the configs folder. Okay? So again, we're using the admin profile to sync our local with our S3 bucket. So let's go ahead and run that. And there we go. You can see that it did everything in the source except CloudFormation because CloudFormation was already there. We put it there with previous commands. Now what I want to show you is if we were to add files locally, then we can resync again and get only those files that were recently added. So we can use this nifty little bash command head with the dev urandom to generate a 10,000 character dummy file. All right, so let's run that. We're just going to make a random 10,000 byte file. And if we were to list source, we will see there is that 10,000 bytes worth of dummy data in that file. Okay? And so now, if we resync, again excluding the configs file, we should see that the only file being synced is the dummy file, because that was the only one that was changed. Now let's go ahead to remove that file. So let's go ahead and do that. Let's remove the source dummy file, and now we can sync in reverse. we can sync, instead of local to S3, we can sync S3 to local. Okay, so notice the difference there. In the earlier ones, we synced local to S3, source, destination, right? It goes in that order. Here, we're going to reverse that. So now the source becomes our S3 bucket, and the destination becomes our local source folder. Okay, so let's go ahead and do that. Let's sync in reverse, and we should see that it gives us back that dummy file. You can see, there we go, we just downloaded that file. All right, so let's go ahead and remove that again, and what we're going to do next is a few other things that I want to point out, some of the subtle differences in some of these commands, some things to be aware of, okay? So let's go ahead and remove that source dummy file. Now it's gone. If we list our source directory, you can see that that dummy file is gone, okay? If we were to sync again from local to S3, excluding the configs, nothing happened. Now we removed that file, and then we tried to sync from local to S3 again, but that file, nothing happened with it. Okay, if we were to list, let's list that bucket and show that the dummy file is still there in our S3 bucket, even though we removed it from our local and then did another sync command. What we have to do is include the -- delete flag. So if you indeed want to delete from the destination things that don't exist in the source, you have to include the -- delete flag. All right, so let's do that again. Using that -- delete flag, we will do that, and you will see, there we go, we just deleted the dummy file from our bucket because it doesn't exist on our local machine. Okay, so one final section here, we're going to upload our configs to the configs bucket. Remember that we created a bucket specifically for configs, which might include sensitive data like protected endpoints and credentials. There are plenty of great places to store credentials. I'm showing you one way that we can use S3 as a place to store that, and we know by enforcing the encryption on that bucket that it's going to be protected by being encrypted at rest. So here, we're going to copy the local configs folder recursively, and we will see that because of the policy we put in place earlier, that this will be denied. There you go. It says access denied. Put object operation access denied. It doesn't tell us why, but knowing the policy that we put in place that explicitly denies when we aren't using server-side encryption, we know that that's the problem. Okay, so now what we're going to do is basically the same command, but notice here we're going to specify server-side encryption, --SSE, and the value of AES 256. That is really the only valid value right now, and that is how we turn on server-side encryption for the objects that we're uploading. So I'm going to copy that one. Let's run that. Copy all of our configs to our configs bucket, ensuring that they are encrypted at rest. And you can see here we only have a couple of files in there. So we've reviewed a lot of good stuff. We reviewed listing buckets, copying files, syncing files, and dealing with encryption. And those are just some of the operations that we can do on Amazon S3 with the AWS command line interface. Perhaps more than any other service, Amazon EC2 gives us many opportunities to automate a number of tasks, from managing key pairs and creating machine images to launching instances and cleaning up unused resources. We review several valuable use cases commonly seen in a cloud operations role. We also review how AWS Lambda can be used in place of cron to keep our environments clean and keep costs down. Now let's review Amazon EC2. With EC2, we do get access to virtual machines. We call them instances. We get a sort of a price-fixed menu of various combinations of CPU, memory, disk, and network I/O. Of course, we can launch just about any number of instances. We can launch one instance at a time. We can potentially launch thousands of instances at a time. And of course, that is according to the service limits that are in place. Keep in mind that various AWS services have their own soft limits and hard limits that apply. Soft limits are there to help control resource consumption. So out of the box, your account is limited to a certain number of EC2 instances. And if you need to go above that, you just submit a support ticket to AWS for them, asking them to increase that limit. Now, one of the keys to effectively using EC2 is to consider our EC2 instances disposable. Ultimately, we are no longer treating these machines like pets. We're no longer an operations team that has invested a ton of money into a machine that we want to baby and keep running all the time. We are ultimately now handing over the maintenance of the physical layer to AWS, and we are shifting the onus of responsibility for high availability and fault tolerance to our applications. And so, again, one of those key architectural questions is what happens when this component fails? We design for failure. We assume that EC2 instances can come and go at any particular time, and we account for that within our application. So again, we should be considering them disposable. Personally, I've been using Amazon for nearly 10 years now, and I have seen EC2 instances live for 4 years. I've seen them live for 4 days and everything in between, and sometimes they just go away for who knows why. Maybe there was a problem with the underlying physical host, there was some kind of a networking issue, or Amazon decided that they needed to retire them for whatever reason. Now, when Amazon knows about something, they will give you a warning saying, hey, at some point in time, this instance needs to be retired, so, go ahead and move it. So again, consider them disposable. And in that regard, instead of patching in place, just replace them. If you know that you need an update to OpenSSL or some other underlying library that is a part of that machine image, go back to the machine image, go back to some operational instance, update the software, create a new machine image, and just replace the machine instead. And so by doing that, by replacing the machine instead, you know that you're avoiding configuration drift. You know that the machine is going to be replaced with one that comes up into the exact state that is sort of encapsulated by that machine image. And then, of course, with EC2, we have a number of different billing models. On demand is sort of the MSRP. If Amazon says that a machine image costs 20 cents an hour and you're willing to spend 20 cents an hour, then you'll get a machine and that's how much you'll pay until you decide to turn that machine off or terminate it. We also have reserved instances. Reserved instances, in some cases, do reserve capacity, and we have an opportunity here to commit to either a 1-year term or a 3-year term and pay either nothing up front and get a little bit of a discount, pay a partial payment up front, or we could go ahead and pay for every hour over that 1 or 3-year term all up front. The more money we pay up front, the more discount we get using reserved instances. We also have the spot market, which is the spot market. The price fluctuates according to supply and demand, and we are ultimately bidding on unused capacity. So the spot market, there are plenty of use cases where we can use the spot market to gain instances at a fraction of their on-demand price. Now with Amazon machine images are ultimately a bit-for-bit copy of the root volume. So whatever operating system was on that root volume, whatever applications or other configuration, whatever users were there, anything that was a part of that root volume at the time the machine image was started will become a part of the Amazon machine image. Now we can take that machine image and then we can launch clones of the original machine, and we know by launching those we get an exact copy as that instance. So that way if we do launch 1,000 instances, we know that all 1,000 instances will come up and give us the same exact state every time. Now, when we do create Amazon machine images, we know that the data here that comprises that machine image, we know that that is stored in S3. Now, we don't have to create a bucket for that. Amazon handles that for us. We know that it is stored and backed by S3, but we don't have direct access to those objects. That is all handled for us by AWS. Now with key pairs are ultimately public and private key pairs. They are 2048-bit SSH2 RSA key pairs. We can create key pairs within AWS, allowing AWS to create the key pair for us, and then we download the private, or we can create the key pair and import our own public key. I know a number of people, myself included, prefer to create our own and import our own public key. That way we know for sure that AWS never had the private key. Now AWS does tell us that when they create the key pair that they do not keep the private key. And then of course when we launch a particular EC2 instance, we will choose which key pair we want to use for that particular instance. If you don't choose a key pair, that is possible, then depending on the machine image being used, you could get into a situation where you don't have access to that machine. It all depends on the particular machine image that's being used. Now, in the case of Linux, we're going to use AWS will copy the public key. They will add that to the authorized keys file for whatever user is marked as the admin user. For Amazon Linux, it's EC2-user. For Ubuntu, it's the Ubuntu user, so on and so forth. It just depends on the flavor of Linux. We will then use the private key pair or the private key for logging in over SSH. In the case of Windows, AWS will use the public key pair to encrypt the administrator password. We will use the private key to decrypt the Windows password. Now, the way that we can control what permissions an EC2 instance has in regards to other Amazon resources is by way of roles. We can apply policies to roles that grant, and then of course we can assign roles to EC2 instances. And through that, we can then grant any applications running on our EC2 instance the ability to interact with other Amazon services such as S3. Now, again, the way that happens is if we are using the CLI tools or the SDKs on this EC2 instance, the CLI tool and the SDK will automatically detect that a role is being used, that a role is in place. The CLI tools and the SDKs will then use that role information to automatically call the security token service on our behalf. It will then use these temporary credentials to make calls to other Amazon services like in this example, S3. When those temporary credentials expire, the CLI tools, the SDKs will automatically refresh those temporary credentials by again making a call to the security token service, and getting back those temporary credentials. So the really beautiful thing about using roles is that they give us a way of using, automatically rotating credentials so that we don't have to embed long-lived credentials within our code. Now let's take a look at managing key pairs using the AWS CLI. Here in our text editor, we have 5.2 bash commands open. And the first thing that we're going to do is use the CLI tools to create a key pair. And by running this command, again, we're using the EC2 service in our dev account. And here, we're going to create a key pair. This will cause the key pair to be created on Amazon's side. So Amazon will actually create the key pair and then give us the private key. So let's go ahead and do that here and see what happens. We're going to call this key name lab, and we're going to end up creating this key pair several times here just to prove some points and see how things work. All right. So let's go ahead and run that here with the dev profile, create key pair. And of course, we're doing this in our dev account, so it is going to ask us for our MFA PIN number. So I'm going to open up my device here, enter that PIN again, and there we go. Now you can see that it created a key pair and it gave us back the private key. And now Amazon documentation says that Amazon will keep the public half of that key pair, give us the private. The documentation says that Amazon does not keep the private key pair, and so this right here is our only opportunity to save the private key. If we lose it, there is no way for us to recover that from Amazon. We would have to create a new key pair. So from here, let's just go ahead and delete that one because we need to run the command in a particular way that saves that key material. All of the data that makes up that particular key, we want to be able to save that. And if you notice, all of that material came out through the command line. So yes, we could technically, copy and paste this into a file that would be our key pair. But the fact is, if someone were to scroll back in your history, the material of the key pair is still there, and we don't want that. So we want to run the command in a way that avoids this material being output like we see here. So we can do that with this command. We can create the key pair, we can query for just the key material, output it as plain text rather than it being wrapped in JSON, and then we can output that directly to a lab.pem file, and that would create our private key. So let's go ahead and do that. So you can see what happened here is that because we tried to create the same key pair with the same name, it's giving us an error. It says that particular key pair lab already exists. That's because we tried to create it twice. So either we need to delete the original one or create a key pair with a different name. So let's go ahead and delete that key pair. We're going to, again, use the EC2 service to delete the key pair by name using the key name parameter here. So I'm going to go ahead and delete that. And now that the original one has been deleted, I can then call that create key pair. Again, I'm just going to replay that last create key pair command. Again, using the query parameter to grab the key material property that came back from the API call and output that as text and save it to a file called lab.pem. So let's go ahead and do that. And there we go. Now, if we do a list, you can see here is our lab.pem file. we could view that. Typically, we don't want to do a cat because a cat will leave that in our history. So if we do a VI or a vim on that, then we can view it. There we go. Now we can see that we do have the key material just like expected. Okay, so we've seen how we can use these commands, create key pair and delete key pair. We've seen how we can run create key pair to grab that key material and save it to a PIM file. And again, that is causing or having the key pair created by Amazon and given to us, right? So now that we have a key pair in there, let's go ahead and describe key pairs and get a list of the key pairs back from AWS. And there we go. You can see that it's telling us the name and the fingerprint, and that's about it. It doesn't really give us a whole lot of information about it, and that's by design. That's for security, and it's up to us to maintain a secure storage for that private key pair. Now, some people that I've talked to over the years just don't like the idea of someone else creating their private key and giving it to them. And even though Amazon says that they don't keep it, and I trust that Amazon doesn't keep the key pair, some policies and some business practices just say, you know what, we create our own private keys. We don't allow anyone else to ever have them, and we want to show an audit trail that no one else ever created or had the private key. And so in that regard, instead of having Amazon create it, we can create it and import the key. So let's take a look at doing that. First, again, just like before, we can't create two keys with the same name. So before we show importing a key, let's go ahead and delete that old key one more time. So we're going to delete that lab key pair one last time here. And if we replay the described key pairs, you'll see that we don't have any anymore. We're also going to remove the lab PIM file that we saved, because now this was created by Amazon. Now we're going to create our own and then import that into AWS. All right, so now we're clean. We don't have any key pairs anywhere. We don't have any in Amazon. We don't have any locally. So the first thing that we're going to do is use the OpenSSL to generate a 2048-bit private key pair. So let's go ahead and do that. There we go, and if we list, you can see here is our PIM file that we created. Now we know, and we have an audit trail to show that we created the private key pair. But you can also see that the permissions are fairly wide open. They would be something like 644. So we don't want anyone else to be able to read this key pair. So one of the first things that we need to do is change the permissions to be much more restrictive so that only our users can read that key pair. So let's do that. We're going to chmod 400 on that key pair to change the permissions to be more restrictive. Now, if we list that again, you can see that only my user is allowed to read, and it can't write, can't delete, and no one else can do anything. Okay, so now that we have that, let's take a look at the public key. When we use OpenSSL to generate a private key, the public key can be derived from that private key. That's how public-private key pairs work. The private key doesn't really contain the public, but the public can be mathematically derived from that private key pair. So we can use OpenSSL to show us that by using the -pub_out. Some messages come back on standard error, and we don't want those, so we're going to pipe those to dev null, and we only want to see standard out. So let's take a look at the public part of that key pair. There we go. There's the public key. When we give this to Amazon, in order for us to import that key pair, what Amazon wants is what they call the key material. And the key material is all of this here, all of this data between the begin and end lines. And not only do they want that key material, but they also want it without these new lines. You'll see here that public key pairs and private key pairs generally have new lines over here, and we want to remove those as well. So this next command, a little bit of bash magic using awk, we're going to take that public key pair that's generated by OpenSSL, and we're going to pipe it through the awk command, and this little bit of magic right here will essentially strip out the begin and end lines, and it will remove all of those new lines, right? So let's take a look at the difference, and we'll see just what this command is doing. So there we go. You can see that it has extracted the key material from the public key by removing the begin and end lines and removing the new lines. And that right there is exactly the data that we will give to Amazon. Okay, so now what we're going to do is we're going to call the import key pair. We're going to, again, call this key name lab. And here we're saying the public key material is all of the stuff that we're going to get back from this command. Now, when we're dealing with key pairs like this, these type of security things, I could assign the output of this to a variable and then use that variable in the next command. But again, that would mean that now that data is living in a place that could be found later. And by not assigning it to a variable, by passing it in directly like this, we can avoid those kinds of situations. So let's go ahead and import that key pair. And there we go. Now we've imported our own key pair, and we know that we created the private, we gave Amazon the public key pair, and no one else ever had our private key. Okay, so we can do our describe key pairs one more time. And there we go. We can see that in our dev account, we now have our lab key pair. So the thing to keep in mind at this point is that key pairs are unique per account, per region. So if we wanted to do something with this key pair in another region, we would have to import that key pair into that region. If we wanted to use this same key pair in another account, we would have to import that key pair into that other account, right? So let's do that. Let's go ahead and import this key pair again into the admin account. So I'm going to, instead of using the dev profile, I'm going to use the admin profile. So that way we have this key pair available for use in both the admin account and the dev account. Now, moving forward, we will continue to launch our EC2 instances for our development environments in our development account. But when it comes time to creating machine images or doing some other type of operational thing, like perhaps running Jenkins, then we will do that in our admin account. And so we need this key pair across those two accounts. So let's go ahead and use the same command, but using the admin profile so that we can import that same key pair into our admin account. And of course now, if I rerun the describe key pairs with the admin account, you can see now I have that key pair available there as well. And that is how we can use the AWS CLI to manage key pairs. Okay, so here we'll use AWS CloudFormation to create Amazon EC2 instance profiles. In our text editor, we have 5.3 bash commands open. Before we get into the CloudFormation steps, let's first take a look at the template that's involved, and we can find that here under Source CloudFormation Access Roles for EC2. So let's take a look at that file. CloudFormation Access Roles for EC2. Okay, so in this file, just like before, we're creating a number of resources here. The first one here is we're going to create an IAM role, and this one later on in later labs we will use this particular role to be applied to our ECS nodes, the nodes that will make up our container cluster. So we're going to, again, this is a role type. We're going to name it ECS node, and I generally like to name the role and the instance profile all the same, so I know exactly what they're being used for. And I like to name them with something that describes the function that they serve, right? In this case, the function that this instance serves is being a node in an ECS cluster, an EC2 container service cluster. So here, you can see that we have an assume role policy document that is granting the EC2 service the ability to assume a role. We're also going to apply here a managed policy to that, and this managed policy will give that particular role whatever permissions are specified in that policy. In this particular case, we're applying a policy specifically for the EC2 container service for EC2, which will allow whatever role this policy is applied to and whatever role or whatever instance this role is applied to, that will allow the EC2 instance to communicate with the ECS service. And we'll talk more about those details later on. For now, just it's good enough to understand for now that we're creating a role with an attached policy, and that's not enough. The role and the policy are ways of getting temporary credentials. We also need a way of bridging that role with the EC2 instance, and that's what an instance profile does. An instance profile tells Amazon what role is applied to that instance. And so you can see here we're creating an instance profile. We're calling it ECS node profile, and I generally like to name the instance profiles the same as the role. It just makes scripting and other things a little bit easier later on if they both use the same name. And here, we're saying what roles are being used for this profile, and it could be a list of roles. In this, we only have one, and I'm calling it ECS node. We also want an instance, we're going to be doing something later with EBS volumes. So here we're going to create another role. You can see here another role that, again, the assume role policy is allowing the EC2 service to assume this role. And we're going to create, instead of managed policies, we're going to create inline policies. So the inline policy on this role says that we want the EC2 instance to be able to manage EC2 volumes or EBS volumes. And so here we are going to allow this EC2 instance to do all actions related to volumes. This EC2 instance will be allowed to create volumes, delete volumes, describe volumes, and so on. Now, that in your particular situation, that might be too many permissions. You might want to limit that. For the sake of the lab and keeping things simple, we're just going to do some wildcards. But moving forward, I would suggest that you look at being more restrictive. We're also going to allow this EC2 instance to create snapshots and describe snapshots. And then here we are explicitly saying that this instance is never allowed to delete volumes, just to be safe. So once something is denied, it can never be allowed. So if something else, if another role was attached or another policy was attached that granted the allow delete volume, it wouldn't matter because this deny will always take precedence. And then, of course, we have our role, the EC2 volume access role. We also need a volume access instance profile, again, as a way of bridging the role with the EC2 instance. Okay, so now that we've taken a look at the template, let's go back to our commands here. And first, let's validate the template and make sure that there are no errors in there. Okay, so there you go. You can see that we don't have any parameters that we need to enter. We do have the capabilities, the IAM capabilities, because we are creating roles, which are all, if you look at all the resources, are namespace with AWS IAM, and because of that, we have to specify those IAM capabilities. So let's go ahead and create that stack. We're specifying the capabilities here on that command, -- capabilities, named IAM, capability named IAM being the capability that we need. Okay, so let's go ahead and run that one. And we will wait for that stack to complete. So while that's running, let's go ahead and wait for stack create complete by stack name, roles for EC2. And roles and instance profiles, especially considering that we only have 2 of them, should create in just a few minutes. Really shouldn't take very long at all. Again, it may take longer than what it appears like in the video. All right, so there we go. Our stack has created. And now that we've gotten that complete, let's go ahead and take a look at our stack. So we're going to run the CloudFormation describe stacks command, specifying our stack by name, and taking a look here using the query. We want to just see the stack status and output that as text. So let's run that, and this should say create complete. There we go. Now we know when it says create complete that everything is fine, that all of the resources were indeed created, there were no errors. And then, of course, we can also take a look at the resources that were created. So by running the describe stack resources on that roles for EC2, we can see a list of all of those resources. And you can see here that we've created our EC2 volume access role. We've created our volume access instance profile, our ECS node and ECS node profile. So now we can use the IAM get role commands to get some details about those 2 roles. So let's take a look there. Let's say, again, using the dev profile, IAM get role, specifying the ECS node role by name. And there we go. Now we can actually see the role policy document that says that this role gives the EC2 service the ability to assume roles. So we're essentially delegating permissions to the EC2 service, specifically for whatever instance or instances this role is applied to. And let's do the same thing for our EC2 volume access roles. There we go. So now, not only have we verified that the resources were created by CloudFormation, we have verified that they do exist within the IAM service. So if we take a look here in our CloudFormation access, you'll see that we have another template for roles for EC2 ops. So for doing operations, we might have a couple of roles. You can see here, we have a role so that we can launch an EC2 instance for the sake of automatically creating Amazon machine images. And that machine will need a specific set of permissions. In this case, not very many. It really only needs the permission to create tags. So we're going to use this template to create a role in our admin account. And so that we can use our admin account to create Amazon machine images in a centralized place and then publish those machine images out to other accounts. Okay, so let's go ahead and create that one as well. Here we're going to, again, just quickly, we'll run through these. We're going to validate that roles for EC2, and then we will create the stack for roles for EC2 ops, and all of that will be done here in the admin account. So these last few commands, we will be using the admin profile. Okay, so let's go ahead and do that. Validate that template. Everything's fine. Again, taking note of the capabilities that are required for this particular command. And noticing here, again, we are specifying those at the time we launched that particular template. So let's go ahead and create that using the create stack command of the CloudFormation service, naming that stack roles for EC2 ops. And again, we are going to wait for that to complete. And you can see here this auto completion is being done with the OhmyZSH plugin. So I have the AWS plugin for OhmyZSH. So I'm going to wait for stack create complete. I'm going to specify that by name, roles for EC2 ops. And again, because it's only one role and one instance profile, it really shouldn't take that long at all. Sometimes if our connection is slow, or sometimes Amazon may be under heavy load, the IAM service could be under heavy load, then sometimes doing these kinds of operations takes longer than others. But generally, it doesn't take very long at all. Okay, so there we go. We have our roles for EC2 ops created now in our admin account. So let's just verify that. We can describe stack resources, again, using the admin profile, describe stack resources by name, and quickly verify that indeed we have created our necessary role and necessary profile for things that are coming up in our admin account. And that is how we can use AWS CloudFormation to create and manage EC2 roles and instance profiles. Now let's practice finding Amazon machine images with the AWS CLI. Here in our text editor, we have 5.4 bash commands open. I'm going to collapse that. Now, the first thing that we want to do is take a look here that we are using the EC2 service. We're going to be calling the describe images command. And if we were to just run it like that, we would get back a really, really long list of images. And we don't really want that. We want to narrow our focus down. Here, what we want to do is say, first of all, I'm not interested in all the other public images owned by other people. Let's just look at images that are owned and provided to us by Amazon. So we're going to name Amazon as the owners here. And of course, if you wanted to look at Windows-based images, you could specify Microsoft here as the owner as well. Or you could specify your own account number. So for this first one, let's just leave Amazon as the owner. And now we can add some filters to further narrow down what we're looking for. And those filters could be, in this case, we're looking for machine images for the 64-bit architecture. We're also looking for images that are of the HVM virtualization type. We're not interested in PV virtualization, we're interested in HVM. So here, we're also going to further manipulate the data that is displayed or limit what's displayed by using a query to say, show me only the name of all of the images. I don't really want to see all the other data, but just show me the name. Okay, so let's go ahead and run that one. And we're doing this with the admin profile simply because in this particular example, we aren't launching anything into our development account, and by using the admin profile, we can avoid having to enter our MFA PIN. So by running that, sometimes this command, because there are a lot of images, that one might take a little bit longer. And so this case, you can see that we've got a very long list of machine images that match what we were looking for. And ultimately, we could use our own script to further pull out what came back from the API, but by using more filters or using the right filters, we can further limit what comes back from the API. So let's take a look at that. In this particular case, let's build on the filters that we've created. Here we're going to say, not only am I interested in 64-bit architecture and the HVM virtualization, I'm also wanting images that have an EBS root volume. I don't want to see images that are instance-based storage. I want to see instances or machine images whose root volume will be backed by an EBS volume. I also want to see images whose name begins with Amazon AMI HVN, which is Amazon Linux, and that ends with GP2, a general purpose SSD volume. So let's run that one and see what we get back. And of course you can see here that we get back a number. Here is 2016-03.3. Here is 2016-09.1. So these aren't necessarily in an order that we want. We could limit these even further. So we have done a pretty good job of narrowing things down, but we can keep going. Let's go ahead and do the same filters. You can see here in this next command, we're still looking for HVM virtualization, EBS root volume. We are looking for those same names essentially for Amazon Linux, but we want to use the query parameter to sort the images by creation date. And for every image in that array, we want to see the name of the image and the image ID, and we want to output that as a table. That will make it a whole lot easier for our human eyes to read and understand. So let's try that one. So again, describe images where the owner is Amazon and applying all of the filters that we've talked about using the query parameter to further manipulate what we're seeing. Now these should be in order, and you can see it's much easier to read and understand. So now they are in order, at least by creation date, and if they have been named in a similar way, then the name should also be in order. And you can see here that that seems to be the case. We have 03.1, 2017, 0623, and this right here would be the latest Linux, Amazon Linux machine image that matches our filters in that particular region, our default region, US East 2 in this case. So if we were to run this in another region, then we would see a list of the same names, but with different IDs. So keep in mind that an Amazon machine image is unique per region. Now we can create an Amazon machine image in one region and then copy it to other regions, but it will get a unique ID per region. Okay, so we can do the same thing, But in a case where we're programmatically looking for the latest machine image of a particular type, and there are plenty of opportunities when you might want to go out and find the latest version of Amazon Linux, the latest version of Red Hat, of Ubuntu, of Debian, and so on. And here is how we can find that latest machine image. If we take a look at this next command, we're again applying all the same filters, the same architecture, the same virtualization type. But in this case, the only key difference here is that instead of listing the image ID for all of them, we are going to use -1 here to pull off the last image ID. And so again, because we are sorting the images by creation date, we can use a -1 index to pull off the last one, output that as text, and that will give us back the latest machine image. And we know then that that machine image will have been updated by the publisher. So let's run that one and see. This should give us back the last one in the table. There we go. We can see that what we got back, 8A7, here correlates to the last one in that table. So if we wanted to find the latest official Ubuntu 16.04, we can do this command. Notice here that we are specifying this account number as the owners, and this account number correlates to Canonical as the publisher for Ubuntu images. And so here, we're doing some very similar filters, 64-bit architecture, HVM virtualization type, but down here we're looking for the name, we're looking for Ubuntu images, SSD-based HVM, we're looking for Xenial, which is 16.04 LTS, and we're going to finish that with a star because all of the other things that differentiate those updated images will come after that. So we know that the images that we're looking for begins with this particular string. And once again, we are going to sort those images by creation date and display those names in a table. And if we wanted to pull off the last one, we could just modify this query and output to use the -1 index. So let's take a look at the official Ubuntu images. And there you go. We get a long list of all of the Amazon machine images published for official Ubuntu 16.04. And this last one here would be the latest one. If we wanted to do the same thing for Debian Jessie, then we could use this again, setting the owner to the official publisher of Debian Jessie images. So let's take a look at those. And again, here we're specifying the name as being Debian Jessie, followed by the asterisk, and again sorting those images by creation date. So let's go ahead and run that one. And there we go. We get back a list of Debian Jessie, and you can see that their images are not updated nearly as often as Ubuntu. So again, one way to use this as you want to move forward in your environment is to make use of this feature of finding machine images, sorting them by creation date, by filtering by the necessary architectures, the type of root volumes, and so on, to find that latest image, and then you can go on to launch EC2 instances based on those, or you can use those to create your own custom machine images. And that's how we can use the AWS CLI to find Amazon machine images. All right, in this lab, we'll use the AWS CLI to launch Amazon EC2 instances. Here in our text editor, we have 5.5 bash commands open. The first thing that we want to do before we launch one is find and capture the latest Amazon machine image ID for Amazon Linux. In this example, again, we're going to, just like we did before, we're going to find a machine image that's published by Amazon. And in this case, again, we're looking for very similar things that we've done before: 64-bit architecture, HVM virtualization, and ultimately by using this name here, AMZN, AMI, HVM, this will give us back a list of Amazon Linux. And just like before, we're going to sort those images by creation date and pull off the last one. But this time, we're going to output that as text, save it to a bash variable, and echo that so that we can see and verify that we do indeed get something back. Okay, so let's go ahead and capture that ID. And because we're running this in our dev account, we may need to enter our MFA PIN. Sometimes if my MFA device is right there at the last 4 seconds, then I might wait for it to come back around, because sometimes I've found that if I'm too close to the PIN expiring, that by the time I type it in, it's expired. So I'm going to enter a fresh PIN here. There we go. And you can see that we did capture one, and by echoing that, we see that we do now have that latest Amazon Linux machine image ID captured. So now we can use that to run instances. And so let's take a look here. We're going to use the EC2 service to run instances, which will create new EC2 instances. We're going to specify the image ID that we just captured. We're going to use the lab key pair that we created earlier. In this case, we're going to specify the instance type as a T2 Nano, which is the least expensive machine we can run. And we're going to associate a public IP address with that. Now, I want to take note of what's missing from this command. What's missing from this command is the subnet ID. We have not specified where exactly we want this EC2 instance to be launched in our network. So if we were to run this by not specifying a subnet ID, AWS will automatically choose one for us, and in this case, Amazon will use our default VPC. The default VPC has a public subnet attached to the internet with an internet gateway and routed to and from the internet. And so by leaving off a subnet ID specification, we can know that Amazon will place this instance into our default VPC. And for the sake of this lab, that's what we want, so that we know we're going to be able to shell into this machine from the internet. Okay, so let's go ahead and launch that. Again, into our dev account using the dev profile. And just like that, we get some information back. Now, at this point, if we look at this code, you can see that the instances are pending. The state of that instance is pending. So just because we got data back doesn't mean that the instance has launched and is ready to use. It means that at this time that instance is pending and we're waiting for it to become available. Linux instances generally boot pretty fast. So while that instance is booting and becoming ready, let's first take a look at the security groups that have been applied to that instance. In this case, we're going to describe the instances, but we don't want all of the data. All we really care about are the security groups that are attached to the one instance in the one reservation. Let's go ahead and take a look at that. We'll output that as a table. And you'll see that, again, because we allowed this to be launched into the default subnet of the default VPC, and we did not specify a security group, Amazon automatically attached the default security group. And this is the ID of that default security group. Now, before we move on, I do want to take a minute to point out a couple of things about this query that we just ran. This word here, reservations, a lot of people confuse that with reserved instances, and that's not what it means. When we ran this command here, the run instances, we allowed it to default to running one instance. Had we specified a number, we could have launched 2, 3, 30, 400 instances. If we were within our account limits, we could have launched any number of instances. And so that's what this reservations means. When we use one command to launch numerous instances, in this particular context, that's what the word reservations means. So in this particular case, we've only executed that command once. And so we only have one reservation. Every time we execute this command or cause instances to be launched, we will get another reservation. So if we had launched that with 12 instances in that command, then we would have one reservation, and within that reservation, we would have 12 instances. So that's why when you're querying for, when you're doing a query here on the describe instances data, we have to not only specify instances, but we have to specify reservations as well. And so in this case, we know that we've only run it once. We know that we're only going to have one reservation. So we can specify that at 0, being the first and only one. And because we ran one instance, we only have one. And so we're specifying 0 as the first and only one. And from experience, I know having Amazon use the default subnet and the default security group, that will give us one security group. So we can use the 0 index for all 3 of those lists. Okay, so now that we've taken a look at the security groups that are applied to that instance, or at least the one default security group, before we shell into this machine, we need to open port 22 from our own IP address. I generally don't like to open port 22 from everywhere. For the sake of us logging into this as part of the lab, we want to open port 22 from our own IP address. So we need to replace this placeholder here with that security group ID. So let's go back and copy that. I'm going to copy the whole security group ID. I'm going to paste it here and replacing this whole placeholder, including the less than, greater than. We are opening port TCP port 22, and the CIDR range we're going to create as a /32, meaning one specific IP address, and we're going to use the dig command to find our IP address. I don't really know, being on someone else's network, I don't often know exactly what my public IP address is, and it could change. If you don't have a static public IP, it could change. So we're going to use this command to pull back our IP address. So let's go ahead and add that, authorize that security group to receive port 22 from our IP address. And there we go. We've done that authorization using the EC2 authorize security group ingress command. Okay, so now that we've got that, we also want to grab the public IP address. You'll notice here in that launch command, when we launched that instance, we specifically said, yes, associate a public IP address. So now we want to query for that and find the public IP address of the only instance in the only reservation that we currently have. Right? So let's go ahead and pull that public IP address. There we go. That's the public IP address of our EC2 instance. I'm going to copy that, come back here, and now we're going to shell into that. Because we specified at the time we launched it, we specified that we wanted our lab key pair that we created earlier to be used. So I'm going to SSH-I and specify that identity file. Because we're using Amazon Linux, I know that the power user is EC2-user, and I'm going to paste that IP address that I got back. Now again, if you are trying to use what's on screen here, then it probably won't work. You will need to perform these functions and use the IP address that you get back. I'm going to go ahead and shell into that machine. Yes, and there we go. The fact that we see this here, this text art, EC2, Amazon Linux, now we know that we have established a shell connection into a remote EC2 instance. And that's how we can use the AWS CLI to launch EC2 instances. Now let's talk about instance metadata service. Within EC2, there are plenty of times when we want an EC2 instance to be able to get information about itself. And we can use the instance metadata service to do that. There is a very special URL available to us, 169.254.169.254/latest/metadata. And by calling that, we will get a list of all of these different things that we can learn about that EC2 instance. Now, it is important to understand that this is available only from an EC2 instance. We're not going to get anything from this URL if we try to reach it from our local laptop. We can't get to this from outside of Amazon. We can only get to this from within an EC2 instance. And an instance can only use this to get information about itself. One instance cannot use the instance metadata service to get information about another machine. And so an instance can get information about itself. And so we can retrieve a number of things. We can retrieve the AMI ID, the machine image ID that's being used, the host name, the instance ID, the instance type, private IP addresses, both IPv4 and IPv6 if we're using that. And we can use this information during instance bootstrapping. So when we pass user data to the EC2 instance for the purpose of getting this machine up and running, doing what it's supposed to do automatically, our bootstrapping scripts can use this information for all kinds of purposes. So again, the instance metadata service is available at this particular URL. It's available from within an EC2 instance to get information about itself. Now let's use curl to get instance metadata. The first thing that we're going to do is shell into this instance. So here in our editor, we have 5.7 bash commands open. And the first thing that we want to do is, just like we did earlier, we want to capture the public IP address of the instance that we've already launched. So in an earlier lab, we launched an EC2 instance into our default subnet of the default VPC. We instructed Amazon to automatically associate a public IP address. And so we're going to run a similar command to query for that public IP address, output it as text, and then capture that as a bash variable. So let's go ahead and do that. And of course, because we're doing this in the dev account, you may need to re-enter your 6-digit PIN. Okay, so now we can echo that instance public IP. There we go. Now we know that we have that captured. So now we can use that IP to shell into that instance once again. Again, using the lab private key. There we go. Now we're back into our EC2 instance running Amazon Linux. So from here, we want to, again, use the curl command to pull back data from this very special IP address, which is only available from within an EC2 instance. And by finishing here at metadata slash, we will get back a list of various pieces of data that we can get about this EC2 instance. So let's go ahead and run that curl command and see what we can get back. So you can see here there's a long list of various types of data. The machine image ID, we can get back block device mappings that show where volumes might be mapped to on this particular EC2 instance. We can pull the host name, the instance ID, the MAC address, all kinds of information we can pull about this machine. And then, of course, we can use this information in our bootstrapping scripts. Perhaps our bootstrapping needs to reach out and grab an EBS volume and attach it. Perhaps this needs to modify route tables, or it needs to modify a call home to some sort of management server running on premises and report information about this instance to some other tracking software. So here, while we're in here, we can grab the local IPv4 if we wanted to. Here we can again use curl to grab the local IPv4 and capture that to a local variable. And by doing that, we can then echo it all on one line. So let's try that. And then, of course, if we're doing this programmatically, then we certainly don't want all of curl's verbosity to be captured in that variable either. So let's try that again, but add the -s option for silent to curl, and you'll see that now we get just the IP address rather than all of the transfer information that we don't need when we're doing something in a script. That would be the local private IP address of this EC2 instance. We could also do the same thing with the local host name. So let's do that. I'm going to replay one of the earlier commands, and here we're going to say local host name. And you can see that came back here. There's not a new line involved, it's just text, so that's why it's coming out on the same line as our command prompt. So that would be the local host name. We could do the same thing here. Let's replay an earlier one and take a look at the instance type, or excuse me, the instance ID. Let's try that. And there we go. So that's how we can programmatically gain the instance ID that we're currently on. So you can see how the instance metadata can be used for an EC2 instance to get information about itself and then use that information in later scripts. And we will see examples of that as we move forward in this class. So that is using curl to get instance metadata. Now let's use Python to create Amazon machine images. Again, in our text editor, we have 5.8 bash commands open. And before we move on, let's take a look at a particular Python script, which we have here under Source, Scripts, AMI Builder, Cassandra AMI. So I'm going to come down here and open that. I'm also going to open, whoops, I lost that. Let's make sure that we keep that open. So I have my bash commands, my Cassandra AMI, and I also want to open the user data shell script. Well, we're going to talk through these here as we go along. So in our Cassandra AMI, this is the Python script that will be used to script all of the actions necessary to launch an EC2 instance, wait for that EC2 instance to finish bootstrapping, and then create a machine image from that EC2 instance. Again, we're importing the Bodo 3, which is the Python SDK. We're importing a number of other things to be used in this script: JSON, time, OS, and sys modules. Here, because we're running this locally, we're going to be running this in our admin account, so we're using the admin profile. Now, if we were to run this in Lambda or run this on an EC2 instance, then of course we would just leave this blank and allow the profile and the Bodo session to figure out all of the credentials based on the EC2 role. So again, just keep in mind that we're only setting this profile name here because we're going to run this locally. We won't need that in EC2 or Lambda. So something very similar to what we did earlier. We want to find the latest Ubuntu 16.04. Now, that's what we're using here. I actually have an error in my comment here. Let's fix that. So you might want Debian. You might want Red Hat or CentOS. So you can use the same thing. Just make sure that you put in the right account ID for the owner and fill in the right filters for whatever it is that you happen to be looking for the image that you want to find. In this example, again, we're looking for 64-bit architecture, HVM virtualization type, EBS root volumes, and we're looking for images whose names begin with Ubuntu images HVM SSD Ubuntu Xenial 16.04. And we know that that will give us, by looking for that and sorting those by the creation date, we can find the latest Ubuntu 16.04. And so once we get that data back, we get that back as a dictionary. And so we're going to look through the images list. We're going to sort those by creation date using a Lambda here. And we want to sort those descending. And then by doing that, we can know that the latest one will be on top. It'll be the first one. So we're going to pull the image ID from that sorted list. Now what we're going to do is we're going to capture our user data script that we have here sitting alongside of our image creation script. And we're going to walk through this here as well. So we're going to come back to this user data shell script here in just a minute. We've captured that user data, and we're going to use that to pass that into our run instances command. You can see here we're passing in the contents of our user data shell script into the launch of the machine. And we're going to be also passing in the image ID that we found. We're also going to specify the EC2 AMI builder as the instance profile that we created earlier in our admin account. And so this EC2 AMI builder is a role and an instance profile that will allow this EC2 instance to tag itself. We're also going to specify a T2 medium, and T2 series are an interesting family because they are ultimately meant for bursting. And these T2 series come with enough burst credits right off the bat to sustain 100% CPU usage for about 30 minutes. So that would give us plenty of time to gain access to the full CPU of that machine before our credit balance runs out. And so the reason I've chosen a T2 medium for this case is that we essentially get the same performance as a C4 large for half the price. If I was doing some type of compute-intensive application that needed a lot of CPU all the time, then I would go for a C4. But because this particular application is bursty, it's going to run something for a few minutes and then go away. The T2 series is perfect. So we've specified our image ID, our user data. We're also specifying a tag. So we're going to specify a tag called bootstrapping with a value of pending. We're going to be looking for that later. Okay, so let's keep that in the back of our mind. As a side note, we're going to come back to that here in just a minute. This is a very important piece of what we're doing here. So now that we've launched the instance ID, we're going to capture the instance ID and then use what we call waiters to wait on that instance ID to be running. So you can see here, we're waiting for the instance to reach a running state. Once that instance is in a running state, we are going to say, all right, now the instance is bootstrapping. The next thing that we're going to want to do is wait for the bootstrapping tag that we placed earlier, notice here that we placed a bootstrapping tag at the time it was launched. The user data script internally, once the user data script has finished on that first boot, it will set the value of this tag to complete. And so we're going to wait, we're going to query, you can see here every 10 seconds, we're going to query those instance tags to look for that value, right? So as long as the value does not equal complete, then we're going to keep querying for that. And once this script sees that tag value is marked as complete, then we can continue on to create the image. And here all we need to do is say instance create image. We're going to name it Cassandra. We're going to also append the time of day in year, month, day format. And then we're also going to wait for the image state to reach a pending status. And once the image has been completed, we can then terminate the EC2 instance. So you can see here in just about 100 lines of code, we have a complete solution for automatically creating our own custom machine image based on the latest published image from a publisher that we trust. All right, so now let's take a look at the user data. What's going on during that first boot, during the bootstrapping process of that EC2 instance? So what we've given that EC2 instance as user data is a bash script, and we're going to use this bash script to install the latest version of Cassandra. In your case, you might want to use this to install and configure Cassandra or Kafka or Zookeeper or MongoDB or some specialized form of a database, some specific version of MySQL or SQL Server or something else that isn't supported on RDS. Whatever the software is, you can use this type of pattern to automatically bootstrap and create your own custom base image. In this example, we're going to, first of all, add the Oracle repository so that we can install Java later. We're going to add the Apache repository so that we can then install Cassandra. And I'll let you read through all of the fine detail of this script later. Here, we're just going to do a high-level overview. We're then going to update apt-get, and notice that we are missing the sudo. We don't need sudo because this user data script will be executed as the root user. We're going to here go ahead and pre-mark that we've accepted the Oracle licenses so that our installation of Oracle Java can move along programmatically. Otherwise, without these two lines, it would get stuck here waiting on user input. The next thing we're going to do is install Cassandra, again using the -y because this is being done automatically. No one is there to press the Y button. Once Cassandra is installed, we're then going to stop Cassandra. We're also going to, just like we did something earlier on our local machines, we're going to check to see if Python and curl are installed. If they're not, we will also have those installed. We will then install, just like we did locally, install pip, install the AWS CLI tools, and then all of this output that we're doing, all of these echoes, is just so that we can go back and look at the EC2 system log. If there was an issue, if something went wrong, we can go back and look at the EC2 system log and see at what point did it fail. We can see our echoes here and then use that to debug where this script may have gone wrong. We might also want to install the Systems Manager agent. And just in case later we want to use the Amazon EC2 Systems Manager. Now here comes the really important part. Our Python script needs a way to know that our user data has finished bootstrapping that machine. So once everything has been installed, we need that user data to tag the instance so that our Python script can see that and know that the bootstrapping process is finished and that it's now safe to create an image. Creating an image requires the machine to be shut down. And so we certainly don't want to do that prematurely. We don't want to do that before everything has been installed. Okay, so now just using instance metadata, like we saw earlier, we're going to capture the instance ID as a variable. We're also going to capture the current region, and we can get that from the availability zone here. The metadata placement availability zone will give us the AZ that it's currently in. And then from the AZ, we can derive the region. All we need to do is pull off that last letter. So the AZ might be US East 2A or 2B, and by removing that last letter, we get US East 2. And so we're going to do some bash magic here to pull off that last letter and give us the region. From there, we're going to use the AWS CLI tools that we just installed to specify the region, which is essentially the current region. And we're going to call the create tags. We're specifying that the resources we want to tag is the current instance. So this instance is tagging itself. And notice here, that same bootstrapping tag that we set earlier, we're going to reset the value of that to complete. So from here, let's go ahead in our bash commands. All we need to do here, let me change the colors of this to make it a little easier to read. We're going to execute that Python script. And again, we're doing that locally. Let's go ahead and run that. And there we go. It very quickly found the latest version of Ubuntu 16.04 and it showed us the image ID. Now it's launching that EC2 instance. And now that script, if we go back here, the script, our Python script is right here, launching and waiting for that instance to launch. So this is what's happening right now, is that we're waiting for that instance to be in an instance running state. There we go. Now it shows here that the instance ID is indeed running and instance is bootstrapping, and now it will continue to check. Every so often it will check to see if that bootstrapping tag is set to complete. And this particular script, the installation of Java and Oracle, only takes a few minutes. And there we go. You can see now, after just a little while, only took a few minutes, that our bootstrap process is now complete. Now our script is going to create the Amazon machine image. And again, our script is going to query the state of that image every 10 seconds to let us know as soon as possible when that image is ready. And then, of course, once the image is ready, it will terminate the instance. So that way we have a fully automated way of creating machine images and cleaning up after ourselves. We certainly don't want those EC2 instances hanging around, and we don't want to have to, we don't want to have to shell in to a machine and do things manually every time. That's exactly what we want to get away from. We want everything as automated as possible, and this is one of the very key things that we see in a cloud operations role is automating these kinds of things. Common tasks, let's get away from doing it manually. Let's let Amazon do it for us. Just like that, we have our latest Cassandra AMI. If you want to take this code and modify it to create your own custom base images, apply your own configurations, and of course you could apply that to Cassandra, Kafka, Mongo, you name it. It's just about limitless what you can do with something like this. Okay, so now that our image is created, let's take a look at some of those details. So here we're going to do, again, in our admin account, we're going to use the EC2 describe images command. We're going to specify the image ID. So here I'm going to copy just before the image ID placeholder here. I'm going to copy that, paste it, and then I'm going to take the AMI that my Python script gave me and get some details about that image. And there you go. You can see that our image is based on, here's our name that we added. You can see the block device mappings is our EBS root volume, which is an 8 gig general purpose SSD root volume. And now what we might want to do is share this image with another account. So again, the pattern that we're following here is that we've used our admin account as a place to create the machine image, and then we have one place from which we can publish this image out to numerous accounts. So we have one place where all of our auditing points to. That way we don't have to track down, oh, we created an image over here and we need to share it over there. We created another one over here and now we have to share it somewhere else. So instead, we have one place to go to where we know all of our machine images are created and published from. And we know that by creating it in the admin account and taking that same machine image and launching it in development, launching it in production, we know that we're starting from the same place. That development and production are both using the same exact machine image. So before we can do that, we have to share that image from one account to another. We can do that by using the EC2 modify image attribute command, specifying the image by ID, and notice here what we're going to add is a launch permission, which is a JSON policy document. Now here, I know this seems perhaps counterintuitive. The user ID in this case is actually an account ID. I'm not sure why they decided to name it like that, but ultimately what we're going to put here is our development account ID. So here what I want you to do is open our accounts text file that we created earlier. I'm going to copy my development account ID. You will copy your development account ID. Again, if you try to use what's on the screen, it probably won't work. Okay, I'm going to come back to my bash commands, and I'm going to paste my development account ID. I'm also going to go back here to my terminal and copy that machine image ID that I got back from my Python script. You will do the same thing. We're going to paste that here. By modifying that image attribute and adding that launch permission, this will then give our development account the permission to use this image. Let's go ahead and copy that, execute that command. It gave us no error, so we know that that command ran successfully. And now if we wanted to, we could verify that the image is indeed shared with the development account. So once again, let's paste the image ID that we got back. I'll paste mine, you'll paste yours. We're going to describe the image attribute, specifying the image ID and the attribute that we want to describe. And there we go. You can see that our image ID does indeed list our development account as having launch permissions. Now, from here, we could use our dev profile to query machine images in our dev account to ensure that the dev account can actually see that. So let's try that. AWS profile dev, using our dev profile so that we are acting from within our development account. We're going to say EC2 describe images. Again, all of that auto-completion is being done by the AWS CLI plugin for OhmyZSH. Now, if I were to run this command at this point, I would get back way too much information. I want to limit it by owners. I'm going to use the owners parameter and specify our admin account. Again, I'm acting from the development account, and I want to say, hey, show me all the images that are owned by the admin account. The development account only has permissions to use it. It doesn't own it. The admin account still owns the image. So I'm going to go back here to my accounts text file, and I'm going to copy my admin account number. You will do the same thing and paste your admin account number there. And there we go. We get back. You can see that our development account does indeed have the ability to list that. And from there, if we wanted to run Cassandra from within our development account, we can use that machine image. So that is how we can use the AWS CLI tools and Python to create and share Amazon machine images. In this lab, we're going to use AWS CloudFormation to create an autoscaling group. Now, for this particular lab, because we want a cluster of machines to house our microservices, we want to put those in an autoscaling group so that in case a machine fails, the autoscaling group will automatically replace that machine. We also want to set ourselves up so that in the future, if we do need to scale based on demand, we can leverage autoscaling group policies to trigger the scaling and adding or removing machines based on demand. So we're going to create an autoscaling group that leverages all three availability zones in the Ohio region. We're going to leverage US East 2A, 2B, and 2C. We're going to create this autoscaling group in our private subnets so that the machines that get launched into this autoscaling group remain private and protected from being accessed from the internet. Once we set our desired capacity for this autoscaling group, we're going to start off as 0, but later we will turn the autoscaling group up to 3 machines. We don't need to create the EC2 instances. The autoscaling group itself will create these machines. And when we specify that we want 3 machines, the autoscaling group will create those 3. It will do its best to achieve a balance between the number of machines that we want and the availability zone. So in this example, in this particular lab, our autoscaling group uses all 3 availability zones. Later, when we go to turn up the desired capacity, it will place a machine per AZ and attempt to maintain a balance. Now, aside from the autoscaling group, we are also going to create security group for our EC2 instances. We are going to inform the autoscaling group that every time a machine gets launched, it should have a particular security group applied. And of course, we only need to create the security group once, and then that same security group will be applied to each EC2 instance that gets launched. With our editor, we have 5.9 bash commands open. Let's go ahead and collapse that real quick and take a look here. Now, before we move forward with these commands, let's first take a look at the template. The template that we're going to be creating from is the EC2 Autoscaling ECS template found here in CloudFormation Compute. So let's go ahead and open that. CloudFormation Compute EC2 Autoscaling. And let's take a look at what's happening in this template. So earlier, we've created a VPC specifically for housing our container services cluster. And we're going to be referencing that network stack with this template, just like we did earlier. We're also going to hold a place for the machine image, the key name that we want to use for our EC2 instances that will be launched into this autoscaling group. We're also going to collect a parameter for the number of nodes. This will default to 0 nodes. The first thing that we're going to create in this template is a launch configuration. A launch configuration is a blueprint for the type of machine that gets launched. And you can see here that we specify that we want EBS optimized, we want a particular instance profile. You recall that we created the ECS node instance profile earlier, which will allow these EC2 instances to communicate with the EC2 container service. And we'll talk more about that later on. We're going to reference the Amazon machine image ID that we pass in as a parameter. We're going to set this to run an M4 large, pass in the key name. We're going to reference a security group that we are creating here in this template. For purposes like this, I generally like to create a security group per function. Rather than having generic security groups that have a whole bunch of rules and are applied to a bunch of different things, I like to have very targeted security groups. And so here, I want a security group specifically for the machines that are in this autoscaling group because they all serve the same purpose. If I were to create another autoscaling group for another purpose, those would get their own security group. What I want to draw your attention to here and spend a moment talking about is the user data. So because the launch configuration ultimately controls what machine and what that machine looks like, this is where we can pass in user data so that as autoscaling creates new machines, it passes in the user data that we put here. Now, user data within CloudFormation is not necessarily the easiest to read because ultimately user data has to be base64 encoded. So we're using the base64 intrinsic function to do that. And because we within YAML or JSON, we don't have a way of putting multiple lines all together in one string. Because of the nature of the template, we have to use the join function in order to split those out into multiple lines to make this template readable. Otherwise, if we just did the /ns on our own, the template would be very difficult to read. If you find that you're adding user data more than one line, then I would encourage you to look at a different way of doing that. In this case, the only thing that we're doing is creating a bash script, and it has one line. It's setting the ECS cluster parameter to the stack name that we pass in, and it's going to output that to the ecs.config file. And that will allow these machines to again register themselves with the right ECS cluster that we will create later. If you find that your user data here within your launch config or within a CloudFormation template becomes longer than this, then one thing that you could do here is store that longer user data script on S3 and then use curl or the AWS CLI tools to pull that script down from S3 and then pipe it to bash. That way, the user data here is essentially one line. The longer script is stored in S3 in a place and form that is easier to read and manage. So we're also going to specify the autoscaling group itself. We're referencing the number of nodes that we passed in. We're going to reference the launch configuration that we created just in the lines immediately before. We're going to also specify that the number of nodes parameter we use not just for desired capacity, but also for the max and the minimum size. What we're saying autoscaling is that we want exactly this many instances, no more, no less. We're going to, for the VPC zone identifier, this is a list of subnets that we want this autoscaling group to use. And we know that in our network that we've created specifically for this purpose, we have 3 subnets designated for nodes to be used in our container services cluster. So we're going to import those, just like we've done earlier. We're importing those IDs that our network CloudFormation stack exported. We're going to add a tag called cluster, and we're going to use the stack name Whatever it is that we named this particular stack, we're going to use that as the cluster tag. Here's our security group. We're going to be referencing the VPC ID that we're importing. We're going to allow that security group to make outbound connections. Here's our egress rule. We're going to allow it to receive NTP traffic from anywhere. And then we're also going to allow it to receive all traffic or all ephemeral ports from the local VPC range. So you'll notice here that we're adding this to the security group that we create in this stack by using the reference. We're importing that VPC CIDR, and we're saying that this machine is allowed to receive all ephemeral port traffic as long as it originated from within this VPC. So now that we've taken a look at our template, let's go ahead, and the first thing that we want to do is let's validate that template. And here, instead of, we're going to use the query parameter to control the output of what comes back from that template. We're going to make the parameter list a little bit easier to read. All right, so let's go ahead and run that one and validate that template. It showed us no errors. It showed us a list of parameters, the key name, the network stack, the AMI, and the number of nodes. Those are the 4 things that we need to specify when we create the CloudFormation stack. The next thing that we want to do is we're going to set our stack name as a variable. In this case, because we're running in this is for a development environment in the Ohio region, I'm going to call this stack Microservices Dev Ohio. That way later, if I see a lot of things, if I'm looking at things across numerous accounts, numerous environments, I can know the differences between a cluster for development, a cluster for production. I can spot the differences between a cluster in Ohio versus a cluster in Virginia or Oregon or Europe. Again, feel free to adopt this naming scheme or find a naming scheme that works for you in your particular business. Now, the reason I'm doing this is so that I'm showing you how you can write scripts later, scripts that are fully automated rather than going through them manually. So let's go ahead and set our stack name as a bash variable. We can echo that to make sure that we have it captured. And now we're going to use that stack name to create this CloudFormation stack. Again, we're doing that in our development account, pointing to our right template, and we're specifying all the parameters that are necessary. We're specifying our microservices network that we created earlier. We're going to capture an image ID and use that. We're setting the key name as the lab, and here, notice that we're setting the number of nodes to 0. Right now, all we're interested in is creating the autoscaling group itself. We don't really need any instances in there yet. We still have more work to do before we're ready for instances to actually be launched. So for now, we're just going to leave the number of nodes at 0 and suffice to have just an autoscaling group with no instances yet. We'll come back and change this value later. So let's go ahead and capture that image ID. Here, just like we did before, we're going to filter based on Amazon images. We're looking for, in this case, we're not just looking for Amazon Linux, we're looking for Amazon ECS optimized. This is a very trimmed down version of Amazon Linux, very geared towards running containers, Docker containers, with the EC2 container service. All right, and again, we're just like we did before, we're going to sort by creation date and pull off the last one. So let's go ahead and capture that image ID. And because of our dev account, we need to put in our MFA pin, 804202, and we can echo that image ID to know that we got one back. Now that we have our image ID and our stack name, let's go ahead and not only create the stack, but we're going to create and wait for it to complete all at once. And for anyone who might not be familiar with Bash, these slashes indicate a new line so that we can get away with having one command have a series of new lines within that one command. Okay, so I'm going to copy all of that. There we go. Now you can see that we have an ARN back for that particular stack, and now we'll just wait for that stack to complete. If we didn't want to wait, now we know that what's running right now, the second command, the wait for stack create complete command is what's running right now. If we wanted to, we could stop that just by hitting Control-C, and we could do a describe stack events again. We could do AWS, again, use the dev profile, the CloudFormation service, describe stack events, and I think we have that in our history that we've done that before. So there we go. I'm going to essentially replay a describe stack events, but this time I want to go back and change the name of the stack that I'm interested in. Here, it was microservices dev Ohio is the name of the stack that I want to take a look at. So I'm going to hit return. Whoops, I got a misspelling in there. There we go. Try that again. There you go. You can see that if instead of just sitting around waiting for it, we could run this command and see an ongoing list of events within that stack. And now we can see that our security group, our launch configuration, security group egress rules, autoscaling group, all of those things finished creating successfully. There's nothing in this list that indicates an error or that anything failed. And then this last one here, microservices dev Ohio create complete, shows us that our autoscaling group and all of those resources in that stack finished creating. Now we can also describe the stack resources. So let's go ahead here. We're going to use the describe stack resources to take a look at all of those resources and what their statuses are in a table. So let's go ahead and run that one. And there we go. We get a very much quicker snapshot of exactly what state all of those resources are in. Our launch config, autoscaling group, security group, and everything else has finished creating. So that's how we can use AWS CLI and AWS CloudFormation to create autoscaling groups. Now let's review AWS Lambda. AWS Lambda gives us access to what we could call serverless infrastructure. Serverless meaning that we don't have, as an organization, we don't have servers that we have to worry about. There are no servers for us to create, no servers for us to manage. AWS is managing all of that. Of course, we know that behind the scenes there is a server somewhere running our code, but when we say serverless, we're talking about from our perspective. There is no servers for us to manage. All we really have to do are upload our functions, invoke those functions in some way, and then we pay for the compute time. Compute time according to how much memory our function uses. The longer it goes, the more memory it uses, then the more we pay. And we are billed per 100 milliseconds. Now we can create functions in a couple of different ways. We could use the inline editor if we just have one file that we're editing. Otherwise, if our function requires a number of external dependencies, then we would want to zip all of those dependencies and then we would upload a zip file. We could upload that zip file directly to Lambda. We could upload it to S3 and then point Lambda to S3. Now, when it comes to invoking functions, invoking means that we are causing that function to execute, and we could do that manually through the SDKs or the CLIs. We could do it, we could use events. Events could come from S3. An object being uploaded to S3 would generate an event, and that event could then cause Lambda to run, and Lambda could then do something with that object that was uploaded. We could have scheduled events so that Lambda runs every so often according to potentially cron format. So perhaps things that we generally used cron for, we could use Lambda for by creating scheduled events. We can trigger or invoke Lambda functions from a number of different places. Events can come from a number of different AWS services. Events could come from S3. So as objects are uploaded to an S3 bucket, we could have events fire and trigger Lambda to then do something with that object. We could have CloudWatch logs trigger Lambda. We could have DynamoDB streams trigger Lambda. We could have Kinesis streams, Amazon Cognito events. We could have the API gateway and the simple notification service all send their events to Lambda and have Lambda respond accordingly to whatever the case may be. And so using this ecosystem, we get an event-driven ecosystem. We get the ability to write our code, have Amazon handle the deployment and the execution of that code, handle all of the underlying hardware and software necessary to get that code to run, and we get to focus on writing our code. And by using all of these different services and using events, again, we have that very powerful, very flexible, event-driven ecosystem that allows us to write asynchronous applications. In this lab, we'll use AWS Lambda to clean up our environment. So here in our text editor, 5.11, we have our bash commands open. Before we get too far into this, I do want to open a couple of other things. I want to open our CloudFormation template and a Python script that we will pass on to Lambda. So we're going to open here under CloudFormation Compute our Lambda cleanup script. We're also going to come down here to Scripts, Lambda, and open our cleanup Python script. What we're going to be doing here is creating a Python script that will be run within AWS Lambda. And we will schedule that Lambda function to run every 24 hours. So things that we used to do with cron, we can now do with Lambda because we can schedule Lambda. So long as our procedure runs within the limits of Lambda, within the memory constraints and the time constraints. Remember that currently, at least as of the time of this video, Lambda has a maximum execution time of 5 minutes. So if our scripts can be performed within that, then we could very easily move things that we used to do in cron to AWS Lambda. So first, let's take a look at our Python script, the script that will be doing the bulk of the work. So again, we are importing our Boto 3 Python SDK and a few other modules to help us along the way. Now here, if we were running this script locally, we wouldn't need this particular function. Because we're giving this to Lambda, when Lambda invokes this function, Lambda will load our cleanup.py script as a module and then look for a handler within there. We tell Python the name of that handler function. So we're going to create a function here called handle cleanup, and we will be using that later when we configure the Lambda function. So what we're going to do is create an EC2 client. We're going to use that client to describe instances. And in this example, what we're looking for are instances that are tagged with the environment tag, and we're specifically looking for instances that are tagged either as a dev instance or a sandbox instance. So in a cloud operations role, you are generally concerned about saving money, keeping costs down, not only gaining all of the flexibility and agility and time to market advantages that we get with AWS, but we also want to capitalize on the cost savings advantages. And one way to do that is to turn machines off when we don't need them. So dev environments and sandbox environments are really great examples of machines that don't necessarily need to be running. Sandbox environments, in this example, we're going to find machines that are tagged as a sandbox. We're going to terminate those, and we're going to find machines that are tagged as development environments, and we're going to stop those so that every morning, perhaps we start all of the dev machines, and then in the evening, we stop them, and in the evening, we terminate all of the sandbox environments. That way, we ensure that every day, we aren't having a number of machines running when we don't really need them to be. So again, we're looking for instances that have a particular environment tag. We're also looking for them to be in a running state. We're not interested in stopping machines that have already been stopped, or terminating machines that have been stopped, or are pending. We're looking for machines that are currently running. We're then going to gather those instance IDs in a couple of lists. So remember that every time we launch EC2 instances, no matter how many instances that are launched at any one time, the fact that we launched a group of instances creates what we call a reservation, not to be confused with reserved instances. That's something else. So what we get back from that describe instances command is a list of reservations in which each contains a list of instances. So we're going to iterate over those, and what we're looking for, we're going to find the tag where the tag equals environment. So we're looking for that environment tag, and here we're going to, the tag is either of a value of dev or a value of instances, and we're going to map that value of that tag. Notice here, we're mapping that value here to the instances dictionary up here. So the value of the tag will be dev, which will go here. If the value of this tag is sandbox, then we'll go here. All right, so that's our programmatic mapping, our dynamic mapping. We're going to use that to append the instance ID to that list. Then we can look, if we have a number of machines in our dev environment, then we can stop those instances all at once. We don't have to stop each one individually. We can stop all of them at once. That's why we're collecting a list of IDs, so that we can pass all of those IDs at once and stop all of the instances in one call. We're going to do the same thing down here by looking at the length of our sandbox collection or list. And for the ones that were tagged as a sandbox, we're going to terminate those instances by calling the client terminate instance, and again, passing in that list of instance IDs that belong to the sandbox environment. Okay, so that is the code that we're going to be passing to Lambda. Here, let's take a look at the CloudFormation template that we will use to create our Lambda function. The first thing that we need is a Lambda execution role. And this role gives our Lambda function the permissions it needs to actually execute. We're going to pass it a couple of different policies. So again, we're trusting the Lambda service to assume this role and act on our behalf. We're going to give it the ability This is a stock policy that gives it the ability to read and write to CloudWatch logs, gives it the ability to read and write to S3. Down here, we're going to give some inline policies that allows this particular function, not the Lambda service as a whole, but just this one function. We're going to allow it to describe EC2 instances so that it can perform that call within the function, within the Lambda code. We're then going to allow this Lambda function to stop EC2 instances only under the condition that they contain an environment tag with a value of dev. Now we're going to allow this Lambda function to terminate instances under the condition that its environment tag is set to sandbox. So through the IAM policies that we grant to this Lambda function, that's how we can tighten security around our function. If somehow our function is compromised, let's say the code were to be changed somehow and changed to something perhaps either accidental or nefarious, then through the IAM policy, we would prevent the wrong resources from being terminated, right? So this is a perfect example of security in layers, one of the architectural best practices that we should be adhering to. So we've got our role for the execution, we've got our policies, managed policies and inline policies attached. Now, here we are creating our Lambda cleanup function. This here is the logical ID within the CloudFormation stack. And of course, this is of type Lambda function. You can see we're going to point Lambda or point CloudFormation to S3 and say that we can find our code here in this particular bucket at this particular key. We're naming our function. We're also going to specify a handler. So the file, you remember back here, we have a file called cleanup.py, which is here would be considered the module name. And then we are referencing that handle cleanup function name that we defined within our Python script. So that is the handler that we need to give to Lambda. We're setting 128 megs worth of memory, which is plenty for this particular function. We're specifying the role as the Lambda cleanup execution role that we created, again, using the getAttribute intrinsic function to pull the ARN attribute, setting the Python 2.7 as the runtime with a 5-minute timeout. Not only do we want to create the Lambda function, but we also want to regularly execute this every so often. In this example, we are running this function every 24 hours. You can see here we're using the events service to create an event rule that executes every 24 hours. The target of this event rule is our Lambda function. So we're again using the getAttribute function to pull the ARN of our Lambda function. And then down here, in order for the events service to have permission to invoke our function, we are creating an invoke permission. You can see here this is a Lambda permission, and we are giving the events service the ability to invoke Lambda functions. So that's all that's happening within our CloudFormation template. Creating a Lambda function, giving it the necessary permissions, and scheduling the event service to automatically trigger that function every 24 hours. Okay? Before we create this function and manually execute that function, let's go ahead and launch a few instances into a dev and sandbox environment just to give that function something to do. Okay, so first of all, just like we've done earlier, we're going to capture an image ID, essentially the latest version of Amazon Linux. So let's go ahead and do that, capture that image ID. We may need to enter our PIN. There we go. And now if we echo that, there we go. Now we have that image ID captured. We can use that to execute the run instances command, passing in that image ID. We're going to launch 3 T2 nanos. And here you can see we're going to specify the tag specifications. We're going to set the environment tag to sandbox on 3 of them. We're going to set the environment to dev on another 3. So let's go ahead and launch 3 instances in the sandbox environment. We're going to replay that and change that value to dev and launch 3 more in the dev environment. Now, before we create our Lambda function, we need to zip our Lambda script into a zip file and then upload that to S3 so that CloudFormation can pull it from S3. Right? So we're going to zip with the -J so that what we really don't want is these directories in the zip file. We want our script to be right there at the root of that zip file. So I'm going to zip that, and if I list that folder, you will see there is my zip file. Let's go ahead and sync that to S3, again excluding the configs folder. We'll go ahead and do that, and you'll see that it's going to upload that zip file. That was the one that changed. Okay, so now that we have everything in place, as far as our code is concerned, our code is on S3. Let's validate that Lambda cleanup template. Okay, no errors, listing the capabilities that are required. Let's go ahead and again call the CloudFormation service to create a stack. This time we're going to name the stack Lambda Cleanup, pointing to our template and specifying the capabilities that we need. Let's go ahead and execute that. There we go. So now we've created our stack, Lambda Cleanup. And we're going to wait for that to finish. We're calling the CloudFormation service. We're going to, again, wait for stack create complete, calling it by name, Lambda Cleanup. And you can see there that I had just a little bit of a misspelling. That's okay, I can easily fix that. And you can see if you do misspell something, then the AWS CLI tools are fairly smart. They had a pretty good idea of what I meant, so it's giving me a reminder there that, hey, perhaps this is what you were going for. So we'll go ahead and wait for that CloudFormation stack to create. And there we go. Our stack is finished creating. Now we can use the Lambda service and call the list functions command to see that our Lambda function is there. And there we go. There's our Lambda cleanup function specifying the handler that we created. You can see the role that we had created for it. Okay. So now from here we could either just sit back and wait for the events service to automatically trigger this function, but let's go ahead and invoke it manually and see what happens. Here we're going to use the Lambda service to invoke this function, calling it by name. Here we're going to say the invocation type is an event, just like it would receive from the event service. And here we need an output file. Whether or not we get anything back, we still have to specify a file for output. So I'm going to go ahead and execute that. And you can see status code 202 means that it's essentially pending that this is an asynchronous operation. So now the Lambda function is actually executing. And now, if we describe instances, we should see that some instances are either in a shutting down state or a terminating state, perhaps even already terminated or already stopped. So we should see that. Let's go ahead and describe instances in the dev account, and we will see. Let's go back here and look. Here's a few instances. Let's see here. Quite a bit of information that we get, and what we're looking for is the state. Here you go. You can see that one is stopped, so that clearly was a dev instance. If we look for the tags in that one, here we go. There's environment dev. So that dev instance has been put into a stop state by our Lambda function. And if we scroll back far enough, we will see that some would have been put into a terminated state because they were tagged as sandbox. Okay, so that's one way that you can use Lambda and Python to keep your environments clean. One last note here is that I have purposely left this off. I've left a challenge for you to take what we've learned so far and to make the output of that command easier to read. So there we go. That's how we can use AWS CloudFormation and Lambda and Python all together to keep our environments clean and keep costs down. Now let's review elastic load balancing. With elastic load balancing, when we create an elastic load balancer, from our perspective, it's one device. We know under the hood, AWS will manage the creation of nodes. Generally, when we use the elastic load balancer, we're going to specify that it use at least 2 subnets, 1 per availability zone for the sake of high availability. We want to answer that question. What happens when an EC2 instance fails? If an EC2 instance fails, we have another one. If an entire availability zone fails, we have another one. So by leveraging multiple availability zones, we gain higher availability, we gain fault tolerance. So again, we need a network footprint for our load balancer, and we need a way for our load balancer to have EC2 instances registered behind it. Now, the load balancer itself is inherently highly available and fault tolerant. As a service, AWS is managing the underlying nodes that make up the elastic load balancer. You know, it does span, it is a regional service. We can use every availability zone. It gives us a DNS endpoint. The way that we send our users to it, the way that we point traffic to the load balancer is to provide that DNS endpoint. It's very important that we don't rely on the IP address. I did that once. In the very early days of AWS, I did a host lookup on the DNS name, and I used that IP address as the A record for my root domain. And then the next day, someone said, "Hey, what's going on with your website?" When I looked, I saw someone else's website on my domain. Took me a couple of hours of hair pulling and documentation reading, and the documentation said, don't do what you just did. Don't use the IP address in that way. Always point people to the DNS endpoint, because the IP addresses of the underlying nodes come and go. They are ultimately transient. And so ultimately, we either use CNAMEs for our own subdomains, or if we want to point our root domain to the load balancer, we use Route 53 alias records to do that. We don't rely on the IP address. Now, When it comes to what you pay for, typically what I say is don't, especially if you are looking to study for a certification, don't worry about remembering dollar amounts. Dollar amounts change. There are no questions on the exams regarding dollar amounts. It's important that we understand what we pay for. In the case of a load balancer, we are going to pay an hourly fee for the load balancer itself. We are also going to pay for bandwidth that passes through the load balancer. Another really important, and it's not so much that it's hidden, but it's one of those things that can be easily overlooked. So I have seen companies be surprised at how much money they pay for cross-zone traffic. Cross-zone traffic is where if you have, let's say a load balancer node in US East 2A receives the initial incoming request. Cross-zone traffic says that the load balancer could send that request to another zone, to an EC2 instance in another zone. So that's cross-zone traffic, and you do pay for that. So keep that in mind. Elastic load balancers come in a couple of different flavors. We have the internet-facing and internal schemes. They are functionally identical. The only difference is that an internet-facing load balancer will give us, the DNS resolution will give us public IP addresses. For the internal scheme, DNS resolution will give us private IP addresses. And that's really the only difference. If we want a load balancer to handle public traffic coming in from the internet, of course we use an internet-facing. And if we wanted to keep a load balancer private for the sake of some internal API, as an example, then we would use an internal load balancer. A load balancer requires listeners. So listeners are how we can configure the load balancer to listen on one port to receive traffic on, say, port 80, and then forward that to backend instances on some other protocol and some other port. We could receive on 443 using HTTPS. We could then forward to port 8080 using HTTP. We can also receive and forward straight TCP traffic or SSL traffic as well. Not necessarily, we aren't limited to just HTTP and HTTPS. The load balancer, we can also configure health checks so that the load balancer will only send traffic to instances that it considers healthy. When we configure an HTTP health check, then that health check will need to send an HTTP 200 response, and then if it ever stops sending that response, the load balancer simply says, hey, that machine is no longer healthy, and I'm going to stop sending traffic to it. If we are using the Elastic Load Balancer in conjunction with autoscaling, then in the case where an instance is considered to be unhealthy, the load balancer can then tell the autoscaling group that the machine is unhealthy and allow autoscaling to replace it. So keep in mind that the load balancer simply sends traffic to backend instances or not. Autoscaling is responsible for replacing unhealthy machines. And then, of course, in order for our application on EC2 to receive traffic from a load balancer, we have to register those instances behind that load balancer. If we aren't using autoscaling, then we are responsible for registering the instances. We could do that programmatically. If we are using autoscaling, when the machine comes up, when a new instance is launched, the autoscaling service will then register that instance behind that ELB for us. Now, within the Elastic Load Balancing service, we have two different types of load balancers we can choose from. We have the classic load balancer, which operates at layer 4. That is only considering the port. We receive on one port, let's say port 80, and then we forward to another port, and that's it. We get fixed port mapping. And so it's fairly limited. If we wanted to support multiple domains, then we would essentially need multiple load balancers. If we wanted to do something more advanced, especially if we want to support containerized services, then we can use an application load balancer. An application load balancer can load balance on layer 7. Layer 7 is the content layer. And so with layer 7, we can do both host name and path-based routing. We could say one host goes to these instances, another host goes to another instance or group of instances. We could say that /users goes to one place, /videos, /articles, /billing goes to some other place. We also get access to dynamic port mapping. What that means is that each instance behind that load balancer could be using a different port. That's not possible with the classic load balancer. With classic load balancing and fixed port mapping, every instance that's registered behind that load balancer has to use the same port. With the application load balancer, dynamic port mapping says that each instance could use a different port. That right there becomes key to managing containerized services behind a load balancer. In this lab, we will use AWS CloudFormation to create an elastic load balancer. So again, in this lab, we're going to create an elastic load balancer. We want that elastic load balancer to have a network footprint in all 3 of our public subnets because we want the load balancer to communicate directly with the internet. We want internet traffic to be able to come into the load balancer. And so in order for the load balancer to then communicate with the internet and for the load balancer to communicate to our backend instances, it needs a network footprint. And so we're going to give it a network footprint within our public DMZ subnets. We also want a security group for the load balancer. So we're also going to create that security group as a part of this lab. That way we can control access to the load balancer. Ultimately, we only want the load balancer to receive HTTP and HTTP traffic. So we only need ports 80 and 443 open, and those are the ports that we're going to open using the security group. We have our 513 bash commands open. Let me change the colors there. We're also going to be taking a look at the ELB for microservices template. So let's go ahead and open that. That's going to be in CloudFormation load balancing ELB for microservices. So CloudFormation load balancing. We'll open this template. Within this template, we will use this to create our load balancer. Here, we're just like we've done before in earlier stacks, using cross-stack references, we're going to be using the network stack that we created earlier because this particular load balancer still needs a network footprint just like we've talked about. So we're going to reference that network stack. We're also going to pull in a name. So this particular template, we could use this to deploy this template in development, in production, in multiple regions, and every time we get the same exact thing. And by accepting a name parameter, we can control the name for different accounts or for different regions, but still know that the underlying resources will be built in the same exact way. So here we're creating, again, an application load balancer. And you'll notice here, we can tell that by this here says Elastic Load Balancing V2. So Elastic Load Balancing V2 indicates that we're creating an application load balancer rather than a classic load balancer. So here we want a load balancer that can operate at layer 7. We're passing in the name parameter, and here we're creating an internet-facing Elastic Load Balancer. We want the DNS name for this to return a public IP address. We're going to add the 3 public subnets that we exported from our network stack. We're also going to reference the security group that we're also creating here in this template, adding some tags. Here's the security group that we're creating specifically for the load balancer. Our EC2 instances in our autoscaling group already have their own security group. Here we're creating one for the load balancer. We're going to pull in the stack name, whatever it is that we call this stack, we will also use for the group name. Now, you might decide to name your security group something else, and that's totally up to you. This is generally a pattern that I follow. You're welcome to adopt it, or what I would really encourage you to do is explore other things that might even work better for you in your particular use case. Again, pulling in, importing the VPC ID from our cross-stack reference. We're going to add some security group rules to that security group, allowing all traffic to leave. We're going to allow this security group for the ALB to receive on port 80 from the anywhere. We're going to allow it to receive on port 443. And now what we need is what we call a listener. We have to configure the load balancer to listen on one port and forward to another port to another group of instances. So we are here creating a listener referencing the ALB for microservices that we're also creating here. Here we're saying that this listener should forward requests to a particular target group. In this case, we're going to be ultimately later on creating a billing microservice. And we want here, just for now, we will have this target group, the default forwarding target group be for our billing microservices service. Now we're going to create a target group. We're going to call it microservices billing. Down here, we're specifying that the VPC belongs to our network that we've created, and the purpose of this target group is for microservices billing. As we go and add more services, we will come back to this template and just add more target groups. Essentially, the pattern is that when we're using an application load balancer, that every service will get its own target group. It will also get its own listener rule. We're going to create a listener rule that says we will forward to that target group, microservices billing, any paths, we're using path-based routing, when we see any path starting with /billing/. So this particular path will always forward to our billing microservice. You can see here we're correlating that to the listener for that we created just a few lines before. So that's what's happening in our template. Let's go ahead and validate that template. And you can see we're getting back our parameters, so everything is fine. We know our template is okay, so let's go ahead and, again, in the dev, we're doing this in the dev account. We're going to create this stack, and here we're going to call this Microservices Dev Ohio ELB. So we know that this is an elastic load balancer for our microservices development environment in the Ohio region. And back here, we're passing in all of the parameters that particular template needs. Microservices Dev Ohio as the ELB name. And here we're going to also wait. So we're going to create, I'm going to copy that whole line. We're going to create the stack and wait for it to finish. So I do want you to notice that the stack name is Microservices Dev Ohio ELB. That's so that when we look through our CloudFormation stacks, we can see we have one for our ECS cluster, for our autoscaling group. We have another for the load balancer, and we can tell those apart. You can't have two stacks with the same name. But you can see here that the name that we used for the load balancer is Microservices Dev Ohio. So there's two different names, one for the CloudFormation stack and one for the load balancer itself. So we'll just wait for this to finish. All right, there we go. Our Microservices Dev Ohio ELB stack has finished creating. Now, of course, we can describe the stack events, building out a custom output. Notice these curly braces here. We're going to build out custom output and put that into a table so that we can make that a bit easier to read. So let's take a look at the events that happened. There you go. You can see that all of our resources created, our ALB, the application load balancer, and its security groups and all of its entries, the listeners and listener rules, and ultimately this is the stack itself finished creating, and this status shows that it all went without errors. Let's take a look at the stack resources. Again, specifying the Microservices Dev Ohio ELB as the stack name. Further manipulating that data using a query parameter. So let's go ahead and run that one. All is well with our ALB. It has been created in the right network, the same network as our autoscaling group, and we will revisit that here in a little bit. So that is how we can use the CLI tools in CloudFormation to create load balancers. Amazon Elastic Block Store gives us a highly durable and performant, persistent disk-based storage with little operational overhead. In this lesson, we review and perform a few common tasks, such as creating volumes, creating snapshots, and cleaning up volumes no longer in use. Now let's review Amazon Elastic Block Store. With Amazon EBS, what we gain by using that service is durability in our data. Some EC2 instance types come with storage already built in, but those storage devices are ephemeral. If we want our data to live on even when the EC2 instance fails, then we can use EBS. And so one of the great features of EBS is that the data is independent from the EC2 instance. And we get that by connecting that EBS volume to the EC2 instance over the network. Now, I do want to point out that even though it is connected over the network, it is different than typical network-attached storage. With typical network-attached storage, when we think of that, we think of NFS, and in those typical solutions, it would be possible to connect one volume to multiple machines, but EBS doesn't work that way. With EBS, we can only attach one volume to one EC2 instance at a time. We cannot attach one volume to multiple instances at a time. We can, however, attach multiple volumes to one instance simultaneously. And we can, if we wanted to, we could detach them and reattach them to other machines. That ability right there, the ability to detach from one machine and reattach to another machine, has saved my life a number of times. Volumes can be encrypted, and we can do that at the native level. EBS itself can handle the encryption. And of course, if we wanted to, we could encrypt at the operating system and application levels if we wanted to. Multiple volumes can be used in RAID or a logical volume manager if you want to use those types of systems. It's also important to remember that EBS volumes do exist in a single availability zone. Within that one availability zone, the EBS volume, the data is replicated across numerous devices, but it's only available within that one AZ. And so If you want to connect an EBS volume that's in one AZ, the EC2 instance has to be in the same availability zone. And then, of course, we can take snapshots. Snapshots are essentially a bit-for-bit copy of all of the data that has changed since the last snapshot. So the initial snapshot is the full backup. Subsequent snapshots are incremental. They record deltas. And of course, what we pay for is provisioned storage. So keep that in mind. If you provision a 1 terabyte volume, then you pay for 1 terabyte, no matter how much of that volume you actually use. If you use 1 meg out of 1 terabyte, you still pay for 1 terabyte. Now, within EBS, we do have several types of volumes. The first volume I'd like to point out are the SSD volumes. And within the SSD volumes, those come in 2 different flavors. We have the general purpose, which will operate at a baseline of about 3 IOPS per gig. So you can expect a 100 gig volume to give you somewhere around 300 IOPS. And then, of course, we could go, depending on the size of that volume, the larger the volume, the more IOPS we get. We're going to max out at around 10,000 IOPS for the general purpose volumes. And of course, those you'll see here that those come in a range of anywhere from 1 gig to 16 terabytes. Now, with a provisioned IOPS says that perhaps you want a certain amount of space, but you want to guarantee that you're going to get not just a baseline performance, but you want a performance far above what you might get with general purpose volumes. And so with provisioned IOPS, we do have a higher minimum of 4 gigs. We can still go up to the 16 terabytes, but here we can get all the way up to 20,000 IOPS per volume. So provisioned IOPS volumes are really great for cases, especially like databases. If you want to run your own database, MongoDB, Cassandra, MySQL, Postgres, whatever it is, on EC2, then you definitely want to look at provisioned IOPS. If you have some other application that is doing more streaming, more sequential I/O, then you might want to look at the hard disks. The hard disks have 2 flavors. We have the throughput optimized and the cold storage. The throughput optimized, you're going to see here, if we compare the throughput, this is where we can get upwards of 500 megabytes per second. So we just have different devices for different use cases. Solid states for more I/O intensive applications, the hard disks for more throughput intensive applications. All right, now let's take a look at creating Amazon EBS volumes using the AWS CLI tools. Here in our text editor, we've got 6.2 bash commands open. If you think back to when we first launched an EC2 instance on the command line and then we shelled into that instance, we're going to use that again later to mount some of these volumes. So before we create these volumes, we need to create them in the same availability zone as the instances we want them to be attached to. And so we're going to use the describe instances to find the machine. At this point, we should only have 1 machine running. Now, even though we launched some other ones, we launched ultimately 7 machines. We launched 1 initially and then 6 more, but then using our Lambda script, we terminated 3 and then we stopped 3. So that means that there should really only be 1 machine running right now. So we're going to use this command to find that machine where instance state is running, and we're going to pull out from that 1 instance in that 1 reservation, we're going to pull out the availability zone, and we're going to capture that, output it as text, and capture that into a variable. Okay, so let's go ahead and run that. Now if we echo that, you can see that machine was launched into US East 2C. you may end up with a different value there. And that's okay. We're going to use that variable. Okay, so now let's go ahead and create a few volumes. Here, we're going to create just a general purpose SSD volume, and we can do that by running the create volume command, specifying the availability zone. Keep in mind that EBS is not a regional service. It is available throughout the region, but each EBS volume is specific to an AZ, so we have to specify the availability zone. Here we're saying the volume type is GP2, which is general purpose SSD. We're going to specify a size of 100 gigabytes, and we can expect that the general purpose will operate at about 3 IOPS per gig, so this volume will give us about 300 IOPS. It might be okay for certain conditions, but in other applications like databases, we might want something more. Okay, so let's go ahead and create our first volume, general purpose 100 gig volume. There we go. We got one. You can see that we've created a GP2 volume in US East 2C. We're going to now create a provisioned IOPS volume. And we can do that. It's a very similar command, but the volume type for that is IO1. We're going to specify, again, 100 gig size. And here we're specifying that we want 1,000 IOPS. So let's go ahead and create that one. And there we go, just like that. Really easy to do, really easy to programmatically create EBS volumes using the CLI tools. Now I will say that sometimes in a case like this, if all you need is 100 gigs and 1,000 IOPS, then it actually, in some cases, it could be cheaper to, instead of creating a smaller drive with higher IOPS, it could be cheaper to create just a larger general purpose volume. So a general purpose volume of 400 gigabytes would give you a baseline IOPS level of 3 times 400 would give you about 1,200 IOPS. And that actually may very well be cheaper than paying for the provisioned IOPS. So consider that as well as you move forward. Here we're going to create some volumes with a few tags. We're going to create a couple more general purpose volumes, and we're going to say that we're going to tag these. Notice here that I'm going to say that one belongs to the MongoDB service. I'm going to also specify a particular cost center. Here I'm going to specify that another one belongs to the Kafka service, or ultimately will be used by instances running Kafka, and it might belong to the analytics project. And again, though the way that you tag your instances and volumes is totally up to you. I'm just showing you some examples of how you might go about that, and then of course we can use those tags within our automation. We can use it to find what we're looking for, and we can use it to correlate cost. Okay, so let's go ahead and create those 2 volumes. There you go. You can see that the tags that we added in that command came out into that volume that we created. We're going to go ahead and create that next one there for Kafka. Pretty easy and pretty fast to create EBS volumes. Now, I will say that at this point you can see that it is creating. It's not quite ready to use yet, but at least this command does return very fast, and this right here is a perfect example of the on-demand nature of the cloud. Getting what we need when we need it, and not having to wait on anyone else. That is a very key tenet of cloud computing, and that enables all of the agility and flexibility and time to market advantages that we're looking for by moving to AWS. All right, so now that we've created some volumes, we can use the list volumes command. Let's run that to describe the volumes that we have. And of course, that's going to give us a whole lot of data that we might not be interested in. Now, we might want to use it programmatically, but we could filter that. Let's take a look at ways that we can filter that. So here we're going to filter by tags. So here, let's filter. This is an interesting one that we haven't seen before. We're going to describe volumes using the filters attribute that so many services support. But here, instead of looking for a tag by the value, we're looking for a tag by its name. So notice here that the name of the filter is tag key. So we're looking for volumes who have a tag named service. We're not so much interested in a specific value of that tag, but just the fact that it has the service tag. Okay, so let's go ahead and try that and see which volumes we get back. We should get back those 2 volumes. And my MFA PIN expired, or my temporary credentials expired, so let me enter my PIN again. There we go. And you can see that the 2 volumes I got back from that command, filtering by those tags, or the fact that it had a service tag, here's the service Mongo, and down here, service Kafka. Now, if I wanted to make that more readable, I could do the same thing, but back here, for every volume, I want to take the service tag, I want to pull out the value of that service tag, and through the pipe and the flatten, I want to pull that out onto one line. So that's what all of this punctuation is all about here, is pulling the value of that tag out of the nested array and putting it back up onto a flat line. And we're also going to pull out the volume ID, the size, the volume type, and the state of that volume and output that as a table. So let's take a look at that. There you go. Now we can see we have our MongoDB and Kafka volumes, 100 gig general purpose, and both of them are available. That means that they are not yet attached to an EC2 instance. They're just sitting there, available to be used by an EC2 instance. Here, if we wanted to take that a little bit further, we could list all of our volumes. Notice that we don't have any filters here, but we do want to customize some titles. So it's a very similar query that we had up here, but notice that we are using the curly braces and keys and values to create our own keys. And by creating our own keys here, we can output that in the table. The table will then get custom headers. So let's go ahead and run that one. And this will list all of our volumes, not just the ones for Mongo and Kafka. So you can see here we have a number of volumes. This list may be longer or shorter for you, and that's okay. You should be seeing the MongoDB and Kafka volumes in there as a general purpose volume. You can see here's our provisioned IOPS volume as noted by the IO1 type. Okay. We can also show attachment information by volume ID if we wanted to. If we go back here, you can see here that these volumes show that they are in use. That means that these volumes are attached. The fact that they're 8 gigs tells me that those are the root volumes for a Linux instance. So 3 of these belong to the instances that were stopped by our Lambda function, and 1 of these 8 gigs belongs to an instance that is still running. For our purposes in this particular lab, this last step here, I'm going to just copy one of these volume IDs. You will copy one of yours, and I'm going to come back here and paste it here. And what we're looking for is we're going to describe the volumes by volume ID, and what I want to see are the attachments for that volume in table form. All right, so let's take a look at that. There you can see that that volume is attached to device dev xvda to this particular instance, and xvda tells me that that's the root volume on that Linux instance, The delete on termination says that if we terminate this instance, then the volume will also be terminated, or the volume will also be deleted along with the instance. All right, so that's how we can use the AWS CLI to create and manage EBS volumes. Now let's take a look at mounting an Amazon EBS volume with the AWS CLI tools. And what we're going to do here is use the CLI tools on an EC2 instance. And we're going to have that EC2 instance go and find the appropriate EBS volume and attach that volume to itself. In order for that EC2 instance to do that, it needs permissions. And it gets those permissions through an instance profile. Now, here in our text editor, we have our 6.3 bash commands file open. And the first thing that we're going to do is find the instance that we're looking for. In this case, we want to find the instance that we created earlier. We created an instance with a public IP address that we shelled into, and we want to continue to use that instance. But at the time we launched it, we did not supply a role. So we can add a role to an existing instance. That was a fairly recent update to EC2. So here I want to show you another filter that we can use to find EC2 instances. Here, we've seen this before, but we're going to add to it. Here, instead of looking for just instances that are running, which could bring back more than one, we're going to look for an instance whose private IP address starts with the range 172.3.1. And notice the wildcard that we have there. That's why this particular filter is quoted. So because we launched that EC2 instance into the default VPC, and we know that the default VPC has a range of 172.3.1.00/20, or 21, somewhere in there, then we can be assured that we're going to find that one running instance in our default VPC. So we're going to go ahead and run that to capture that instance ID. So let's do that. We'll capture that instance ID, and we can echo that. There we go. We've captured that instance ID. Now what we need to do is associate the right profile. We're going to associate the EC2 volume access profile that we created earlier with that particular instance. And by doing that, we will give that instance the permission it needs to manage EBS volumes. So let's go ahead and run this command, associate IAM instance profile. We're going to execute that. And of course, I think I have a bug there in my profile. I happened to see it just as I pasted there. So there we go. And you might see that happen, and usually those kinds of things are easy to spot. There we go. Now you can see that by associating that, it shows an IAM instance profile association. Here's the instance ID that we used. And here is the profile. You can see that it's associating. So that might take it a minute to do that. Should be pretty quick. And here is the ARN of that instance profile that we created with CloudFormation earlier. Now, while we wait for that to finish associating, we're going to capture the public IP address of that instance. Because we launched it into the default VPC with the associate public IP address flag, we should have a public IP address that we can use to shell in. So let's go ahead and capture that. And if we echo instance public IP, there we go. We have the IP address that we used earlier. And with that, we're going to shell into that, just like we've done before, using our lab pim file. Okay, so now we have a shell session into our EC2 instance. Let's use the instance metadata service to take a look at the IAM information and see that the role is now provided to that EC2 instance. So we can use curl to do that. There we go. So by curling the instance metadata service here with IAM info, you can see that it does indeed have the instance profile EC2 volume access attached. It is through that instance profile that the CLI tools will go and retrieve temporary credentials that the AWS CLI tools can use to manage EBS volumes. So now that the instance has the right permissions, we're going to capture that instance ID again, but this time these following commands we are running from within the EC2 instance. So we can again use the curl to capture the instance ID from the instance metadata service. So let's go ahead and do that. This is the EC2 instance getting information about itself. We have its instance ID. We also, in order to get the region, we first have to get the availability zone, again, from instance metadata. Let's capture the AZ, which should be, if we echo that, it should be US East 2C. In my case, it should be 2C. You might get something else. There we go, US East 2C. We also want to grab the region because when we make calls with the AWS CLI on an EC2 instance, those tools haven't been configured with the default region. So when we make calls, we have to explicitly specify the region, and we can derive that from the availability zone. Okay, so now we have our region. Now what we're going to do is use the EC2 describe volumes command to find a volume in that same availability zone where the status is available, meaning that it is not yet attached to another EC2 instance. We also want to find it based on a service tag. So in this example, we're looking for an EBS volume that is used for MongoDB. And we're going to find the volume ID and set the output to text so that we can capture that. Let's go ahead and capture that and echo volume ID. There we go. You can see that we have indeed captured a volume ID. So now what we want to do is to see, before we can mount that, we want to see the naming pattern of devices. Different flavors of Ubuntu and Windows and so on will use XVDA versus SD and so on. So we want to see, we can use the ls block command to show us what's being used there. So I'm going to say sudo ls block to list our block devices, and you can see that it's using the XVDA naming scheme rather than SD. And you can see XVDA is essentially our root disk with that root partition. So what we're going to do is we're going to, again, use our region flag. We're going to call the EC2 attach volume command, specifying that we want to attach a volume to the dev xvdb device path. We're going to specify our own instance ID with the volume ID that we just captured. So again, this is an example of an EC2 instance attaching a volume to itself. There we go. Now you can see the attachment information came back. We have state attaching. It is attached at dev xvdb. And now we want to wait. Before we can really do anything, we have to wait for that volume to go from attaching to volume in use. So let's go ahead and wait for that volume to reach the in-use state. And there we go, it's already done. The fact that that wait command came back so fast means that it's already attached and ready for us to mount. So at this point, we've attached the volume to the EC2 instance. we still have to mount it. Mounting is a part of the operating system. Attaching is a part of the AWS environment. So let's go ahead and list those block devices one more time. And you will see that we have not only our root device, but here is the volume that we just attached, the XVDB, a 100 gig volume, and it's just attached. It's not mounted anywhere. So before we can do anything with it, let's go ahead and format this. Now, in this case, because I know that this is a brand new device meant for Mongo, I'm going to go ahead and format that device. If this were a situation where an EBS machine was recovering, being replaced by autoscaling, and then wanting to attach an existing volume with data, then obviously we would skip the formatting step, right? But in this case, this is a fresh volume, and in order to be able to use it, we need to format it. So we're going to go ahead and format that as ext4, specifying dev xvdb, where we know that it's mounted. There we go, done. We've just formatted our 100 gig volume with ext4. The next thing that we want to do is make a folder for us to mount to. And now that we have a folder, we can say mount /dev xvdb to /var Mongo. And now if we do a df, you can see we have the dev xvdb device mounted at /var Mongo. I can go there and list, and you can see that I have attached a volume, formatted the volume, and mounted it at the appropriate file system path. So that is how we can use the AWS CLI tools to attach and mount an EBS volume on an EC2 instance. Now let's take a look at creating Amazon EBS snapshots using the AWS command line interface. So in this lab, we're going to, again, shell back into that instance and use that instance to create a snapshot of the volume that is attached. So here in our editor, we have open 6.4 bash commands. Let's go ahead and shell back into that instance. We should still have our instance public IP variable in place. If not, then it's easy enough to replay the command that generated that. So there we go. We are shelled back into our EC2 instance. From here, let's once again go ahead and show off our volumes. And while I'm here, I'm going to go ahead and copy this command to capture our instance ID. So let's do a df command, which will show that we have 100 gig volume mounted at attached at dev xvdb, and that is mounted to var Mongo. And so here, what we're going to be showing is how we can have an EC2 instance automatically create its own snapshots or snapshot volumes that are attached to it. We don't necessarily need some external service to do that for us. We already have compute power there, and so we can give the machine the ability to do it itself. So here, let's go ahead and capture the instance ID from the instance metadata service. Let's also capture the availability zone and the region as well from the instance metadata service. The region will be derived from that. So now let's just verify that we have the region US East 2, that's correct. Let's take a look at the volumes that are currently attached to this EC2 instance. We can do that by saying describe volumes and filtering them by the instance to which they are attached. And so by using the attachment.instanceID filter, with a value of the current instance ID, we can get a list of volumes that are attached to this instance. And there we go. Here is that, this first one here, XVDA is our root volume. Can verify that because it's an 8 gig volume. And down here, we can verify that our MongoDB volume is indeed mounted at dev XVDB. Okay, so now we're going to essentially do the same command, but there could be a case where we have a number of volumes attached for different purposes. So in order to ensure that we're taking a snapshot of the right one, we're going to further filter this by service, tag service MongoDB, to ensure that we are grabbing the volume used for that particular service. And we're going to query on the volume ID, output that as text, and capture that in a variable. So let's go ahead and capture the volume ID for our MongoDB volume. Now what we're going to do is use that volume ID to create a snapshot. We're going to call the create snapshot. We're going to give it a description, MongoDB automated snapshot. And here we know that we're going to get some data back from that, and we're going to query on the snapshot ID so that we can capture that in a variable. So let's go ahead and do that to create that snapshot. There we go. So now that snapshot is pending and running. We're going to wait for that. We're going to use a waiter here, the EC2 wait for snapshot completed, passing in that snapshot ID. Here I need to fix that. Had a little bit of a typo there. Let's go ahead and wait for that snapshot to complete. Now, of course, all of this stuff is a really perfect example of how we can script this. All of these commands are all in the right order. I would encourage you to take inspiration from this, to leverage this code to build your own scripts, to automate your own environments. And perhaps you want to take a script very much like this and turn it into a cron script that runs locally on the machine, if that makes sense for you. Or you could perhaps run this on a machine on premises that's making calls to Amazon and doing it from the external rather than inside EC2. So a 100 gig volume with essentially at this point, we know that this was all fresh volumes with no data really being written in this particular lab. So the snapshot should complete pretty quickly. There we go, it's already done. So now that we've created the snapshot, we can run the describe snapshots command, filtering it by volume ID. So let's go ahead and do that. And there we are. There is the snapshot that we just created. And that is how we can use the AWS CLI tools to automate the creation of Amazon EBS snapshots. In this lab, we'll use Python to perform some volume cleanup. Here in our editor, we have 6.5 bash commands open, as well as our source scripts volume cleanup Python script is also open. Now, the purpose of this script is to automatically find volumes that are essentially no longer in use and go ahead and clean those up. We want to take a snapshot of those and then delete those volumes. So this is an example of where in an cloud operations role, you might find just during the normal course of business, the normal course of running applications, deploying applications, experimenting, prototyping, and so on, that you may end up in a situation where you look and go, oh wow, look at all of these EBS volumes that we've created. They're sitting there and not attached to anything. We're paying the monthly storage fees, but we're not actually using them. So here's an opportunity to script that to keep that environment clean. Now, of course, you don't want to just go deleting volumes without performing a backup, so that's why we're going to create a snapshot of that volume first. So let's take a look at our Python script. Here, again, we are importing a few things, namely the Boto 3 Python SDK. Because we're running this locally, we're going to use the session module to specify that we're using the dev profile. Again, if this were done in Lambda or on EC2, then we wouldn't have to do this. We would just allow those services to configure the permissions using roles. The first thing that we're going to do are describe volumes, to find volumes that are not currently attached to anything. And we can do that with a filter, status available, meaning that the volume is available for use, but it's not yet attached and in use by an EC2 instance. If we find some volumes, we're going to keep on going. Otherwise, if we don't find anything, we're just going to go ahead and exit at that point. Okay, so the first thing that we want to do is make a list so that we can hold snapshot IDs. Now we're going to iterate through all of those volumes, and for each volume we're going to create a snapshot by saying snapshot equals create snapshot, passing in the volume ID that we got back from that response. We're then going to pull that snapshot ID from what we got back here. We're going to append that to our snapshot IDs list. And now we're going to wait. Notice what we're doing here. Instead of doing all of that serially, instead of snapshot, wait, we're essentially, through this for loop, we are initiating all of the snapshots concurrently and then waiting for all of them to complete. And you'll notice here we're getting a waiter, and we're saying we want to wait for the snapshot completed status, and we're waiting on all of those snapshot IDs at once. So that way we're doing all of this concurrently rather than serially, and that will cause our script to function a whole lot faster. And so once all of those snapshots have been completed, we can then go through, iterate over that volume list one more time, and delete those volumes. Okay? So let's go ahead and run that. The only thing we need to do is say Python, execute this Python script, and it should find 2 or 3 volumes that are no longer attached. We created a number of volumes earlier that are just sitting there that we don't need, but we're paying for them. Right? So let's go ahead and run this to clean those up. And of course, because we're using the dev profile, we're going to enter our PIN there. There we go. Finding volumes, it found 3 of them. And now it has initiated 3 snapshots, and those 3 snapshots are now running concurrently. And we're waiting for all 3 of them to complete before we move on. Just like that, they're all done. And now it says deleting volumes. If we were to do a describe volumes, let's just try that. Again, using the dev profile, EC2, describe volumes. We're going to use the query to pull out just the volume ID. Let's put that in a table form. There we go. And so those are the volumes that are left over. Some of those volumes belong to machines that are stopped and machines that are serving other purposes. So we have found 3, we created snapshots, and we deleted those volumes. So pretty straightforward how you can use Python to automatically find volumes that are no longer in use and clean those up. Let's just replay that one more time. Let's export this here just to show that these volumes that we're still getting back, output as JSON, we want to show that these volumes that we're getting back are indeed attached to things. And you can see here, Here are the attachments. So the volumes that are left over are still attached to existing instances. Now, one last thing I want to leave you with is if we look here at the code, I have left you with a challenge here. Within this for loop at this point, by creating the snapshot is somewhat ambiguous. There's nothing telling us what volume that snapshot came from other than perhaps a volume ID, and that doesn't really mean anything to our human brains. So the challenge that I'm going to leave you with is that we need a way to mark the snapshot to indicate what volume it came from. And I will give you a hint, it does involve key value pairs. So there's your challenge, to keep going and improve this code to mark those snapshots in a way that indicates not what volume ID that they came from, but mark the snapshot in a meaningful way. So again, that is how we can use Python to keep our environment clean by cleaning up unused volumes. Amazon Relational Database Service and Amazon DynamoDB give us fully managed relational and NoSQL data stores, which require very little maintenance and effort from us. In this lesson, we review creating database resources with AWS CloudFormation and automating database backups for disaster recovery. Now let's review Amazon Relational Database Service, or RDS. With the Relational Database Service, of course, we get our choice of a number of different popular database engines: MySQL, SQL Server, Oracle, Postgres, MariaDB, and Amazon Aurora. And Amazon Aurora it can be a drop-in replacement for MySQL 5.6 or Postgres. So with Amazon Aurora, a number of things are handled for us, like automatic storage scaling and a number of other things. So by leveraging the Relational Database Service, we are ultimately handing over the operational burdens of keeping this database running to AWS. And so we can get out from underneath the operational burdens of doing things like managing not only the physical layer, but also patching the operating system, patching the database engine. Those kinds of things can be automatically done for us. We can have backups automated and done daily for us as well. It's also, because Amazon can do the backups, we can also do manual backups, and we can copy those to other regions. And so we get a very easy way of gaining geographical diversity in our data. And we can also create read replicas if we want to either increase the performance, or we can also do read replicas not only in different availability zones, but we can also do cross-region read replicas. Now with the RDS multi-AZ deployments, this is a recommended best practice for production systems. With multi-AZ deployments, AWS will create a primary instance in one availability zone, and they will create a secondary instance in another availability zone. So all we really have to do is create our subnets, one per availability zone, and we then create what we call a subnet group. We will see that in an upcoming lab. And then we let AWS, we say that we want our RDS instance in a multi-AZ deployment, and we allow AWS to create these two instances. AWS will also handle the synchronous replication between those two devices. Now, what we get out of that is that we do know that those are going to be not only physically distinct machines, but also they will be placed in physically distinct data centers. That gives us high availability, and it also lowers our RTO and RPO to minutes. In the case of a failure, if the primary database fails because of a loss of network, because the compute system failed or the storage system failed, it doesn't matter. Whatever the reason that the primary system might fail, AWS will handle the automatic failover, and they handle that by, one, the secondary RDS instance will be promoted to primary. The IP address behind the DNS endpoint that we connect to gets updated, and then the failed, in the case where the primary fails, that failed primary will then be replaced. So again, if we're using RDS in production, it is a best practice that we choose multi-AZ deployment so that we get this automatic failover and high availability, all of that handled for us by AWS. Now, because RDS is ultimately built on top of EC2, but managed by AWS, we still get the same benefits of EBS snapshots. So ultimately the snapshots work in the same way as EBS snapshots. Those snapshots are stored in S3, and we know that data in S3 is replicated across numerous availability zones. So by taking regular snapshots, we can gain a much more durability in our data. And then, of course, copying those snapshots to other regions, which is very easy to do, we can also get geographical diversity and an even higher degree of durability in our data. Now, with automated backups, we set the backup window, but it's important to remember that automated backups, even though we can set the backup window, we can set the retention time up to 35 days. When we delete the RDS instance, the automated backups are also deleted. If you want to ensure that you still have a snapshot of that data when the RDS instance is deleted, then you need to be sure that you take manual snapshots. Automated snapshots are going to happen during that backup window once a day, but manual snapshots can be performed anytime, and they are kept even when the DB instance is deleted. And then, of course, we can use snapshots to very easily restore a DB instance if there was some kind of a problem and we do need to recover back to from a backup or a point in time. Or we could use that to clone a DB instance in another availability zone. So again, when we are running an RDS instance, it's very important that we take these backups, and we know that those backups are going to be stored in S3, giving us a higher degree of durability. Now let's talk about Amazon RDS subnet groups. Within RDS, if we're going to launch an RDS instance, first we need a place in our network for that. Now, with RDS, you can't simply launch an RDS instance directly into any subnet. Now, our network already has 3 private subnets that we have specifically set aside for RDS instances. You recall that we've created 3/28 ranges specifically for holding RDS instances. Now, when we go to launch this RDS instance, again, we can't just place the RDS instance directly in one of these subnets. What we need to do is take these 3 subnets and put them into what we call a subnet group, a DB subnet group. So ultimately, the way that this works is that we are telling AWS, hey, when you manage the database for us, I want you to make use of these subnets. When we create the DB subnet group, we have to have at least 2 subnets and at least one in each of at least 2 availability zones for the sake of gaining that physically distinct data center and gaining high availability, not just to the loss of an RDS instance, but also to the loss of an availability zone. So again, before we can launch an RDS instance, we have to first create the DB subnet group by selecting at least 2 subnets that are in at least 2 availability zones. And by doing that, by creating a DB subnet group, ultimately now AWS says, okay, I have these 2 or these 3 subnets to choose from. Thereby, because subnets are one-to-one with availability zones, Amazon now has multiple availability zones to choose from. And when AWS launches the underlying instances for our RDS DB instance, AWS will choose the best availability zone for both the primary and the secondary at that time. We don't have to worry about what the best AZ would be. We just tell Amazon which subnets we want to use and allow AWS to handle making the decisions as to where the best place for that instance is. And again, we do that by creating a DB subnet group. In this lab, we will use AWS CloudFormation to create an Amazon RDS DB instance. Now again, we have already created our 3 subnets with a /28 range. So we already have our subnets there. The first thing that we need to do in this lab, we're going to create a DB subnet group that leverages these 3 private subnets. We're also going to create a security group specifically for our RDS instance. And we're going to then create the RDS instance itself. So in this lab, we will be using CloudFormation to create our DB subnet group, our security group, and our RDS instance. Okay, so here in our text editor, we have 7.3 bash commands open. We also have in our CloudFormation data store folder, we have open the RDS billing Postgres YAML file, which is our template for creating our RDS database instance. So let's take a look at this template file first. Just like before, we are using cross-stack references. So we are going to reference the network stack that we created earlier. We're also going to accept an environment variable so that we can specify whether this is dev versus production. And we will use that later in the script to determine a few things. We're also going to accept a DB user and a DB password parameter. Now here, this is something we haven't seen before. Within CloudFormation, we can specify conditions. And conditions allow us to determine whether to do one thing or another, or whether certain resources should be created or not. In this case, for RDS, if we create this in a development environment, then we want our instance to be just a single instance. If we launch this into a production environment, we want it to be a multi-AZ deployment. We want it to be 2 instances, a primary and a secondary. So here, we're going to create a condition called create prod resources. We're using the intrinsic equals function to determine whether or not the environment parameter equals prod. If it does equal prod, then later we will create that as a multi-AZ deployment. The first thing that we're going to create is our DB subnet group. The DB subnet group, again, being the logical grouping of subnets so that the RDS service can determine the best place to put these database instances. So we're going to be importing values from our network stack. We're importing our subnet DB A, B, and C IDs. Those are the subnets that we created specifically for housing RDS instances. Those subnets were in the /28 range. We're going to add a few tags to those subnets, scoping it as private, setting its purpose for a DB, setting the service to billing, and then setting the environment tag as well to whatever we enter in as the parameter. Now that we have our DB subnet group created, we're going to use that to create our DB instance. This is our billing service DB. So the typical pattern in microservices is that each microservice gets its own data store. That way we can avoid single points of failure, we can avoid cascading failures. So our billing service will get its own database, and in this case we're using a Postgres RDS instance. Here we are calling it billing service. We are saying that the subnet group that we want to use is the microservices DB subnet group that we're creating just up here at the top. We're going to give this 100 gigs worth of storage, and we're going to launch that on an M4 large machine. We're specifying Postgres 962 with 1,000 IOPS on that disk storage. And then here, this is where we're going to reference the create prod resources condition. We're saying we're using the if intrinsic function. If the create resources equals true, then multi-AZ will equal true. Otherwise, multi-AZ will equal false. We're also going to say that this RDS instance is not publicly accessible. We're going to set our master username referencing our DB user. Same with the password, referencing the parameter that we pass in. Also setting tags, just like we did with the subnet group. And now along with the RDS instance itself, we also want to create a security group. So here we're creating a security group called Billing Service DB, referencing the VPC ID, so Amazon knows what VPC the security group belongs to. We're creating an egress rule to allow all traffic to leave, but so long as the CIDR range that it's leaving to is within our local VPC. We want to use this security group to ensure that this database is not making outbound connections to somewhere outside of our VPC. We're also going to allow 5432, which is the Postgres port. I'm going to change that here. I put in the wrong name there. I'm going to change that to Postgres, allow Postgres. So this is our incoming security group, referencing the security group that it belongs to. And here we're saying that we're allowing inbound port 5432 from the range of our VPC. Okay, so that's what's happening in our CloudFormation template. Let's take a look over here. Before we go on to create that stack, let's take a look at a few other things. First, let's take a look at the exports that we have within CloudFormation. We're going to take a look at the values here. And of course, because we're in that dev profile, let's go ahead and enter our MFA code here. All right, so there we go. Now we're seeing these are all of the values that have been exported by that previous stack. But it's not terribly meaningful to us. We can say that, yeah, we know that this is the range and this is the VPC, but we don't really have any correlation as to what these subnet IDs belong to. So here, what we want to do is use the query to limit to just the DB subnet. So what we're going to say here is in this query statement, we want to find the exports. Notice here, using the question mark, starts with. So we're looking for exports whose name starts with microservices network subnet DB. And from that, we're going to pull out the name and the value of that, and we're going to output that in a table. So that should show us only the subnet values that belong to our database subnets. And there we go. You can see this is the name of the exports for microservices network subnet DB A, B, and C, and there are those correlating values, and those will be imported into our template when we execute it. Okay, so now let's go ahead and just like we've done before, we want to validate that template and make the output of that validation a little bit prettier here using the table output. So let's go ahead and validate that template. Okay, so these are the parameters that we need to enter at the time we create the template. In this case, we're going to create that template. We're going to name it RDS Billing Postgres, point to our template file, and then here we're going to again add those parameters. Microservices network for the network stack. We're going to set, here I'm going to change that to dev. If you want to try that as production just to see that RDS will create a multi-AZ deployment, then feel free to do that. For the sake of this demo, so this stack finishes quicker, I'm going to set this to dev. Now here, I'm going to set my DB user to rjones. I'm going to set my password to a value of OICU812, exclamation point. And from there, we're going to come back and talk about that point here in just a little bit. But let's take that and execute that stack. Okay, now let's wait for that stack to complete using the waiters like we've seen before. Now, I do want to point out here that while we're waiting on that, let's take a look here. You will notice that we are accepting a DB user and a DB password as parameters for the master user of this database. And because those were placed as parameters on the CLI, that means that the master user credentials are now a part of my are a part of my bash history, which is not necessarily a good thing. So because that is a database user, we could go ahead and make a connection to the database, use that user to change its own password. That way, the password that is here in my history is no longer the same password that's actually in the database. So keep that in mind. Right, this is the master user, and it would essentially have root privileges on that database, or close to root privileges anyway. Again, we're just going to wait for that stack to complete. Now, instead of waiting, if you don't want to wait, we can always replay. I'm going to replay a describe stack events command, and I'm going to change the name of that stack here, and I'm doing that with Control-R and searching for describe stack events, which will look back through my history. So I'm going to go back here and describe the events for my RDS billing Postgres stack. And there you go. We can see that a number of things have finished, but the billing service DB is still in create in progress. So we're still waiting on the database instance itself to be created. You can see here that the microservices DB subnet group has completed, that the security group has completed, the ingress rule and egress rules have completed, and now we're waiting on the actual database. I can replay that to see it's still in create progress, and I can just keep going for as long as it takes if I wanted to. I could just keep replaying that every few seconds if we wanted to. Otherwise, we can just replay the waiter. I can do a Control-R. I'm going to show you that again. If I do Control-R and type in wait, it will go back in my history and find the last command with the word wait in it, which is the one we want. So I'm going to again run that and allow that to wait for me for that stack to complete. And there we are. Our database stack has created. Let's take a look at the stack events one more time. You can see that our database instance finished creating and the stack itself finished creating. And then of course we can describe the parameters. I want to show you something here. Let's run the describe stacks command with the stack name, and we want to output the parameters of that stack into a table, and I want to show you something here. Notice that all of the parameters that we entered into that stack are available, including our DB user and our DB password. So in this regard, we really only have a couple of choices for this. We could either hard code the username and the password in the template where it's exposed, or we could put it in as parameters where it's exposed in essentially two places now. It's exposed here, where anyone with the ability to describe stacks, any member of our team that has access to CloudFormation, can describe the stack and pull those parameters and see the master user for this database, see the credentials. Anyone who gains access to the CLI history will also gain those. So that's something to be aware of, that the first thing you'll want to do is log into that database and change the password for that user within the database. All right, so keep that in mind. And that is how we can use AWS CloudFormation and the AWS CLI to create RDS instances. Here in this lab, we will use Python to create an Amazon RDS snapshot and copy that snapshot to another region. So here in our text editor, we have 7.4 bash commands open. We're also going to open our source scripts RDS snapshot copy Python script. And let's take a look at this code and see what this code is doing. Just like before, we're importing our Boto 3 Python SDK and a few other modules to help us. Here, because we're going to run this locally for now, just to prove how this works, we are going to create the session and set the profile to dev. This is an example of a script that could very easily and probably should be run in Lambda. And I will let you learn from what we've done before. We've already done a lab on creating Lambda functions, so I will leave it up to you to package this particular function in Lambda if you choose to do that. That will be another challenge that I'll leave you with. So here, the interesting thing about copying a snapshot is that the database, in this example, the database currently exists. Our RDS billing database exists in US East 2 in Ohio. And so we want to take a snapshot of that database, and for the sake of disaster recovery, or for the sake of cloning that database into another region, we want to copy that snapshot from Ohio to Oregon, US West 2. In order to do that, we need to create the snapshot in Ohio, where the database actually is, and we need to copy the snapshot or perform the copy snapshot command in Oregon. So here we need two clients. This first client will be a client that represents that will be functioning in the Ohio region. The second client, Client West, is a new client, and we're going to set the region name to US West 2. So we have two clients, one for use in Ohio and one for use in Oregon. The first thing that we need to do now is find all of our DB instances, and we're going to use here the client for the Ohio region where our database actually is. Now we're going to iterate through that list of instances. For each database, we're going to create a DB snapshot, and we're going to name that snapshot. We're going to use the DB instance name and a date. You can see here we're using a year, month, day, date to create the DB snapshot identifier, assuming that this is something that might be run once a day. We're also going to specify the DB instance identifier that this snapshot belongs to. Now that we've initiated the create DB snapshot command, we're going to wait for that snapshot to complete. So again, we're going to instantiate a waiter, waiting for the DB snapshot completed status, and we're going to tell the waiter to actually wait for that particular snapshot to complete. Once that snapshot has completed, we can then copy that snapshot to another region. And again, in order to make the copy from one region to another, we will make the copy DB snapshot call in the Oregon region using the client West client. And you can see here, in order to identify the DB snapshot, it's not enough to use the DB snapshot identifier like we did up here. We need to use the full ARN, which includes the US East 2 region name. We also want to copy tags so that all of the tags on that snapshot go along with it. So at this point, what I want you to do is let's highlight this dev account number placeholder. Let's open up our accounts text file that we created, and I want you to copy the value of our development account. We're going to come back here to RDS snapshot copy, and we're going to paste the value of our development account. I've pasted mine, you will paste yours. And that's what our Python script will be doing. And now all we have to do is execute that Python script. Again, put in our MFA code. There we go. You can see that it found our billing service DB instance, and it has initiated a snapshot of that. It's naming that snapshot as billing service 2017-0629. Now, while we're waiting on that snapshot to complete, I'll go ahead and point out that what we've created here, even though we've written a script to do this, and this script could be automated by running it in Lambda and scheduled with an event scheduler like we saw before, this is ultimately, as far as RDS is concerned, this is what we would call a manual snapshot. And if you recall what we talked about, the difference between a manual snapshot and an automated snapshot, again, as far as the language of RDS is concerned, is that an automated snapshot is performed by the RDS service once a day for us anyway. What we're doing here is a manual snapshot because we are doing it. Yes, it's automated, but because we are doing it, not the RDS service, it will be considered a manual snapshot. And the key difference between those two is that if we ever terminate this RDS instance, the automated backups, those ones that were performed by the RDS service, those will be deleted along with the DB instance. All of these manual DB snapshots, the ones that we create, will be saved. And so here, not only do we have database backups that are exempt from deletion, we're also copying them to yet another region several thousand miles apart for the sake of disaster recovery. And there we go. We've finished the snapshot. We've copied that snapshot off to the Oregon region. And now we have not only a backup in Ohio, but we also have a backup in Oregon. From there, we could choose to recreate this database in another region if we wanted to. And that's how we can use Python to automate the snapshot and copy snapshots of an Amazon RDS instance. Now let's review Amazon DynamoDB. DynamoDB is a NoSQL data store along the lines of MongoDB and Cassandra. Because it is backed exclusively by SSDs, we do generally get a single-digit millisecond response time. So it is designed to be very, very fast when using indexed-based queries. Now, because DynamoDB is built to be replicated across numerous facilities, not just numerous devices, but numerous data centers, it is inherently highly available and fault tolerant. All of that is built in. We don't have to worry about it. Again, it is replicated across numerous availability zones within one region. So Amazon DynamoDB is fully managed. The only thing that we have to do is to provision our throughput, and we can do that in terms of reads per second and writes per second. And beyond that, there really is no management for us other than creating a table, creating our indexes, specifying our throughput, and then reading and writing data. All of the underlying management and ongoing operational burdens are handled by AWS. And DynamoDB can auto-scale the throughput. So again, DynamoDB, any data that we write to a table, we know that that data will be written to numerous solid-state drives in numerous availability zone for the sake of fault tolerance and high availability and durability in our data. Again, all of that is built into the service. We don't have to worry about it. Now with DynamoDB, we do get to create tables, and tables are comprised of items, and items are comprised of attributes. Now, even though we do have tables, there are no relationships between tables, and so DynamoDB does not have a concept of relationships, and DynamoDB will not perform joins. Generally, these tables are schemaless. The only things that we really need to define up front would be our unique primary keys and any secondary indexes that we might want to have on that table. Secondary indexes can only be created at the time the table is created, but we could create global secondary indexes on that table at any time later. Now, ultimately, there is no limit to the size of a table. The data can grow and grow and grow as much as we want. The only limit that we do have is on a per item basis. We do have a 400K item size limit. Another really nice feature that DynamoDB has is support for a per item TTL, or a time to live. And so in that way, we can get DynamoDB to act very much like a cache, something that we have long relied on Memcache or Redis to do for us. So by using a TTL, we can get items to expire out of our table and be automatically deleted. That way we're not holding on to data that we don't necessarily need. So this right here, using DynamoDB with built-in TTLs, could make DynamoDB very useful as some type of state storage, especially in regards to sessions, if you have to store something like that. Ideally, our applications are stateless, but sometimes we do need to store that kind of data, and DynamoDB is a perfect use case for it. So So again, with our tables, we do have to specify some type of a primary key. Every item in that table needs a unique identifier to identify that object. And of course, the primary key will be indexed. And if we have two choices with our primary keys, we could have, in this example, we have a users table with their name, with their date of birth, with their zip code, maybe some other general information that we might store. And in this example, we are using simply one field. We're using the name attribute as the partition key. And as the name suggests, because DynamoDB is a distributed system, it is storing the data across numerous shards or numerous partitions, we need a way of determining which partition will hold the data. And of course, that's what the partition key is for. So AWS will use, in this example, AWS will use the value of the name attribute to determine which partition the data lives on. Now, it's really important to think deeply about the nature of these values. If you end up with one particular name that's much more popular than all the other names, then you're going to end up with something called a hot key and then a hot partition. So if you end up with relatively few values for this partition key, then you could end up with one partition handling the great majority of data and requests. And so you're going to end up with some performance degradation. So ultimately, when we're creating a partition key, we want to choose a key whose values will contain a wide range of values so that we can get an even distribution of data across those partitions. Now, another thing that we can do with our primary keys is that we can create what we would call a composite primary key, which is the combination of the partition key plus a sort key. And it's the unique combination of those two that forms the primary key. In this example, we're showing that we have, notice here that we have the same value for name, but we have a different value for the friend. So here we have a different friend over here. And so again, it's the unique combination between name and friend that makes that unique. And so here we could do a query that says something like query based on where name equals Jane.doe, and then we can sort the friends. Again, that's why we call it a sort key. We can sort based on the friend column or the friend attribute, or we could apply other filters to the friend attribute like less than, greater than, between, and so on. Keep in mind that if you want to get the fastest response possible, we want to use some type of an indexed query. So we want to, by querying on the partition key or the partition plus the sort key, that is going to give us back the fastest possible response because the primary keys in either case, whether it's a partition key or a partition plus sort key, those are going to be indexed. And that ultimately is our review of Amazon DynamoDB. In this lab, we'll use AWS CloudFormation to create an Amazon DynamoDB table. Now, what we're going to create in this lab is a DynamoDB table that we will use for operational purposes. So DynamoDB is great for our applications. It can also serve us in operations. So one example that I'm pulling from personal experience is using DynamoDB to record deployments and deployments of various services to various environments. And so in this lab, we're going to create a table called deployments. And that table, of course, will need a primary key. In this case, we're going to use the service attribute. We're going to create an attribute called service as a string, which will serve as our partition key. We will also create a time attribute as a number, and we will record that as a Unix timestamp. and we will use that as our sort key. And those are the only two attributes that we will need to specify up front in the creation of the table so that we can create our primary key. Now, we will also be storing the environment that we deployed to, whether it be development versus production versus test, UAT, and so on. We will also store the URI of the image. In this case, this will be a Docker image that we're deploying. So we're going to store that URI so we know we can record exactly what went where at what time. And then later, we can perform queries on this and say things like, show me all of the deployments for billing sorted by time, descending, so that we can get the latest one first. We can limit it to say 1 and grab the latest deployment of the billing service and go, what was the latest deployment? What environment was that? Or we could also filter and say, show me all deployments for the billing service sorted by time where the environment equals a particular, where the environment attribute equals a particular place, like dev versus production. And so that's what we will be creating in this lab. Okay, so now in our text editor, we have 7.6 bash commands open. We also have our source, CloudFormation, data store, DynamoDB deployments, YAML file open. So let's take a look at that and see what we're creating in this YAML template. The first thing that we're going to be specifying here is our DynamoDB table. You can see here it is of the AWS DynamoDB table type. And here are the properties that we're specifying are the table name. We're going to call that deployments by service. And here, the only attributes that we need to specify up front are those attributes that will be indexed. So if we were creating, besides our primary key, if we were to create any local secondary indexes or global secondary indexes, whatever keys we use for those indexes will also need to be listed here as attributes. And so in this case, we're going to be listing the name of the service as the attribute name, and the type of attribute is we're using S for string. Here, the time attribute is going to be a number, and we're going to be specifying that our service attribute is the partition key. We call that a hash. And the time attribute will be the range type, or that will be the sort key. And those two will be indexed. Together, the service plus the time will be a composite primary key. We're also specifying that the provisioned throughput for read capacity units and write capacity units, for now we're just going to set those to 2. We could later adjust those if we want, but now as far as deployment goes, I don't think that we're going to be deploying 2 services per second. So we can rest assured that 2 write units and 2 read units are more than plenty for this particular table. And this table will be very, very inexpensive, even with those 2 read and 2 write capacity units. Okay, so that's what's happening in our CloudFormation template for our DynamoDB table. Let's come back over here to our bash commands. And first, let's go ahead and, just like before, validate that template and make sure we don't have any syntax errors or unresolved dependencies. Everything looks good. We don't have any parameters in this particular case because DynamoDB is so fully managed. It doesn't rely on our VPC. It doesn't rely on anything else that we've done. It's all self-contained and fully managed. Everything that we need for that table has already been specified in the template. Okay, so now let's go ahead and create that stack. We're going to call that DynamoDB deployments. Again, using this table to track the deployment history of microservices. Let's go ahead and enter the MFA code. There we go. And because we're creating a single DynamoDB table, that should create fairly quickly. So just like before, we can use the waiters to wait for that. And there we go. Our DynamoDB table has created. And now we can describe. We can use the DynamoDB service to describe tables. And we can do that by table name. And if we look back here, the table name that we used is deployments by service. So let's go ahead and describe that DynamoDB table. And there we go. You can see that it has been created. It is an active table in DynamoDB. Here are our attribute for our keys. You can see that those are also reflected here in the key schema, just like we specified in our YAML template. So that's pretty straightforward, pretty easy, and really fast. And that's how we can use CloudFormation to create Amazon DynamoDB tables. Reliable instrumentation is a key component to effectively managing cloud-based applications, and the monitoring and centralized logging with Amazon CloudWatch provides just what we need to gain insight into the performance or operational issues our applications might be facing. In this lesson, we review Amazon CloudWatch, AWS CloudTrail, and use the Python SDK to create some very useful alarms. Now let's review Amazon CloudWatch and CloudWatch logs. With Amazon CloudWatch, ultimately this service is collecting metrics. It's not necessarily a complete monitoring solution. It is collecting metrics from various services, and it is storing those metrics for up to 2 weeks. So if you want to compare this week this year with this week last year, then you will need to use the API, use the CLI tools or the SDKs to pull those metrics in to something else and keep them for a longer period of time. Now, we do get a unique set of metrics per service. We also get the ability to collect custom metrics. From an operational standpoint, it can be really helpful if we are collecting things like the number of processes that are running, the number of threads, the JVM heap size, and so on. Those kinds of things, the EC2 service and other Amazon services really have no way of knowing, so they can't report them. But we can report information on our own applications, and later we might find that the need to scale is based on something like the number of processes running rather than CPU or memory. Now, with EC2, it's really important that we remember that the default interval for EC2 monitoring is 5 minutes. So if we are trying to scale based on those intervals, 5 minutes in some cases, many cases, is just too long to wait. We might want to scale in a matter of 2 minutes. So we might want to turn on detailed monitoring, and of course we're going to pay a slightly higher charge to gain access to 1 minute intervals. Now, it's also worth noting that within EC2, because these metrics are being collected by the hypervisor, and the hypervisor really has no way of knowing exactly how memory is being used. For EC2, we don't get memory metrics out of EC2. We get CPU, which is really accurate. We get disk I/O, network I/O, and a few other things, but we don't get memory. And if we wanted memory, then we would need to use a custom metric and have some type of application running on that EC2, some kind of an agent that is reporting memory usage from the inside out. Now, with the elastic load balancers, because we do rely on those for scaling. Those do give us a default 1-minute interval, and they give us those that the elastic load balancers are going to report things like the number of requests, queue depth, backend instance errors, latency, and so on. With RDS, we do get things like memory, number of connections, disk usage, freeable memory, stuff like that. With DynamoDB, we're going to see things like throughput metrics, provisioned versus consumed. And so that's going to be a really important metric to look at. Perhaps we provisioned 100 reads per second, but we're only actually consuming 50 reads per second. So if we've provisioned some level, but we're only consuming another level, then that would show us where we're perhaps spending more money than we need to spend. So with CloudWatch, again, a number of services will all report their various metrics to CloudWatch. CloudWatch is collecting and aggregating those metrics, and from there we can do a number of things like create alarms. Now with CloudWatch alarms, we can configure CloudWatch to create an alarm, and ultimately what that says is that a threshold has been breached. A number is either too high or too low. Now let's keep in mind that even though we are using the word alarm, it doesn't necessarily mean that there's something wrong, right? The word alarm does not necessarily signal that there is an emergency. Whether or not there is an emergency will be up to you to determine. We just use the word alarm to signal that a breach, some threshold has been breached. So alarms can exist in 3 possible states. They either exist in OK, meaning that for whatever period of time we've specified, that the actual data that CloudWatch is seeing is within the limits that we've specified. It's either below something or above something, depending on the nature of the alarm we've created. If that threshold has been breached, if the number is too high or too low, again, depending on the alarm, then the alarm status will be in the state of alarm, meaning that perhaps some action needs to be taken. We could also see a state of insufficient data. Now, insufficient data can happen in a couple of different ways. Let's say that we do create an alarm. Let's take this alarm here, and let's say that we want to create an alarm on an EC2 instance where the CPU utilization is greater than 80% for 2 periods of 1 minute. So what that means is if we see 2 consecutive minutes where the CPU usage is above 80%, then an alarm will be triggered. So for the first 1 minute and 59 seconds, the alarm will exist in the insufficient data state because it just hasn't been long enough. Now, some resources do not report a value of 0. So when those resources, like the simple queue service as an example, when it reaches 0, it just stops reporting. And so that could also signal that give us an insufficient data because no data has been reported for some period of time. So if you are doing some kind of an operational thing where you're looking for the state of an alarm, in some cases, OK and insufficient data could essentially be equivalent. Let's keep in mind that we do have limits. Most Amazon services have their soft limits and hard limits. With Amazon alarms, we do have a limit of 5,000 alarms per account. Now, again, back to this alarm here for a second. If we do create an alarm on CPU utilization, when that alarm fires, we have a number of choices. We could take some type of action. We could have that alarm go out through a simple notification service topic. So we could create potentially create a topic specifically for alarms. We could subscribe to that by way of email, Or we could have other third-party services. PagerDuty is a really excellent example of a third-party service that we can use. We could have CloudWatch alarms trigger, and then PagerDuty will go through an escalation policy by messaging and calling whomever is on duty and then escalating to the next person in line. We could also have this alarm trigger an auto-scaling policy. So perhaps if CPU is greater than 80%, maybe that means that we need to scale. And so we can have that alarm trigger auto-scaling, add a new machine or some number of machines, and then ideally the addition of those machines would bring CPU utilization down below 80%. Now with CloudWatch logs, we have a service that can ingest and collect logs for us from a number of different places. So let's say that we have a fleet of web servers running something like Nginx or Node.js, whatever it is, and they are logging to their own local files. What we really don't want is to have to shell into each of those machines, especially when we consider that these machines are disposable anyway. What if they go away before we can actually get into it and retrieve those logs? So CloudWatch logs gives us one place that we can centrally aggregate logs from a number of different instances. And so we do need to first install and configure an agent on those instances. It's really easy to do, very quick and easy installation, which can be done on bootstrapping. And then ultimately, that agent will essentially follow whatever log files we point it to. It will essentially follow those logs and stream whatever data is added to the end of that log will be streamed to the CloudWatch log service in near real time. We should remember that we pay for ingestion. We do pay an ingestion fee. So there is a particular amount that we will pay for every gig of data that is ingested. The retention time is indefinite. So CloudWatch logs by default will retain the logs that it ingests indefinitely. You can change that. You can say, hey, I only want CloudWatch logs to retain this for some period of time, 7 days, 14 days, 30 days, and whatever. We can have CloudWatch logs archive those off to S3. We can also very easily have the CloudWatch log service stream those logs directly to Amazon Elasticsearch. And by doing that, because Elasticsearch includes Kibana being a very powerful UI on top of Elasticsearch, we get a lot of analytical capabilities, very powerful means of searching and analyzing our logs. So again, in order to use CloudWatch logs, we are going to need to install an agent on our EC2 instances, configure that agent to point to the particular log file that we're interested in, and then the agent will stream those logs to the Amazon CloudWatch log service in near real time. From there, we can do all kinds of other really powerful things. We can have CloudWatch logs filters in place that are regularly looking for different patterns. In the case of a web server, we can be looking for error codes or HTTP response codes or the number of bytes that were sent. Just about anything that is in those logs can be turned into a filter pattern by Amazon CloudWatch logs, and from those filter patterns, we can create metrics and have Amazon CloudWatch logs automatically collect metrics from our logs for us. And so that is our review of Amazon CloudWatch and Amazon CloudWatch logs. In this lab, we'll take a look at creating Amazon SNS topics and subscriptions with the AWS CLI. Here in our code base, we have open 8.2 bash commands. Now, before we can create alarms we need a place for that alarm to send a message to. We need a topic within the simple notification service, and that's the first thing that we're going to create. Now, just like before, if you've seen the pattern that we're using here, we're using our admin account as a central place to not only to publish from, but also to publish to. So in this case, we're going to create in our admin account, and you'll notice here that we're going to create a topic in using the admin profile so that various accounts have one place that they can publish their alarms to. That way we don't have to go and create topics in all of these different accounts, and we don't have to subscribe to all of these different topics. We have one account into which we can create our one SNS topic, and all of our other accounts can then publish into that one place. With this command here, we're going to use the SNS service, calling the create topic command. In this example, we're going to name it infrastructure alarms. And this is a pattern that I've used over the years, create one topic for all of my alarms. And of course, you might have other topics for other purposes, but what we're going to be creating here in the upcoming lessons are various types of CloudWatch alarms for our infrastructure. Now, you might have alarms at the application layer that development teams might be responsible for, but if you're in a cloud operations role, managing the underlying EC2 instances and other infrastructure, then this might be a good topic for that. So we're going to name it infrastructure alarms, and what we get back from that is a JSON object, so we're going to query for the topic ARN and output that as text so that we can capture that in a variable. So let's go ahead and create that alarm in our admin account. And there you go. You can see that we've created that alarm. We get back the Amazon resource name of that alarm. And now what we want to do is we're going to subscribe to that alarm using our email address. Now, if you recall, with simple notification service, you can subscribe in a number of different ways. Email is just one of them. You could subscribe by way of HTTP endpoints so that you could call some third-party service like PagerDuty or something on premises. You could subscribe by way of text messaging. You could subscribe a simple queue service queue. You could subscribe a Lambda function to this alarm. So it really opens the door to having this alarm send a notification that then goes out to a number of different places, and that enables the event-driven ecosystem. So in this example, we're going to subscribe by way of email. So here we're going to, again, use the SNS service, and we're going to call the subscribe command. We're going to pass in that topic ARN that we captured earlier. And here we're going to specify that we're subscribing by way of email. And here the notification endpoint will be your email address. So you will enter your email address here, and I will enter mine. Okay, so now that we've gotten that, let's go ahead and make that subscription. And you'll see there that we don't yet have a subscription ARN. It says it's pending confirmation. So when you subscribe by way of email, what you have to do is first confirm that you do want to receive those. So at this point, what I want you to do is go ahead and check your email. I'm going to check email on my phone, and we'll see here I should, if I refresh my email, I should get that a test email from AWS telling me that I have subscribed to this particular topic, and there you go. And so now if I look here, we can see that I've gotten that email, and I'm going to hit in there is a confirm subscription link. I'm going to click on that and just confirm that link, and of course you will do the same with your email. Follow the link within that email to confirm that subscription. Now that we've created our topic, we've subscribed to that by way of email. Now what we're going to do is we're going to give the development account permission to publish to that topic. And then later, if we create other environments, testing, UAT, production, and so on, we can have those accounts, then we can grant those accounts permissions to publish into the same topic. So here, before we're able to run this command, what we want to do is, let's go back to our accounts.txt file and copy our development account ID. Okay, so I'm going to go over here to our accounts text file. I'm going to copy that development account ID, come back over here, paste that. You will paste your development account ID, and then we're going to use the add permission command, also specifying that the topic ARN of the topic that we created. And in this regard, we're going to create a permission that allows the development account to publish. And so we're granting, the actions that we're granting here are publish and get topic attributes. Okay, so let's go ahead and run that command, add permission, and there we go. We got nothing back, which indicates that all is well. The development account is now able to publish to that topic. Now what we can do, we can verify the development account is indeed allowed to publish to that topic. Here what we're going to do is call the publish command using our dev profile. So here we're going to be acting from within our development account using temporary credentials that represent the development account and causing that message to be published essentially from the development account. And you can see here we're specifying the topic by ARN, and we are publishing a message with a subject, dev account test, and a message that says hello. So let's go ahead and try that. The fact that we got a message ID shows that it's working. So let's go ahead and check our email one more time, and we should see that we did indeed get an email by publishing from our development account. And there we go. Now I can see that email has indeed come through. There you go. And if I look at there, I can see that it says dev account test in the subject. I can see it says hello in the message. And then you will check your email and you should see the same thing. So again, the simple notification service is a really great tool that we can use to receive notifications about things that are happening within our account. And this is one example of how we can use the AWS command line interface to create SNS topics, to allow other accounts to publish to those topics, and for us to subscribe to those topics. In this lab, we'll take a look at creating Amazon CloudWatch alarms with Python. Here in our code base, we have 8.3 bash commands open. We also have our source scripts create alarms Python script open. So let's take a look at the Python script first. In this scenario, what we're doing is creating a common alarm. And one common alarm that we might be interested in is being notified when the CPU of a particular instance reaches above 70% for more than some period of time. Now, high CPU usage may not apply to every application. Some applications use very little CPU, but high CPU usage could indicate some other problem, but not necessarily with our own application, but perhaps with some other application running on that instance. It could indicate some runaway script or runaway library, some race condition. It could indicate that some type of malware was somehow, some way made it onto our EC2 instance, right? So high CPU does oftentimes indicate something is not the way we really want it to be. So in this scenario, we're going to use this Python script to create that alarm for every instance. And these kinds of alarms can be automated, right? So you can take this script and run it in Lambda, and run it perhaps every hour so that it finds new instances and creates those alarms. So here we're going to, again, because we're running this locally for the sake of the lab, we're going to use the dev profile. If you decide to take this script and put it into Lambda, then we won't need that. We're going to create a client for EC2. We're going to create another client for CloudWatch. Those are the two services that we'll be using. The first thing that we're going to do is describe our instances. And here, we're not interested in instances that are terminating or have been terminated. We're only interested in instances that are pending, running, stopping, or stopped. So once we get back a list of EC2 instances, we are ultimately going to, with these two loops, we're going to be able to list or iterate through all of the EC2 instances. And for each instance, we're going to create that high CPU alarm. So here we're going to name the alarm CPU utilization by appending the instance ID as well. And what we're looking for is the situation where the CPU utilization is greater than 70% for at least one period of 300 seconds. So I chose 300 seconds or 5 minutes because that's the default interval for EC2 monitoring. And all of the instances that we've created so far through this course, we did not enable detailed monitoring, which would give us 1-minute intervals. We left it at the default, which is 5 minutes. So again, we're looking for the CPU to be greater than 70% for more than 5 minutes. And when that happens, we want to know about it. We want to be emailed and notified. So what we're going to do here is let's grab that topic ARN that we just created. I'm going to go back here and echo out that topic. Okay, you're going to do the same thing. And I'm going to copy that topic ARN. And I'm going to paste it in there. You will do the same thing. Okay, so I'm going to save that. And you can see here what we're also doing is setting the dimensions. The dimensions are the instance ID. We're giving CloudWatch the instance ID of the current instance that we're acting on within this for loop. Okay, and so that's pretty straightforward. Now, like I said, you could take this script and put it into Lambda, create an events rule scheduled for every hour so that as new instances come and go, you can have this script automatically add these alarms to your EC2 instances. Okay, so let's go ahead and run that. We're going to execute that Python script. And of course, we're using our dev account, so we do need our MFA pin. And there you go. You should see a similar output depending on how many instances you've created by this point. And so now all of the instances that are in our environment have the automated alarms created for them. And now what we can do is use the CloudWatch service to call the describe alarms command, and we can list out all of the alarms. I'm going to go ahead and execute that. And you can see, let's enter our PIN again. There we go. And you can see that as far as CloudWatch is concerned, we do indeed have these alarms registered for each of those instances. Now, if a CPU on any of those instances were to remain at 70 or greater than 70% CPU utilization for more than 5 minutes, we would get an email notifying us about that. So I do want to point out that in this script, I have left you with a challenge. Now the challenge is that you can't create the same alarm twice. Each of these instances already have their high CPU alarm. So if you were to take this script and put it into Lambda and have it run every hour, looking for new instances to add alarms to, so what we need to do here is implement a way to check to see if the alarm already exists. If the alarm for that instance already exists, then we don't need to create an alarm for it. And I will point out that that check does not necessarily require a call to CloudWatch. And the only hint that I will leave you with here is that you could use key value pairs. All right, so I'll leave you with that challenge. And that is how we can use Python to create common alarms within CloudWatch. And of course, we could extend this to creating alarms for DynamoDB tables. Some of those are automatically created for you by Amazon, but we could create more. We could create alarms for EBS volumes and other pieces of infrastructure within our environments. Now let's review AWS CloudTrail. AWS CloudTrail is the service that records all the calls made to the AWS API. So for the sake of compliance and security auditing, change management, we want a way to know exactly what calls were made to the AWS API for the sake of creating and managing resources. Now, it doesn't really matter where those calls were made from. If they were made from the management console, the CLI tools, the SDKs, or even other AWS services, either way, it doesn't matter what tool was used to make the call. All of these tools ultimately leverage the API in the background. And whatever calls were made to the API will be recorded. And of course, we can use this, like I've mentioned, to for compliance auditing. We can use it to monitor the activity of our users and resources. And if we can also use it to have ongoing audits of anything that might threaten security. Certain things like creating security group rules, network access control rules, things like that, making those kinds of changes could very well threaten security. So we might want to track those changes or be notified of those changes so that we can undo them as quickly as possible. The CloudTrail also gives us a really great way to help troubleshoot operational issues. So there's been plenty of times over my career with using AWS where I've made some little change or maybe several changes, and then all of a sudden I notice, wait, production has been adversely affected, and I don't know exactly what I did to cause that breaking change. So if I just rely on my own memory, which is fallible, then I'm going to be stuck trying to follow my steps backward and remember what I did. Especially in a team setting, when there could be numerous people making changes, along with other AWS services potentially making changes, then without one place recording all of those API calls, recording all of those changes, it could be really difficult to backtrace and figure out what exactly caused that problem. So having a service like CloudTrail record all of the changes that were made, recording who did what on what resource at what time, will really help us to identify exactly the change that broke production. Now, the way that we enable CloudTrail is, first of all, we're going to create and specify an S3 bucket, and then the CloudTrail service will regularly publish log files to that S3 bucket. And then, of course, we can turn this on either for region by region, or we can turn it on for all regions at once. We can also specify whether we want to record write operations, read operations, or all operations. And that's our review of AWS CloudTrail. Now let's review a use case where we use AWS Lambda to analyze AWS CloudTrail logs. So we've talked about how CloudTrail is a service that records all of the calls made to the AWS API. So what we're going to do in this use case is we've enabled the CloudTrail service, which is generating these log files. And these log files are being sent automatically every so often to an S3 bucket that we've specified. We're also going to enable S3 events so that as new objects are placed into this bucket, the S3 service will automatically invoke our Lambda function. So the S3 service will invoke our Lambda function. In order for it to do that, we need to create an IAM role to allow the S3 service to actually make that invocation of our Lambda function. Our Lambda function will also have an execution role, which says that during the execution of our function, Lambda is allowed to read from S3 so that it can pull these log files out, and Lambda is also allowed to write to or make calls to the simple notification service for the purpose of notifying us via email. So again, log files are going to be written to our bucket. The S3 service will invoke our function, and then our function could, in this example, we could be looking for certain actions or certain events that threaten the security of our infrastructure. And some of those events might be authorizing new security group ingress, new security group egress rules. We could be concerned about changes to our network access control lists, or even deleting network access control list entries. So any of these kinds of changes could potentially be dangerous. And so our code could look for those type of events and then compare the rest of the metadata with some other business rules and policies and make more intelligent decisions as to whether or not that is indeed a threat to the security of our infrastructure. And if our code did determine that, yes, that change is a threat, our code could then make a call to the simple notification service, which would then either notify us by way of email or text message so that we are aware of it as soon as possible. We could also potentially use Lambda to undo that change, or we could receive that email or text message and then come back and do that change manually. We might also want to have Lambda send not just the fact that something happened, but also inform us of what credentials were used to make that happen. So, perhaps we might identify that there's a member of our team that has more permissions than they really need to have, or perhaps there is some operational script that has some buggy code in it. So you can see here, by using Lambda to analyze our CloudTrail logs, we can gain a near real-time insight and near real-time action on changes to our Amazon environment. While containers are nothing new, the rapid rise of Docker over the last several years has really brought the advantages of containers into the limelight of the industry. Enterprises and startups alike are making rapid shifts to embrace containers as a way to improve the efficiency of software development and deployments. In this lesson, we review Amazon EC2 Container Service and deploy a containerized microservice. Now let's review the Amazon EC2 Container Service, or ECS. For those of us who might not be familiar with containers, ultimately a container is just a way of running a process in an isolated way. Instead of running virtual machines for the sake of gaining isolation between our applications, we can run our applications on the same operating system, leverage the same underlying operating system kernel, but still gain that isolation, the security between those various processes so that we can have numerous applications ultimately running on the same, leveraging the same compute power, but still gain the security of isolation between them. And so that's really what containers gives us. But when it comes to actually running a container, or if we want to run numerous containers and ensure that they remain running. If they fail, we want them replaced. And so we need a way to manage the life cycle of those containers. And that's exactly what Amazon EC2 Container Service does. It's ultimately a container management service. So the EC2 Container Service, what we do is we say, hey, I want this container to run. And the EC2 Container Service will find a place for it. What we do is create a cluster of machines, and we give the EC2 Container Service what I like to call a sea of compute, or an ocean of compute and memory and resources. And that is comprised of some cluster of machines. It could be one EC2 instance, it could be 2 or 20 or 200. That's up to us, whatever it is that we really need for our collection of services. And so the EC2 Container Service will just find a place for it, and it does so considering how much CPU, memory, network ports, or disk volumes that our containers might need. The EC2 Container Service does support Docker containers, and if you're familiar with other container management services like Kubernetes, then you could say that the EC2 Container Service is analogous to those. It is ultimately in the same family. The EC2 Container Service, you could say, is a competitor to Kubernetes. So what we're using it for is to schedule containers to be run. And those containers could be long-running applications like HTTP-based RESTful APIs. They could be messaging services, whatever they are, some type of service that needs to run for a long period of time. And if for some reason it fails, and the process fails and exits, and then the container dies prematurely, then the service will recreate that container. And it may not necessarily come back up on the same host, and that doesn't really matter to us. It doesn't really matter where those containers run, so long as they run. We can also run batch jobs, containers that come up, do their job, and then go away. And batch jobs don't necessarily need to be replaced if they fail. Because the EC2 Container Service is built on top of EC2, it integrates with Elastic Load Balancing, with the Elastic Block Store, with Virtual Private Cloud, and with IAM. So the EC2 Container Service is very integrated within the rest of AWS, and we will be exploring this throughout the rest of this lesson. Now, it can be helpful to visualize how the EC2 Container Service works. If we have a collection of EC2 instances in our cluster, so this is what we would call our ECS cluster. In this example, we have 3, and of course we could have 30 or 300 if we really needed to. In this case, we have 3 EC2 instances in our ECS cluster, and you can see here we have a number of containers being run. And again, it doesn't really matter to me where a particular container runs. I might have one here, and then 2 over here. So long as they run, I don't really care what machines they actually run on. So the EC2 Container Service, in this case, I might have an API on these 3 containers. And those 3 containers could be registered behind an Elastic Load Balancer, so that as I receive traffic from the internet into the Elastic Load Balancer, the load balancer can then forward those requests on to the containers running on these instances. The EC2 Container Service will ensure that if one of these were to fail for whatever reason, if there was a race condition within my process and my process exited non-zero and my container failed, then the EC2 Container Service will immediately replace that container. Now, that container might not come back on this particular EC2 instance. It could come back somewhere else. The EC2 container service is smart and aware of availability zones, so it does do its best to balance. If these three instances were in different availability zones, then the EC2 container service will do its best to balance containers across availability zones, but that's not necessarily a guarantee. Ultimately, it also has to take into consideration the amount of CPU, memory, and network ports that are available on these EC2 instances. Now, you can see here that I might have, like I mentioned, we might have an API here on these three containers, and I might have some completely different process running on another set of containers. I might yet have a third service running on other containers. And so the EC2 container service is a really great place to host our microservices. They can all live side by side with one another, and we can rely on the segregation, the isolation that that containers give us to protect these processes from one another. So that is the EC2 container service, and we will continue to explore this in depth as we move along. In this lab, we will use the AWS command line interface to create an Amazon ECS cluster. Now, generally when we hear the word cluster, we also think of a collection of machines. It's important to note that what we are creating, even though we are creating an ECS cluster, we are not creating the collection of machines. The collection of EC2 instances that form the body of the cluster are actually going to be created by the autoscaling group that we already have in place. What we are creating here is the logical grouping that we also call a cluster. And we have to inform the EC2 container service that we do have a collection of machines that all belong to one logical group for the purposes of the EC2 container service having a place to launch its containers. And so, again, we have already created, at this point, our autoscaling group. That already exists. Now we're going to create the ECS cluster, the logical grouping, so that the EC2 container service has a place to launch our containers. Okay, so here in our text editor, we have lesson 9.2 bash commands open. Now, the first thing that we want to do is create the ECS cluster. Again, that logical grouping, so that when our EC2 instances come up and join the cluster, they actually have something to join. We're going to call the ECS service to create a cluster, which again, only this in and of itself only creates a logical grouping. It creates a placeholder within the ECS service so that EC2 instances can join and be managed a part of the same logical group. The body of that cluster will be formed by the machines in our autoscaling group, and we'll come back to that in a minute. Now let's go ahead and execute this command to create the cluster name called Microservices Dev Ohio, which we're going to use the same name that we used in our autoscaling group earlier. Okay, so we're going to execute that. You can see here, as far as the ECS service, the EC2 container service is concerned, we have an active cluster, and you can see here that currently we have 0 container instances. Container instances references the EC2 instances on which we will run our containers. So now we need to add EC2 instances, and we can do that by going back to the autoscaling group that we created earlier and adding machines to that autoscaling group. If you recall earlier, when we created the autoscaling group, we created it with 0 nodes. And so now we're going to update that stack to have it create 3 nodes. So let's go ahead and do that. Here in our bash commands, you can see that we are calling the update stack. For the sake of keeping it simple and straightforward, we're just going to go straight to an update stack. Normally, I would recommend, especially in a production environment, especially when you have a change management process involved that you need to comply with things, definitely go through change sets. But here, just to keep it straightforward and simple, we're going to update the stack. We're going to use the previous template. You can see here we're not specifying a template body file like we've done before. We are instead going to tell CloudFormation to just use the previous template. We're also going to use the previous values for network stack, for our AMI, and for the key name. We're not changing anything in those regards. The only thing that we're changing is the number of nodes. We're going to push that up to 3. All right, so let's go ahead and execute that update stack. Okay, and now we can wait for that to reach an update complete status. And there we are. Now the update has completed. What's happening right now is that we have added machines. We've set the desired capacity to 3 nodes. And so now our autoscaling group is creating 3 EC2 instances. And as they come up, the user data that we included in those included a configuration script to have those EC2 instances call in and join the microservices dev Ohio cluster. So let's go ahead and do a list clusters here and see what we get back from that one more time. And you can see that what we get back from the ECS list clusters command is a list of cluster ARNs. So now we can use that list of ARNs to do a describe command. And at this point, I want to point out that as you continue moving forward and learning the AWS CLI tools and start using them, you will see that some of the older services like EC2, when you do a describe instances, then you get back the data. There are no list features, or at least there might be very few list commands in the EC2 service. But in some of the newer services like ECS, we start to see some list commands, and we start to see a little bit of a difference in how some of these services handle their commands using listing and describing in different ways. We also start to see a little bit of a difference in the schemas coming back in their JSON. Some of the older services use uppercase, camel case, and then some of the later services are using lowercase first. So keep that in mind, that the schema of data coming back is not always consistent between services. So you really need to, again, make the documentation your best friend and just get in there and get some hands-on experience and learn what these services will do. And so let's go ahead and, instead of relying on just that, let's capture those clusters as text output. We're going to capture that into a variable. And now that we have that, we can use that to describe those clusters. And here, what we're looking for, we are only interested in clusters who have a status of active. Through the course of business, in the course of whatever else, prototyping and sandboxes, you might find that you have clusters that you've deleted. And ECS doesn't really delete clusters, it just makes them inactive. And so here what we want to do is filter what's being displayed by clusters whose status is active. And then from there, we're going to further manipulate the output here, and by creating our own sort of custom object that's being output, and we're going to set the output to table view. So let's describe those clusters here. And you can see we have our Microservices Dev Ohio ECS cluster. And you can see at this point we have 3 EC2 instances that are members of this cluster. Those instances were able to join this cluster by having our autoscaling group create those instances. Their user data configured their ECS config file with the name of our ECS cluster being Microservices Dev Ohio. And all of that was done automatically. Those machines were created automatically by autoscaling, and through the use of user data, they joined the Microservices Dev Ohio cluster. Now that they've joined that cluster, they can be managed, or at least containers can now be managed on those EC2 instances. And that's how we can use the AWS CLI tools to create ECS clusters. Now let's take a look at creating a private Docker registry with AWS CLI. So in this lab, we have open our 9.3 bash commands. We're also going to open our accounts text file because we're going to need an account number here in just a minute. Now when we talk about deploying containerized services, ultimately what we deploy is a container image. The container image is our artifact. Up until now, we may have been accustomed to deploying zip files or jar, war, or ear files as artifacts. If we're deploying those as containers, then ultimately those files get wrapped in a Docker image, and now we need a place to put that Docker image. We need an artifact repository for that Docker image, and that is exactly what the Docker registry is for. And so we can use the Amazon EC2 container registry as a place to, as our repository, our artifact repository to hold our Docker images. All right, so in this example, we're going to be creating that repository in our admin account. We're going to use the admin profile, again, because our admin account is the source of publishing. We want to be able to take any Docker image and deploy it to any environment. So here we're going to call the ECR service. We're going to execute the create repository command and name that repository microservices billing. So you can see here, because we have a slash in the name, the repositories do support namespacing, and so we might have other applications that are not necessarily a part of our microservices collection that we are running as containers, but here, and this is up to you. You can find a naming scheme that makes sense for your particular business and application. In this example, we're just going to call this microservices billing. So we're going to go ahead and create that repository. There we go. Now we have our Docker registry created in our admin account. And now this is completely private. We can use IAM and all of the security controls of AWS to protect access to this registry. We're not going to be using, for deploying our applications, we're not going to use Docker Hub or something else. Now we have complete control over who can access this registry and who has access to our code and our Docker images. The next thing that we need to do is allow the development account to read from that repository so that our ECS cluster in the development account can pull images out of this registry. So here again, we're going to use the admin profile to set the repository policy. Again, specifying that particular repo by name, and what we're going to pass in is a JSON document that specifies the policy. This is a resource-based policy. And you can see here as we scroll over, what we need to change here is the development account number. So we're going to highlight that, and we're going to go over to our accounts file. We're going to copy our development account number, and we're going to paste it there. So I've pasted mine, you will paste yours, and now we can go ahead and let's go ahead and run that so that we grant the development account the ability to read from our central repository. And if we come back here and now we can say get repository policy, specifying the repo by name. Let's go ahead and run that, and you will see that it gives us back that particular policy. And if we look in here, you'll see that the principal, what we're looking for here is the principal, AWS, and there we should see our account numbers, our development account number. And that is how we can use the AWS CLI to create private Docker registries with the EC2 container registry. And of course, we would go on to create a private repository within ECR for every service that we go to create. All right, now let's take a look at building and pushing Docker images with the AWS CLI. Here in our code base, we have the 9.4 bash commands open. We also want to take a look at the source services billing server.js file. We're also going to take a look at source configs services billing config.json file. So let's first step back for a second and understand exactly what we are going to do ultimately at the end of this lab is have a Docker image being pushed to a remote registry, the registry that we created earlier. A Docker image represents the full encapsulation of not only our application, but all of our application dependencies as well. So we're taking our code, we are creating a Docker image out of that code and informing how that, once the image becomes a running container, what the process looks like. So before we build our image, let's just take a quick look at the code that will be included with this image so that we can understand the application that's going to be running. So here in our server.js file, I've got a very simple HTTP handler in here representing what is the foundation of what might become a microservice billing API. What I really want to point out is a few things that I want to point out here. One, we are including the AWS SDK for Node.js, and we're going to use that to pull in our configurations from our S3 bucket that we created earlier. So if we recall, we created a bucket for our configs, and of course, you named yours something unique, so you'll want to go ahead and modify this. Whatever you named your configs bucket, you'll want to put that value in here. Here, we're saying that the object that we want to pull from that is the config.json for the billing service. And then, of course, we're going to use the s3.getObject function to pull that from S3. Once we get that result back, the data we get back from that asynchronous request can then be parsed by JSON into a config object. And of course, we have defined config up here so that it is available, so that the scope of that is then available down here later. So later on, when we go to add routes and handlers for various other things, we can pass that config onto our database adapter and anything else that might need data out of that config. So the really nice thing about doing it this way is that we know, because of the bucket policy we put on this configs bucket, we know that that data is encrypted at rest. And by using the AWS SDK in this particular way, this guarantees that the object that we're downloading will never touch the disk. It's only ever in memory within our container. And so it's never touching disk unencrypted, except perhaps on our local machine. So this is just one way of allowing your applications to pull configurations from S3, or to pull configuration in at runtime. S3 is just one option. By all means, you could use other third-party tools like Console plus Vault. Those are really great options for doing service discovery and config storage. Amazon Systems Manager also has a parameter store that we could potentially use for that as well. So that's what our application is doing. It's going to pull in that config, and then once it has that configuration file, it's then going to run, and from there we're going to use the Morgan middleware to log all requests to standard out. And we're going to use the Docker container runtime environment to collect anything going to standard out will be collected and then shipped to CloudWatch logs. And we will see how we define that here in just a little bit in an upcoming lab. So from there, we're going to essentially respond to all GET requests by returning JSON and showing the version from our package. And of course, our package at this point says version 1. And then within our container, our application is going to listen on port 3000. And later, we're going to be mapping a container on the host to this container 3000 within the application. Okay, and so our config file, let's take a look at that. The config file in this case will contain, among potentially other things, information about our database. So the first thing that we might want to do here is go ahead and fill that in. So let's run a command here to pull the endpoint, the DNS endpoint information from the RDS instance that we created earlier. So I'm going to go ahead and run that. This is in our development environment. Enter my MFA code here. Okay, so once you perform that action, you will get back a very similar table. So what we're going to do is copy this particular endpoint. The port hasn't changed, but it might. In your case, you may have chosen a different port for RDS. So I'm going to copy that DNS endpoint. Remember that we always connect to RDS using DNS, never a hard-coded IP address, because IP addresses could change, and that's how Amazon enables automatic failover. So we configure our applications to connect to a DNS endpoint. Now we might also want to fill in our user. In this case, I believe I set mine to rjones and the password to OICU812 exclamation point. And of course, this information would be sensitive information. We really would want to control where that stuff is stored. And again, by storing it in S3 with server-side encryption, we know that it's encrypted at rest. The transfers between S3 and our local machines, between S3 and EC2, is all done over HTTPS, so that we know anytime this data leaves our local machine, it is always encrypted. And when it runs in our application, it's only ever in plain text, in memory, within our application. Okay, so now that we've got our config file configured and saved, we need to upload that to our configs bucket. So we're going to use, again, the admin profile, because all of our buckets are in our admin account. We're going to copy that, and you'll notice here at the very end, we're copying that to a very similar path within that bucket, but the bucket policy requires that this SSE AES 256 flag be set. So let's go ahead and upload that. There you go. Now we know that that particular object is encrypted on disk within AWS S3. Okay, so now that what we want to do, we have all of our configuration completed. We have our code in the place that we want it to be. Before we build our image, let's go ahead and find the repository URI from that ECR repository that we created earlier. We're going to run this describe repositories command, naming the microservices billing repository, and we want to use the query parameter to pull out the repository URI. Okay, so let's go ahead and we're going to capture that in a bash variable and echo that out so that we can see it. And there we are. That is the registry URI for our microservices billing Docker registry. We're going to use that here as a tag. You'll see here we're going to use Docker to build out our Docker image, and we're going to tag it with that repo URI at version 1. Notice here the version 1, and we're pointing to our source services billing at where we can find our Docker file. All right. So just real quick, let's go ahead and peek there at our Docker file here in services billing Docker file. Very, very simple and straightforward Docker file. They can be more complex than this, but this is just about all we really need for this simple application. We are telling Docker that we want to create an image based on the Node.js 6.11 Alpine Linux, which is very, very slim and trimmed down. Much lighter weight than something based on Debian or Ubuntu. We're going to instruct Docker to essentially start a container from Node 6.11 Alpine. We're then going to copy our package JSON from our local environment into that running container. We're then going to execute the npm install from within a container. We will copy everything else that we might have within this billing folder down here. We're going to expose port 3000, and then we're telling Docker when this image becomes a container, we want to execute the node process passing in source server.js as the first argument. Okay. So let's go ahead and use the docker build command to build that image. There you go. Now it's running all of the npm install, pulling in all of the dependencies that are listed within our package.json. So we have included Express, Morgan, and the AWS SDK. And of course, each of those will have their own dependencies. So that's what's happening right now. And of course, all of this, you can see here, it says, if you notice these intermediate containers, all of these particular functions that you're seeing right now are running within intermediate containers. And so ultimately what we end up with is this end result container that Docker grabs an image of, and that's what we can clone between environments by publishing it to a Docker registry, and then later we will point the ECS cluster to that registry to deploy this particular image. And there we go. It's continuous. Sometimes it looks like it gets stuck. And of course, my internet here might be a little bit slower. So yours may be faster or slower depending on your connection. And some packages have more dependencies than others. Okay? And there we go. We have, you can see here, successfully built a Docker image. And now let's just list our images, and we can see that we have the, in order for Docker to build that, it first needed the Node 6.11 Alpine image, and it also, then from that image it built ours. So here is our image tagged at version 1, and you can see it's about 88 megs. As far as deployment artifacts go, that is pretty lightweight. So this is one of the advantages of deploying via containers, is that you compare 88 megs with something like 8 gigs for a virtual machine image that includes the operating system and all of the other overhead. Now let's run that, and here we're going to use the docker run command. We're going to run it locally, and in order for that to happen, we're specifying a number of flags here. Namely, the ones that I really want to point out here are the environment tag. We need to tell the AWS SDK within the Node application to use the admin profile. And in order to find those credential files, we need to map our local .aws folder to a .aws folder within the container. We're also going to map our local port 8080 to port 3000 within the container because our application is configured to listen on port 3000. And then we're telling Docker, this is the image that we want to run. Okay? So I'm going to run that one. Let's go ahead and clear the screen. And you can see we ran that. I'll use the -d flag to run it as a daemon. First, let's do a docker ps. And you can see that we do have a Docker running, that it has mapped port 8080 to port 3000. It's running our node source server.js. So let's run a curl on localhost port 8080. And there we go. We got a message back saying billing service online version 1.0. We can run that one more time with -i and get the headers. And you can see here that within our code, we have overwritten the server header that says services billing version 1.0. From there, we can go docker ps one more time. And if we wanted to stop that container, we can say docker stop. We can copy that container ID, paste it there. You will do the same thing. Go ahead and stop that container. While that's happening, let's come back over here. So now we know that we have the image is built and we know it works locally. Now all we need to do is upload this image to the ECR registry. The first thing that we need to do before we do that is get the Docker login command from the EC2 container registry. So here, what I want you to do is let's copy in and paste our admin account number. Let's open up that accounts text file and copy our admin account number. We're going to paste that there. We're also going to paste our admin account number here. You will do the same thing with your account number. And I just want to show you, we're going to do this twice, but the first time I just want to show you what comes back. What comes back from this command, let's go ahead and clear that one more time. What comes back from the get login is a Docker command. Now we could, if we wanted to, we could copy this and then paste it into the shell, or better yet, we can simply run that with a pipe to bash. And then that will cause our local Docker client to be logged in and be authorized against the remote registry. Okay, so let's go ahead and log in to the remote registry by piping that to bash. And you will see there it says login succeeded. And now we can use the Docker push command to push that. Notice how we're pushing exactly what we tagged earlier. When we use the -t here in the build, that's exactly what we're going to push. So I'm going to go ahead and run that. And you can see it happens pretty quickly because we have only 88 megs to push. Now, we'll notice here as we move forward, when we go to update our code on subsequent pushes, this will be a whole lot faster because of the layered file system that Docker uses. Now that we've got that pushed, we can use the ECR list images command and specify the microservices billing registry to see the images that we have in that remote registry. And there we are. You can see that we have the images tagged at 1.0, and that is how we can use the AWS CLI to build and push Docker images to ECR. Now let's take a moment to understand task definitions, tasks, and services. When we use Amazon EC2 Container Service, we don't launch containers directly. Ultimately, we create task definitions, tasks, and services, and through those mechanisms, our containers get deployed and run. So the first thing is a task definition. And through the task definition, we define what our containers look like. A task is really a collection of running containers. Sometimes we might want one task to have one container. Sometimes we might want a task to have two containers running simultaneously, and perhaps those two containers need to be linked in a particular way. So perhaps one task is not just one process. Perhaps one task is multiple processes all running concurrently. So a task definition is really a collection of one or more container definitions. And in the container definition, we specify where our Docker image comes from, the URI of our Docker image. We will also specify which ports our container needs, how much CPU and how much memory our container needs, and also what we're going to do with logs, what the log driver will be. In this case, as you will see in the upcoming lessons, we will be using the CloudWatch logs log driver. A task, again, is a way of launching containers. The task will reference the task definition. Generally, we either will launch containers by way of creating tasks, which are really meant to be one-off, short-running processes, or we could create a service. A service is meant for long-running applications, like HTTP-based APIs. So again, a service is used to guarantee that we always have some number of tasks running at all times. Let's say that we are using containers to deploy a RESTful API, and for the sake of high availability and fault tolerance, we might want, say, 3 containers running across our cluster. The EC2 container service, when we create a service, that service will launch 3 tasks based on a task definition, which in turn will defines the containers that are run. If a task fails because of some kind of a bug in our code, then the service will replace that failed container. A service also integrates with elastic load balancing, and the service can automatically register instances behind a load balancer and configure the port that the container is listening on. So again, these are the 3 primary mechanisms that we interact with as far as using the Amazon EC2 Container Service. Task definitions being our collection of container definitions where we specify our Docker image. The task being the mechanism that actually runs a container based on that definition, and a service being a way of guaranteeing that we always have some number of tasks running. Here we'll take a moment to understand IAM roles and policies used for the Amazon EC2 Container Service. There are 3 primary roles that we need to be aware of if we're going to use the EC2 Container Service. So the first role is our container instance role. And the container instance role is applied to our EC2 instances that make up the body of our ECS cluster. And of course, all of these roles that we're talking about do have their own policies applied, and so it is through the role that our EC2 container instance retrieves temporary credentials, and it is through the policy that that those temporary credentials gain whatever permissions that they need. The other roles that we need to be aware of are the service role. Now, of course, I do want to take one minute to differentiate between the EC2 container service, which is managed by AWS, and the service that we create and we manage. So this service, really, we could say that this represents our application, regardless of how many containers are underneath it. And so each service that we create, in a case of microservices, this would be one service per microservice. And so each service that we create also needs a service role. And it is the service role and its attached policy that allows our service to communicate with elastic load balancing and register the instances and containers behind the elastic load balancer, if we're using that. The last role that we want to talk about here is the task role. And the task role is applied to our tasks. And through the task role, this is how we can grant our tasks the ability to communicate with other services like S3, DynamoDB, Simple Queue service, and so on. So again, we have our task roles that are specific to the tasks that are actually doing the work. We have our service role that allows the service to register containers behind the elastic load balancer. And we have our container instance role that allows our EC2 container instances to communicate with the EC2 container service and allow those EC2 container or instances to be managed by the EC2 container service. Now let's take a look at creating ECS roles and policies with AWS CloudFormation. Here in our code base, in our editor, we have 9.7 bash commands open. We're also going to open the CloudFormation Access Roles for ECS template. So let's take a look at that template and see what we're creating here. Now, we've already talked about the various roles that are necessary to make ECS work. We already created, very early on, we created the container instance role, the role that is applied to the EC2 instances so that they can communicate and be managed by ECS. And that role was already created and already applied by our autoscaling group launch configuration. What we still need to create before we can start deploying containers is the service role and the task role. So here in our template, we're creating the service role, which is again in this case, for our billing service to communicate and manage the elastic load balancer. So we're saying here that we're creating the ECS service role. We're going to name it that. We're going to allow the ECS service to assume this role. And what we're going to attach to it, the policies that we're going to attach, is one of the stock policies provided to us by AWS. And we can notice the managed policies rather than an inline policy. And here we are attaching the Amazon EC2 container service role, which grants permissions for the service to manage elastic load balancing on our behalf. The last thing that we're going to create in here is the task role for our billing service. And again, you can see here that we are allowing the ECS tasks service to assume this role. And we are going to create an inline policy specific for this task. Each microservice that you develop and deploy will get its own specific task role. And it will get inline policies here specific to what that task is doing. In this particular case, our billing service task needs the ability, you can see here, we're granting it the ability to download from S3 from this specific, not just from the bucket, but notice what we've done here. We've extended this to say that our billing service is allowed to download from the service's billing prefix. That way, our billing service cannot download configurations for other microservices. They're all isolated with this particular policy. Okay, so that's what we are building with this template. Let's go ahead and validate that template. Make sure that everything's okay, no syntax errors. Everything's fine, no parameters, but we do have IAM capabilities like we've seen before. And now we're going to create this in the development account using the dev profile, just like we've done before. So let's go ahead and create that stack. All right, there we go. Now we can wait for that to complete. Shouldn't take very long at all. And there we are. Our stack has finished. Now we can verify that we've created those roles by calling the IAM service list roles command and querying by role name. Output that to a table so it's easy to read. And there we are. We can see all of the other roles that we created earlier, plus here is the service role and the task role that we just created. And again, what you'll want to do is as you go through and add more microservices, you will add a task role for each service, and each task role will get policies and permissions specific to the needs of that particular service. And that is how we can use AWS CloudFormation to create and manage roles for ECS. All right, now let's create a task definition using the AWS CLI. Let's first open our 9.8 bash commands. We're also going to open our source, configs, billing services, task definition.json. So the task definition ultimately describes what containers run as a part of that task. It could be one container, it could be 2, 3, or more containers all linked together that need to run simultaneously. For our billing microservice, we only need one container and one application. And so in our task definition, we are going to use that to define our container definitions, which will include essentially a list of one container. We're going to name our container billing-node.js. Our image for now, we're going to come back and automate the update of that value here in just a little bit. For now, we're going to leave that blank and fill that in an automated way. We're specifying that this container is going to get 100 units worth of CPU. We're going to also give it 128 megs worth of memory, which is probably plenty. We're going to say that this container is essential. What that means is that if the container fails, then the task fails. And if the task fails when we're running in a service, the service will replace the container or replace that task, and the task will rebuild a new container. We're also going to specify for our log configuration that the driver should be AWS logs, which is CloudWatch logs, and we need to configure that to say that we're going to group this into the microservices billing logs group, and all of these will function in the US East 2 region. We're also going to specify some port mappings so that we are mapping port 3000 within the container to some port on the host machine. Now you'll notice here that we've specified port 0 for the host port. By doing that, we allow the ECS system to choose a random port from within a particular range, and that's called dynamic port mapping. By doing that, we can enable the ability to run more than one container of this particular service per EC2 instance. If we did something like this, if we were to do static port mapping, then we could only run one billing service container per host. But by opening it up to random ports, then we really enable a lot more flexibility. We also enable a much easier automatic configuration of our application load balancer. So that's what our task definition file looks like. Okay, now let's take a look at how we can automate the creation of a task definition using this file. So remember that our image attribute is currently still blank, but we're going to fill that in using the CLI tools. So what we're going to use for the value of that image property is a combination of the repo URI and the version. So before we do that, let's go ahead and capture those. And again, we're going to use the ECR service, the describe repositories command, to pull out the repository URI and capture that in a variable. And of course, we're going to echo that out so that we can see it. Okay, so let's go ahead and do that. Okay, we have our registry URI. Now we're going to use JQ to pull out the version property from our billing package.json. So we're going to cat that and pipe it to JQ, and we can use the -r, which is raw, and otherwise it would come out with quotes on it. We don't want that. So we're going to capture the version and echo it. There we go. We've pulled 1.0.0 out of our package.json file. Now we're going to use a little bit of bash magic to do what we might call in-place editing of that task definition file. So this is fairly advanced and somewhat arcane. So I'm not going to go into all of the details of exactly what's happening here, but suffice it to say, through this particular line, we will essentially be opening that task definition file, taking the contents, piping it into JQ, and using JQ to replace the image property with our repo URI and our version, and then writing that contents of that file back to the same file. So let's go ahead and do that, and then we will see exactly what happens to our task definition file. Just like that. Now let's take a look at our task definition, and you'll see that JQ added that in place. So that avoids the need for us to copy and paste, right? So that's exactly what we don't want to do. We want to remove as many manual steps as possible, and that's one of the pieces of bash magic that we can use to even automate the editing of our task definition file, because ultimately when we go to deploy subsequent versions of our application, we will need to update this value here. We might go to 1.1, we might go on to 2.0, and we may very well even point to a different registry URI, right? So we want the ability to, a very easy ability to update that image during deployments. Some of these other options we might want to do manually because they might be rare. Okay, so now that we've got our image recorded, the next thing that we want to do is get the role ARN. So remember that we created a role specifically for the billing service task. So we're going to get that role by name, and we're going to query for the ARN of that, output it as text, and capture that again into a bash variable. Let's go ahead and do that. And again, because we're in our dev account, let's go ahead and enter our MFA token. Just going to let this reset here. Okay, there is our ARN. And now what we need to do is create that task definition, and we do that calling the ECS service. We're going to register a task definition, specifying the role that we just pulled. And we're going to use the CLI input JSON parameter to specify that task definition JSON file that we just edited. Let's go ahead and do that. Create that task definition in our development account, and there we are. Now we can use the ECS list task definitions to see that we have for this family, for the microservices billing service, we can list those task definitions. There we are. Now you do see that I have a number of them. I have 1, 2, and 3. That's from work that I've been doing to prepare this particular lab. At this point, you may only have one, and that's okay. So if you only have one task definition and I have 3, then that's perfectly fine. You'll still be able to move forward. So that's how we can use a little bit of magic within the Bash shell or ZSH, whatever the case may be, and how we can use the AWS CLI tools to automate the creation of task definitions, which will be an integral part of deploying your applications to the EC2 container service. Now let's create a service with the AWS CLI. Here in our code base, we have 9.9 bash commands open. So if you recall what we talked about earlier, the service in this context, a service within the EC2 container service, it represents one of our microservices. In this case, we're going to create a service that represents our billing microservice. And within the context of ECS, the service is responsible for keeping a certain number of tasks running at all times. If one of those tasks fails as a result of a container failing, then the service will replace that task, which will replace the container, right? So it's through a service that we can achieve fault tolerance and high availability in our containers. So before we can create a service, we need a number of pieces of information. We're going to need the role ARN of the service role that we created earlier. And so we're going to use the IAM-GetRole function to capture that and output that as text and capture it to a variable. So let's go ahead and do that. There we are. There is the role ARN for the service role, not to be confused with the EC2 container instance role or the task role, right? This is the service role that will be applied to the service itself. The next thing that we want to do is get the latest task definition. We just created a task definition that represents the state of the container that we're deploying. And what we want to do here is use the ECS service list task definitions command, and we're listing task definitions for the microservices billing family, and we're going to sort those descending so that we can pull off the first one, which will be the latest one. And we're going to capture that in a variable. So let's go ahead and do that. And again, you'll see here what we're seeing here is the ARN of that task definition. And you'll notice that in mine it says :3 because in my case, the latest version that I have is task definition version 3. Yours may very well say version 1. And again, that's okay. I've done some work before this, which is why I'm seeing the number 3. If you see the number 1 here, everything is still okay. The next thing that we want to do is, if you recall, we created an application load balancer. That's why we're seeing here we're going to use the ELB v2 service, which is application load balancer. And we created a target group specifically for our billing microservice. So we need to grab the ARN of that target group, which we will use later when we create the service. So let's go ahead and capture the target group ARN. There we are, we have that target group. Now, one more thing that we need to do before we create the service is, if you recall in our task definition, we configured our container to send logs to the AWS CloudWatch logs service. And we configured it with a particular group, and that group name is called microservices billing. Now, before we can create the service, we need to make sure that we have that log group actually exists within the CloudWatch logs service. So we're going to use the logs service create log group command to create a log group named microservices billing, which lines up with everything that we configured within our task definition. We only need to do this when we create new services. And in this regard, again, as we move forward and create more microservices, each service will get its own log group. At least that's the pattern that I'm using. You don't have to do it that way. You could put all of your services into one log group if you really wanted to. You could split out log groups by in any ways that make sense to you. In this example, we're grouping all of our log streams by microservice, and that's why we're creating it in the way we are. Okay, so let's go ahead and create that log group. There we are. It came back with generally when things come back with no feedback, it means that everything went well. If there was an error, it would be explicit about that. So we have our log group created. Now we're going to use the ECS create service command to create a service which will keep a certain number of tasks running at all times. Here we are specifying the microservices dev Ohio cluster that we created earlier, which is running on an auto-scaling group of EC2 instances of the same name. We're going to name our service billing. We're saying here that we want 3 tasks to be running at all times. If a task fails for whatever reason, because of an error in our code, because the EC2 instance failed, because an availability zone failed, whatever the reason, the service that we're creating will guarantee that we always have 3 tasks running. We're going to specify the current task definition that we captured. We're going to specify the role of that service role ARN. We're also going to specify a load balancer's configuration. And here we're saying that this service should be a part of this particular target group that we captured up here. We have a target group specifically for the billing microservice. And we're saying that when requests come in through the load balancer and they get forwarded to that target group, that we're looking for the billing Node.js container. Again, we configured that within our task definition. And that the container port is 3000. And so it will look to that EC2 instance. It'll query Docker to figure out, hey, what's the port that 3000 is mapped to on the host machine? And all of the overhead of configuring that dynamic port mapping between the container and the load balancer is handled by the service. The next thing that I want to draw your attention to is the deployment configuration. Notice here what we're saying is we're setting a maximum percentage of 200 and a minimum healthy percent to 100. So what that means is that under all circumstances, there should always be 100% of the 3 desired running. We're saying that by setting a maximum percent of 200%, that means that we are going to allow this service to double in size under certain conditions. And one of those conditions would be during a deployment. And you'll see that here in an upcoming lab. When we deploy a new version of the service, by setting the maximum to 200 and the minimum to 100, it allows 3 containers or 3 tasks of a new version to come up alongside the old ones before removing the old ones. So it's a really easy way of achieving essentially a form of blue-green deployments by bringing up a completely new system before tearing down the old system. Okay, so now let's go ahead and do that. Let's create that service. Okay, and let's take a look here. You can see our service is now active using the latest version of our task definition. You can see some of our load balancers. Here's our container name that we configured, the target group, the container port. You can see that we've attached the ECS service role that we created earlier, the service name that we configured. And here is the current deployment. Right here says primary. Desired count of 3, that's 3 tasks. And so now what we want to wait for is for those tasks to create containers, for those containers to spawn the node process, for it to do whatever bootstrapping it needs to do and settle into a steady state. And so we're going to wait, we're going to use the ECS waiter to wait for the service's stable status. And we're going to specify that cluster and our billing service. All right, so let's go ahead and run that wait command. Okay, so now you can see that our service has settled into a steady state, which means our tasks have created containers, and those containers have spawned our node application. Had any of the applications failed, it would have caused the container to fail, and it would have caused the task to fail. It would have caused the service to respawn the task. And so if you're ever in a state of constantly respawning tasks, then the service can never really stabilize. It can never really reach a stable state. And so the fact that we reached a steady state meant that all of our tasks created all of the necessary containers, and our applications are indeed running like they should. Okay, so now we're going to, we want to describe the clusters, but before we can do that, we need to capture some information from the list clusters command. All right, so let's go ahead and do that. Capture a list of cluster ARNs. Now we can describe the clusters, and here what we're going to do is we're looking for clusters whose status equals active, because you could, through the course of events, end up with ACS clusters that are no longer active. The ECS never really deletes clusters, it only makes them inactive. And so we're only looking for ones that are currently active. And again, we're going to, using this curly brace, we're going to format our own data here. We're going to customize the output of this data. And we're looking for the number of registered container instances, the number of services, the number of tasks that are pending, and so on. And again, we're going to output that as a table. So let's go ahead and run that. Describe the clusters. And you can see here that in our microservices dev Ohio cluster, we have 3 EC2 instances that are a part of it. And on those instances, we have 3 tasks running. And our task definition specifies 1 container each. So that means that we have 3 containers currently running. Nothing is pending, which means that we can use this to verify that, yes, indeed, all of our tasks and containers have settled into a stable running state. And of course, you can see that we have 1 service. As you go to create more microservices, this number will, of course, increase. Okay, now let's use the ELB v2 service to describe our load balancers. And what we want to pull from here is the DNS name of our load balancer. At this point, we only have 1 load balancer, so we know it will be at index 0 in that list. Okay, so let's go ahead and capture the endpoint of our application load balancer. You can see here, you should see something like this: microservices dev Ohio, and then some random number, US East 2. And of course, we will send, ultimately, if we were to deploy this in production, we will send our users to this endpoint by way of CNAME or alias records within Route 53. Now we can use curl. Let's go ahead and curl that. And we should see, there we are, we can see that our billing service is online at version 1.0. And if we want to look at the headers of that, you can see that it's sending the server header, specifying the billing service at version 1.0. So that's how we can use the AWS CLI tool to create services within the EC2 container service. All right, now let's take a look at updating a service with the AWS CLI. Here in our code base, we have several files open. We have our 9.10 bash commands. We also have, down here in services billing, we have our package.json file open. In our source scripts, we have our update service shell script, and then we also have our accounts text file open. So here what we're doing is we're going to make a change to our application and then rebuild the Docker container, create a new task definition, and use that new task definition to update the service. And that's how you can continually deploy applications or microservices to the EC2 container service. So let's just mimic a change to our application. We don't really need to get into code right now. All we're going to do for the sake of this lab and proving how things can be done is just make a change to the version. So here we're going to go from 1.0 to 1.1. We're just going to save the package.json file. And now we're going to run everything that we've done earlier to deploy that or upload that to the registry and create a task definition based on that Docker image. We're going to automate all of that and see how that can be done in one fell swoop with a bash script. So let's take a look at the update service shell script. And again, this is all the things that we've done before, grabbing the repo URI, grabbing the version from that package.json that we just changed, using those two to build a new version of the Docker image. We're then going to make sure that that Docker is logged in to that private registry. So at this point here, let's go ahead and highlight this admin account number placeholder. We're going to go to our accounts text file. You're going to copy the admin account number, paste it there. Go ahead and save the update service.shell script. Now the rest of it is fully automated. We will then use, now that Docker is logged in, Docker can push, and everything else, we can grab the role, use JQ to update the image in that task definition file. And the only real difference between this and create service is the pretty obvious change down here, update service instead of create service. So we're specifying, again, the cluster that we are working on, the billing service, and the task definition. And now the settings that we used when we created the service was that the service was allowed to have up to 200% of its tasks. And we specified that we wanted 3 tasks running, but we're allowing it to go up to 6 tasks. And so during an update, it will first create the new tasks with the new version, the updated task definition. And then once those settle into a steady state, it will then go back and delete the original tasks. So that, again, is essentially a very easy blue-green deployment. Okay, so now all we need to do is execute our shell script. You can see it found our version 1.1, and now it's rebuilding the Docker image pulling in all of our NPM packages. There we go. We've built that image, and now it's pushing that to the remote repository. You can see the effects of the layered file system, that some of the layers already exist. And there we go. And because let me just go back here. Some of the layers already exist. Essentially what that means is that because Docker is using that layered file system, that when we create updates to an image, sometimes some of the data already exists. Docker can reuse some of the data so that we don't have to push the entire 80 meg image all over again. We only need to push deltas, essentially, or at least something like deltas. So that means that as we create new versions of our image, that deployments become faster than the initial create service or the initial push of the image. You can see here that we have a new version of our task definition. You should see a new version of your task definition. I happen to be at 4. You might be at 2 or 3, depending on where you are in the lab. And you can see down here we have some events. It has registered some targets, registered some new tasks. Now what we can do is we can describe our services again, that cluster, the microservices dev Ohio cluster billing service, and let's take a look at the deployments that are happening. Again, I have to enter our PIN, and you can see that we have 2 deployments, one being the new version, one being the old version. We have, and in my case, I went from 3 to 4, and my the old version, version number 3, has 0 running tasks. So we're seeing the effects of that 200% capacity that we've specified earlier, bringing up the 3 new ones before cleaning up the 3 old ones. And now if we do this again, try those deployments again. There we go. And now you can see we only have 1 deployment, and the desired count is 3, the running count is 3. Here's the latest version of my task definition, so that means that my automated deployment of a new Docker image succeeded. So let's go ahead and grab the endpoint again, make sure that we have the DNS name of our load balancer, and curl that. I'm going to look back in my history by hitting Control-R and typing curl, and I'm going to go ahead and play this one here with the -i, and you can see that I'm now getting the billing service at version 1.1. And if I try that again without the -i, you can see that I am indeed getting the right version in the messages. So that's how we can automate the deployments of our Docker containers by updating a service with new versions of task definitions based on new Docker images. Throughout this course, we've created and managed numerous resources with ease, with a level of automation that is difficult, if not impossible, with traditional on-premises infrastructure. We've seen just how effective tools like the AWS command line interface, AWS CloudFormation, and the Python SDK can be at automating our environments. I highly encourage you to not only perform these labs again, perhaps in a second region, but take inspiration from the code. Use it to automate your own infrastructure. Thank you so much for joining me in this Amazon Web Services Linux Operations live lessons course. I really do appreciate you spending so much time with me and allowing me to share my experience. I hope you've gained some valuable experience, and I wish you the very best in your career automating applications in the cloud with AWS.